A basic but adequate model that is sufficient for our purposes is that each node can communicate with all other nodes that lie within its coverage circle. Real networks are more complicated, with buildings, hills, and other obstacles that block communication, and nodes for which A is connected to B, but B is not connected to A, because A has a more powerful transmitter than B. However, for simplicity, we will assume all connections are symmetric. To describe the algorithm, consider the newly formed ad hoc network of figure 5 to 20. Suppose that a process at node A wants to send a packet to node I. The AODV algorithm maintains a distance vector table at each node, keyed by destination, giving information about that destination, including the neighbor to which to send packets to reach the destination. First, A looks in its table and does not find an entry for I. It now has to discover a route to I. This property of discovering routes only when they are needed is what makes this algorithm on demand. Figure 5 to 20. Range of A's broadcast. B. After B and D receive it. C. After C, F, and G receive it. D. After E, H, and I receive it. The shaded nodes are new recipients. The dashed lines show possible reverse routes. The solid lines show the discovered route. To locate I, A constructs a route request packet and broadcasts it using flooding, as described in Secretary 5.2.3. The transmission from A reaches B and D, as illustrated in figure 5 to 20. Each node rebroadcasts the request, which continues to reach nodes F, G, and C in figure 5 to 20, C, and nodes H, E, and I in figure 5 to 20, D. A sequence number set at the source is used to weed out duplicates during the flood. For example, D discards the transmission from B in figure 5 to 20, C, because it has already forwarded the request. Eventually, the request reaches node I, which constructs a route reply packet. This packet is unicast to the sender along the reverse of the path followed by the request. For this to work, each intermediate node must remember the node that sent it the request. The arrows in figure 5 to 20, B, D, show the reverse route information that is stored. Each intermediate node also increments a hop count as it forwards the reply. This tells the nodes how far they are from the destination. The replies tell each intermediate node which neighbor to use to reach the destination. It is the node that sent them the reply. Intermediate nodes G and D put the best route they hear into their routing tables as they process the reply. When the reply reaches A new route, a G, has been created. In a large network, the algorithm generates many broadcasts, even for destinations that are close by. To reduce overhead, the scope of the broadcasts is limited using the I packet's time to live field. This field is initialized by the sender and decremented on each hop. If it hits 0, the packet is discarded instead of being broadcast. The route discovery process is then modified as follows. To locate a destination, the sender broadcasts a route request packet with time to live set to 1. If no response comes back within a reasonable time, another one is sent, this time with time to live set to 2. Subsequent attempts use 3, 4, 5, etc. In this way, the search is first attempted locally, then in increasingly wider rings. Route maintenance. Because nodes can move or be switched off, the topology can change spontaneously. For example, in figure 5 to 20, if G is switched off, A will not realize that the route it was using to I, a G, is no longer valid. The algorithm needs to be able to deal with this. Periodically, each node broadcasts a hello message. Each of its neighbors is expected to respond to it. If no response is forthcoming, the broadcaster knows that that neighbor has moved out of range or failed and is no longer connected to it. Similarly, if it tries to send a packet to a neighbor that does not respond, it learns that the neighbor is no longer available. This information is used to purge routes that no longer work. For each possible destination, each node, N, keeps track of its active neighbors that have fed it a packet for that destination during the last seconds. When any of N's neighbors becomes unreachable, it checks its routing table to see which destinations have routes using the now gone neighbor. For each of these routes, the active neighbors are informed that their route via N is now invalid and must be purged from their routing tables. In our example, D purges its entries for G and I from its routing table and notifies A, which purges its entry for I in the general case. The active neighbors tell their active neighbors, and so on, recursively, until all routes depending on the now gone node are purged from all routing tables. At this stage, the invalid routes have been purged from the network, and senders can find new valid routes by using the discovery mechanism that we described. However, there is a complication. Recall that distance vector protocols can suffer from slow convergence or count to infinity problems after a topology change in which they confuse old invalid routes with new valid routes. To ensure rapid convergence, routes include a sequence number that is controlled by the destination. The destination sequence number is like a logical clock. The destination increments it every time that it sends a fresh route reply. Senders ask for a fresh route by including in the route request the destination sequence number of the last route they used, which will either be the sequence number of the route that was just purged, or 0 as an initial value. The request will be broadcast until a route with a higher sequence number is found. Intermediate nodes store the routes that have a higher sequence number, or the fewest hops for the current sequence number. In the spirit of an on-demand protocol, intermediate nodes only store the routes that are in use. Other route information learned during broadcasts is timed out after a short delay. Discovering and storing only the routes that are used helps to save bandwidth and battery life compared to a standard distance vector protocol that periodically broadcasts updates. So far, we have considered only a single route. From A to I to further save resources, route discovery and maintenance are shared when routes overlap. For instance, if B also wants to send packets to I, it will perform route discovery. However, in this case the request will first reach D, which already has a route to I. Node D can then generate a reply to tell B the route without any additional work being required. There are many other ad hoc routing schemes. Another well-known on-demand scheme is DSR, Dynamic Source Routing, Johnson and others, 2001. A different strategy based on geography is explored by GPSR, Greedy Perimeter Stateless Routing, Karp and Kung, 2000. If all nodes know their geographic positions, forwarding to a destination can proceed without route computation by simply heading in the right direction and circling back to escape any dead ends. Which protocols win out will depend on the kinds of ad hoc networks that prove useful in practice. 5.3 Congestion control algorithms. Too many packets present in a part of the network causes packet delay and loss that degrades performance. This situation is called congestion. The network and transport layers share the responsibility for handling congestion. Since congestion occurs within the network, it is the network layer that directly experiences it and must ultimately determine what to do with the excess packets. However, the most effective way to control congestion is to reduce the load that the transport layer is placing on the network. This requires the network and transport layers to work together. In this chapter we will look at the network aspects of congestion. In chapter 6, we will complete the topic by covering the transport aspects of congestion. Figure 5-21 depicts the onset of congestion. When the number of packets hosts send into the network is well within its carrying capacity, the number delivered is proportional to the number sent. If twice as many are sent, twice as many are delivered. However, as the offered load approaches the carrying capacity, bursts of traffic occasionally fill up the buffers inside routers and some packets are lost. These lost packets consume some of the capacity, so the number of delivered packets falls below the ideal curve. The network is now congested. Figure 5-21. With too much traffic, performance drops sharply. Unless the network is well designed, it may experience a congestion collapse, in which performance plummets as the offered load increases beyond the capacity. This can happen because packets can be sufficiently delayed inside the network that they are no longer useful when they leave the network. For example, in the early internet, the time a packet spent waiting for a backlog of packets ahead of it to be sent over a slow 56 kbps link could reach the maximum time it was allowed to remain in the network. It then had to be thrown away. A different failure mode occurs when senders retransmit packets that are greatly delayed, thinking that they have been lost. In this case, copies of the same packet will be delivered by the network, again wasting its capacity. To capture these factors, the y-axis of figure 5 to 21 is given as goodput, which is the rate at which useful packets are delivered by the network. We would like to design networks that avoid congestion where possible and do not suffer from congestion collapse if they do become congested. Unfortunately, congestion cannot wholly be avoided. If all of a sudden, streams of packets begin arriving on 3 or 4 input lines and all need the same output line, a queue will build up. If there isn't sufficient memory to hold all of them, packets will be lost. Adding more memory may help up to a point, but Nagel, 1987, realized that if routers have an infinite amount of memory, congestion gets worse, not better. This is because by the time packets get to the front of the queue, they have already timed out repeatedly and duplicates have been sent. This makes matters worse, not better. It leads to congestion collapse. Low bandwidth links or routers that process packets more slowly than the line rate can also become congested. In this case, the situation can be improved by directing some of the traffic away from the bottleneck to other parts of the network. Eventually, however, all regions of the network will be congested. In this situation, there is no alternative but to shed load or build a faster network. It is worth pointing out the difference between congestion control and flow control, as the relationship is a very subtle one. Congestion control has to do with making sure the network is able to carry the offered traffic. It is a global issue involving the behavior of all the hosts and routers. Flow control, in contrast, relates to the traffic between a particular sender and a particular receiver. Its job is to make sure that a fast sender cannot continually transmit data faster than the receiver is able to absorb it. To see the difference between these two concepts, consider a network made up of 100 Gbps fiber optic links on which a supercomputer is trying to force feed a large file to a personal computer that is capable of handling only 1 Gbps. Although there is no congestion, the network itself is not in trouble. Flow control is needed to force the supercomputer to stop frequently, to give the personal computer a chance to breathe. At the other extreme, consider a network with 1 Mbps lines and 1000 large computers, half of which are trying to transfer files at 100 kbps to the other half. Here, the problem is not that of fast senders overpowering slow receivers, but that the total offered traffic exceeds what the network can handle. The reason congestion control and flow control are often confused is that the best way to handle both problems is to get the host to slow down. Thus, a host can get a slowdown message either because the receiver cannot handle the load or because the network cannot handle it. We will come back to this point in chapter 6. We will start our study of congestion control by looking at the approaches that can be used at different time scales. Then we will look at approaches to preventing congestion from occurring in the first place, followed by approaches for coping with it once it has set in. 5.3.1 Approaches to congestion control. The presence of congestion means that the load is temporarily greater than the resources in a part of the network can handle. Two solutions come to mind: increase the resources or decrease the load. As shown in figure 5 to 22, these solutions are usually applied on different timescales to either prevent congestion or react to it once it has occurred. Traffic-aware routing, network provisioning, traffic throttling, admission control, load shedding, slower, preventative, faster, reactive. Figure 5 to 22. Timescales of approaches to congestion control. The most basic way to avoid congestion is to build a network that is well matched to the traffic that it carries. If there is a low bandwidth link on the path along which most traffic is directed, congestion is likely. Sometimes resources can be added dynamically when there is serious congestion, for example, turning on spare routers or enabling lines that are normally used only as backups. to make the system fault tolerant, or purchasing bandwidth on the open market. More often, links and routers that are regularly heavily utilized are upgraded at the earliest opportunity. This is called provisioning and happens on a timescale of months, driven by long-term traffic trends. To make the most of the existing network capacity, routes can be tailored to traffic patterns that change during the day as network users wake and sleep in different time zones. For example, routes may be changed to shift traffic away from heavily used paths by changing the shortest path weights. Some local radio stations have helicopters flying around their cities to report on road congestion to make it possible for their mobile listeners to route their packets, cars, around hotspots. This is called traffic-aware routing. Splitting traffic across multiple paths is also helpful. However, sometimes it is not possible to increase capacity. The only way then to beat back the congestion is to decrease the load. In a virtual circuit network, new connections can be refused if they would cause the network to become congested. This is called admission control. At a finer granularity, when congestion is imminent, the network can deliver feedback to the sources whose traffic flows are responsible for the problem. The network can request these sources to throttle their traffic, or it can slow down the traffic itself. Two difficulties with this approach are how to identify the onset of congestion and how to inform the source that needs to slow down. To tackle the first issue, routers can monitor the average load, queuing delay, or packet loss. In all cases, rising numbers indicate growing congestion. To tackle the second issue, routers must participate in a feedback loop with the sources. For a scheme to work correctly, the timescale must be adjusted carefully. If every time 2 packets arrive in a row, a router yells stop, and every time a router is idle for 20 sec, it yells GO, the system will oscillate wildly and never converge. On the other hand, if it waits 30 minutes to make sure before saying anything, the congestion control mechanism will react too sluggishly to be of any use. Delivering timely feedback is a non-trivial matter. An added concern is having routers send more messages when the network is already congested. Finally, when all else fails, the network is forced to discard packets that it cannot deliver. The general name for this is load shedding. A good policy for choosing which packets to discard can help to prevent congestion collapse. 5.3.2 Traffic-aware routing. The first approach we will examine is traffic-aware routing. The routing schemes we looked at in Secretary 5.2 used fixed link weights. These schemes adapted to changes in topology, but not to changes in load. The goal in taking load into account when computing routes is to shift traffic away from hotspots that will be the first places in the network to experience congestion. The most direct way to do this is to set the link weight to be a function of the fixed link bandwidth and propagation delay plus the variable measured load or average queuing delay. Least weight paths will then favor paths that are more lightly loaded, all else being equal. Traffic-aware routing was used in the early internet according to this model, Kanner and Zinke, 1989. However, there is a peril. Consider the network of figure 5-23, which is divided into 2 parts, east and west, connected by 2 links, CF and EI. Suppose that most of the traffic between east and west is using link CF, and, as a result, this link is heavily loaded with long delays. Including queuing delay in the wait used for the shortest path calculation will make EI more attractive. After the new routing tables have been installed, most of the east-west traffic will now go over EI, loading this link. Consequently, in the next update, CF will appear to be the shortest path. As a result, the routing tables may oscillate wildly, leading to erratic routing and many potential problems. Figure 5-23. A network in which the east and west parts are connected by 2 links. If load is ignored, and only bandwidth and propagation delay are considered, this problem does not occur. Attempts to include load, but change weights within a narrow range only slow down routing oscillations. 2 techniques can contribute to a successful solution. The first is multipath routing, in which there can be multiple paths from a source to a destination. In our example, this means that the traffic can be spread across both of the east to west links. The second one is for the routing scheme, to shift traffic across routes slowly enough that it is able to converge, as in the scheme of Gallagher, 1977. Given these difficulties, in the internet routing protocols do not generally adjust their routes depending on the load. Instead, adjustments are made outside the routing protocol by slowly changing its inputs. This is called traffic engineering 5.3.3 admission control 1 technique that is widely used in virtual circuit networks to keep congestion at bay as admission control. The idea is simple. Do not set up a new virtual circuit unless the network can carry the added traffic without becoming congested. Thus, attempts to set up a virtual circuit may fail. This is better than the alternative, as letting more people in when the network is busy just makes matters worse. By analogy, in the telephone system, when a switch gets overloaded it practices admission control by not giving dial tones. The trick with this approach is working out when a new virtual circuit will lead to congestion. The task is straightforward in the telephone network because of the fixed bandwidth, of course, 64 kbps for uncompressed audio. However, virtual circuits in computer networks come in all shapes and sizes. Thus, the circuit must come with some characterization of its traffic if we are to apply admission control. Traffic is often described in terms of its rate and shape. The problem of how to describe it in a simple, yet meaningful way is difficult, because traffic is typically bursty. Their average rate is only half the story. For example, traffic that varies while browsing the web is more difficult to handle than a streaming movie with the same long-term throughput, because the bursts of web traffic are more likely to congest routers in the network. A commonly used descriptor that captures this effect is the leaky bucket or token bucket. A leaky bucket has two parameters that bound the average rate and the instantaneous burst size of traffic. Since leaky buckets are widely used for quality of service, we will go over them in detail in Secretary 5.4. Armed with traffic descriptions, the network can decide whether to admit the new virtual circuit. One possibility is for the network to reserve enough capacity along the paths of each of its virtual circuits that congestion will not occur. In this case, the traffic description is a service agreement for what the network will guarantee its users. We have prevented congestion, but veered into the related topic of quality of service a little too early. We will return to it in the next section. Even without making guarantees, the network can use traffic descriptions for admission control. The task is then to estimate how many circuits will fit within the carrying capacity of the network without congestion. Suppose that virtual circuits that may blast traffic at rates up to 10 megabits per second all pass through the same 100 Mbps physical link. How many circuits should be admitted? Clearly, 10 circuits can be admitted without risking congestion, but this is wasteful in the normal case, since it may rarely happen that all 10 are transmitting full blast at the same time. In real networks, measurements of past behavior that capture the statistics of transmissions can be used to estimate the number of circuits to admit, to trade better performance for acceptable risk. Admission control can also be combined with traffic-aware routing by considering routes around traffic hotspots as part of the setup procedure. For example, consider the network illustrated in Figure 5-24, in which two routers are congested, as indicated. A congestion virtual circuit congestion BAB. B. Figure 5-24. A congested network. B. The portion of the network that is not congested. A virtual circuit from A to B is also shown. Suppose that a host attached to router A wants to set up a connection to a host attached to router B. Normally, this connection would pass through one of the congested routers. To avoid this situation, we can red row the network as shown in Figure 5-24, B, omitting the congested routers and all of their lines. The dashed line shows a possible route for the virtual circuit that avoids the congested routers. Shake and others, 1999, give a design for this kind of load-sensitive routing. 5.3.4 Traffic throttling in the internet and many other computer networks. Senders adjust their transmissions to send as much traffic as the network can readily deliver. In this setting, the network aims to operate just before the onset of congestion. When congestion is imminent, it must tell the senders to throttle back their transmissions and slow down. This feedback is business as usual, rather than an exceptional situation. The term congestion avoidance is sometimes used to contrast this operating point with the one in which the network has become overly congested. Let us now look at some approaches to throttling traffic that can be used in both datagram networks and virtual circuit networks. Each approach must solve two problems. First, routers must determine when congestion is approaching, ideally before it has arrived. To do so, each router can continuously monitor the resources it is using. Three possibilities are the utilization of the output links, the buffering of queued packets inside the router, and the number of packets that are lost due to insufficient buffering. Of these possibilities, the second one is the most useful. Averages of utilization do not directly account for the burstiness of most traffic. A utilization of 50% may be low for smooth traffic and too high for highly variable traffic. Counts of packet losses come too late. Congestion has already set in by the time that packets are lost. The queuing delay inside routers directly captures any congestion experienced by packets. It should be low most of time, but will jump when there is a burst of traffic that generates a backlog. To maintain a good estimate of the queuing delay, D, a sample of the instantaneous queue length, S, can be made periodically, and D updated according to new equals R plus 1, S, where the constant determines how fast the router forgets recent history. This is called an UMA, exponentially weighted moving average. It smooths out fluctuations, and is equivalent to a low pass filter. Whenever D moves above the threshold, the router notes the onset of congestion. The second problem is that routers must deliver timely feedback to the senders that are causing the congestion. Congestion is experienced in the network, but relieving congestion requires action on behalf of the senders that are using the network. To deliver feedback, the router must identify the appropriate senders. It must then warn them carefully without sending many more packets into the already congested network. Different schemes use different feedback mechanisms, as we will now describe. Choke packets. The most direct way to notify a sender of congestion is to tell it directly. In this approach, the router selects a congested packet and sends a choke packet back to the source host, giving it the destination found in the packet. The original packet may be tagged, a header bit is turned on, so that it will not generate any more choke packets farther along the path, and then forwarded in the usual way. To avoid increasing load on the network during a time of congestion, the router may only send choke packets at a low rate. When the source host gets the choke packet, it is required to reduce the traffic sent to the specified destination, for example, by 50%. In a datagram network, simply picking packets at random when there is congestion is likely to cause choke packets to be sent to fast senders because they will have the most packets in the queue. The feedback implicit in this protocol can help prevent congestion, yet not throttle any sender unless it causes trouble. For the same reason, it is likely that multiple choke packets will be sent to a given host and destination. The host should ignore these additional chokes for the fixed time interval until its reduction in traffic takes effect. After that period, further choke packets indicate that the network is still congested. An example of a choke packet used in the early internet is the source sequence message, Postal, 1981. It never caught on, though, partly because the circumstances in which it was generated and the effect it had were not clearly specified. The modern internet uses an alternative notification design that we will describe next. Explicit congestion notification. Instead of generating additional packets to warn of congestion, a router can tag any packet it forwards by setting a bit in the packet's header to signal that it is experiencing congestion. When the network delivers a packet, the destination can note that there is congestion and inform the sender when it sends a reply packet. The sender can then throttle its transmissions as before. This design is called DCN, Explicit Congestion Notification, and is used in the Internet, Ramakrishnan and others, 2001. It is a refinement of early congestion signaling protocols, notably the binary feedback scheme of Ramakrishnan and Jain, 1988, that was used in the DECnet architecture. 2 bits in the IP packet header are used to record whether the packet has experienced congestion. Packets are unmarked when they are sent, as illustrated in figure 5-25. If any of the routers they pass through is congested, that router will then mark the packet as having experienced congestion as it is forwarded. The destination will then echo any marks back to the sender as an explicit congestion signal in its next reply packet. This is shown with a dashed line in the figure to indicate that it happens above the IP level, for instance, in TCP. The sender must then throttle its transmissions, as in the case of choke packets. Congestion signal host marked packet congested router figure 5-25. Explicit congestion notification hop by hop back pressure at high speeds or over long distances. Many new packets may be transmitted after congestion has been signaled because of the delay before the signal takes effect. Consider, for example, a host in San Francisco, router A in figure 5-26, that is sending traffic to a host in New York, router D in figure 5-26, at the OC3 speed of 155 megabits per second. If the New York host begins to run out of buffers, it will take about 14 sec for a choke packet to get back to San Francisco to tell it to slow down. An ECN indication will take even longer because it is delivered via the destination. Choke packet propagation is illustrated as the second, third, and fourth steps in figure 5-26. In those 14 sec, another 6.2 megabits will have been sent. Even if the host in San Francisco completely shuts down immediately, the 6.2 megabits in the pipe will continue to pour in and have to be dealt with. Only in the 7th diagram in figure 5-26 will the New York router notice a slower flow. An alternative approach is to have the choke packet take effect at every hop it passes through, as shown in the sequence of figure 5-26b. Here, as soon as the choke packet reaches F is required to reduce the flow to D. Doing so will require F to devote more buffers to the connection, since the source is still sending away at full blast, but it gives D immediate relief, like a headache remedy in a television commercial. In the next step, the choke packet reaches E, which tells E to reduce the flow to F. This action puts a greater demand on E's buffers, but gives F immediate relief. Finally, the choke packet reaches A and the flow genuinely slows down. The net effect of this hop-by-hop scheme is to provide quick relief at the point of congestion, at the price of using up more buffers upstream. In this way, congestion can be nipped in the bud without losing any packets. The idea is discussed in detail by Misra and others, 1996. 5.3.5 Load shedding. When none of the above methods make the congestion disappear, routers can bring out the heavy artillery, load shedding. Load shedding is a fancy way of saying that when routers are being inundated by packets that they cannot handle, they just throw them away. The term comes from the world of electrical power generation, where it refers to the practice of utilities intentionally blacking out certain areas to save the entire grid from collapsing on hot summer days when the demand for electricity greatly exceeds the supply. The key question for a router drowning in packets is which packets to drop. The preferred choice may depend on the type of applications that use the network. For a file transfer, an old packet is worth more than a new one. This is because dropping packet 6 and keeping packets 7 through 10, for example, will only force the receiver to do more work to buffer data that it cannot yet use. In contrast, for real-time media, a new packet is worth more than an old one. This is because packets become useless if they are delayed and miss the time at which they must be played out to the user. The former policy, old is better than new, is often called wine, and the latter, new is better than old, is often called milk, because most people would rather drink new milk and old wine than the alternative. More intelligent load shedding requires cooperation from the senders. An example is packets that carry routing information. These packets are more important than regular data packets because they establish routes. If they are lost, the network may lose connectivity. Another example is that algorithms for compressing video, like MPEG, periodically transmit an entire frame and then send subsequent figure 5 to 26. A choke packet that affects only the source. B. A choke packet that affects each hop it passes through frames as differences from the last full frame. In this case, dropping a packet that is part of a difference is preferable to dropping one that is part of a full frame because future packets depend on the full frame. To implement an intelligent discard policy, applications must mark their packets to indicate to the network how important they are. Then, when packets have to be discarded, routers can first drop packets from the least important class, then the next most important class, and so on. Of course, unless there is some significant incentive to avoid marking every packet as very important, never, ever discard, nobody will do it. Often accounting and money are used to discourage frivolous marking. For example, the network might let senders send faster than the service they purchased, allows if they mark excess packets as low priority. Such a strategy is actually not a bad idea because it makes more efficient use of vital resources, allowing hosts to use them as long as nobody else is interested, but without establishing a right to them when times get tough. Random early detection dealing with congestion when it first starts is more effective than letting it gum up the works and then trying to deal with it. This observation leads to an interesting twist on load shedding, which is to discard packets before all the buffer space is really exhausted. The motivation for this idea is that most internet hosts do not yet get congestion signals from routers in the form of ECN. Instead, the only reliable indication of congestion that hosts get from the network is packet loss. After all, it is difficult to build a router that does not drop packets when it is overloaded. Transport protocols such as TCP are thus hardwired to react to loss as congestion, slowing down the source in response. The reasoning behind this logic is that TCP was designed for wired networks, and wired networks are very reliable, so lost packets are mostly due to buffer overruns rather than transmission errors. Wireless links must recover transmission errors at the link layer, so they are not seen at the network layer, to work well with TCP. This situation can be exploited to help reduce congestion. By having routers drop packets early, before the situation has become hopeless, there is time for the source to take action, before it is too late. A popular algorithm for doing this is called RED, Random Early Detection, Floyd and Jacobson, 1993. To determine when to start discarding, routers maintain a running average of their queue lengths. When the average queue length on some link exceeds a threshold, the link is said to be congested, and a small fraction of the packets are dropped at random. Picking packets at random makes it more likely that the fastest senders will see a packet drop. This is the best option, since the router cannot tell which source is causing the most trouble in a datagram network. The affected sender will notice the loss when there is no acknowledgement, and then the transport protocol will slow down. The lost packet is thus delivering the same message as a choke packet, but implicitly, without the router sending any explicit signal. RED routers improve performance compared to routers that drop packets only when their buffers are full, though they may require tuning to work well. For example, the ideal number of packets to drop depends on how many senders need to be notified of congestion. However, ECN is the preferred option if it is available. It works in exactly the same manner, but delivers a congestion signal explicitly, rather than as a loss. RED is used when hosts cannot receive explicit signals. 5.4 Quality of service. The techniques we looked at in the previous sections are designed to reduce congestion and improve network performance. However, there are applications and customers that demand stronger performance guarantees from the network than the best that could be done under the circumstances. Multimedia applications in particular often need a minimum throughput and maximum latency to work. In this section, we will continue our study of network performance, but now with a sharper focus on ways to provide quality of service that is matched to application needs. This is an area in which the internet is undergoing a long-term upgrade. An easy solution to provide good quality of service is to build a network with enough capacity for whatever traffic will be thrown at it. The name for this solution is over-provisioning. The resulting network will carry application traffic without significant loss and, assuming a decent routing scheme, will deliver packets with low latency. Performance doesn't get any better than this. To some extent, the telephone system is over-provisioned because it is rare to pick up a telephone and not get a dial tone instantly. There is simply so much capacity available that demand can almost always be met. The trouble with this solution is that it is expensive. It is basically solving a problem by throwing money at it. Quality of service mechanisms let a network with less capacity meet application requirements just as well at a lower cost. Moreover, over-provisioning is based on expected traffic. All bets are off if the traffic pattern changes too much. With quality of service mechanisms, the network can honor the performance guarantees that it makes even when traffic spikes at the cost of turning down some requests. 4 issues must be addressed to ensure quality of service. 1. What applications need from the network? 2. How to regulate the traffic that enters the network. 3. How to reserve resources at routers to guarantee performance. 4. Whether the network can safely accept more traffic. No single technique deals efficiently with all these issues. Instead, a variety of techniques have been developed for use at the network and transport layer. Practical quality of service solutions combine multiple techniques. To this end, we will describe 2 versions of quality of service for the internet called integrated services and differentiated services. 5.4.1 Application requirements. A stream of packets from a source to a destination is called a flow. Clark, 1988. A flow might be all the packets of a connection in a connection-oriented network, or all the packets sent from one process to another process in a connectionless network. The needs of each flow can be characterized by 4 primary parameters: bandwidth, delay, jitter, and loss. Together, these determine the QoS, quality of service, the flow requires. Several common applications and the stringency of their network requirements are listed in Figure 5-27. Note that network requirements are less demanding than application requirements in those cases that the application can improve on the service provided by the network. In particular, networks do not need to be lossless for reliable file transfer, and they do not need to deliver packets with identical delays for audio and video playout. Some amount of loss can be repaired with retransmissions, and some amount of jitter can be smoothed by buffering packets at the receiver. However, there is nothing applications can do to remedy the situation if the network provides too little bandwidth or too much delay. Application bandwidth, delay, jitter, loss, ML, low medium, file sharing, high low medium, web access, medium low medium, remote login, low medium audio on demand, low high low video on demand, high low telephony, low high video conferencing, high low. Figure 5-27. Stringency of applications, quality of service requirements. The applications differ in their bandwidth needs, with ML, audio in all forms, and remote login not needing much, but file sharing, and video in all forms needing a great deal. More interesting are the delay requirements. File transfer applications, including ML and video, are not delay sensitive. If all packets are delayed uniformly by a few seconds, no harm is done. Interactive applications, such as web surfing and remote login, are more delay sensitive. Real-time applications, such as telephony and video conferencing, have strict delay requirements. If all the words in a telephone call are each delayed by too long, the users will find the connection unacceptable. On the other hand, playing audio or video files from a server does not require low delay. The variation, that is, standard deviation, in the delay or packet arrival times is called jitter. The first 3 applications in Figure 5-27 are not sensitive to the packets arriving with irregular time intervals between them. Remote login is somewhat sensitive to that, since updates on the screen will appear in little bursts if the connection suffers much jitter. Video and especially audio are extremely sensitive to jitter. If a user is watching a video over the network and the frames are all delayed by exactly 2.000 seconds, no harm is done. But if the transmission time varies randomly between 1 and 2 seconds, the result will be terrible unless the application hides the jitter. For audio, a jitter of even a few milliseconds is clearly audible. The first 4 applications have more stringent requirements on loss than audio and video, because all bits must be delivered correctly. This goal is usually achieved with retransmissions of packets that are lost in the network by the transport layer. This is wasted work. It would be better if the network refused packets it was likely to lose in the first place. Audio and video applications can tolerate some lost packets without retransmission because people do not notice short pauses or occasional skipped frames. To accommodate a variety of applications, networks may support different categories of COS. An influential example comes from ATM networks, which were once part of a grand vision for networking, but have since become a niche technology. They support 1. Constant bitrate, for instance, telephony. 2. Real-time variable bitrate, for instance, compressed video conferencing. 3. Non-real-time variable bitrate, for instance, watching a movie on demand. 4. Available bitrate, for instance, file transfer. These categories are also useful for other purposes and other networks. Constant bitrate is an attempt to simulate a wire by providing a uniform bandwidth and a uniform delay. Variable bitrate occurs when video is compressed, with some frames compressing more than others. Sending a frame with a lot of detail in it may require sending many bits, whereas a shot of a white wall may compress extremely well. Movies on demand are not actually real time, because a few seconds of video can easily be buffered at the receiver before playback starts, so jitter on the network merely causes the amount of stored but not played video to vary. Available bitrate is for applications such as email that are not sensitive to delay or jitter and will take what bandwidth they can get. 5.4.2 Traffic shaping. Before the network can make COS guarantees, it must know what traffic is being guaranteed. In the telephone network, this characterization is simple. For example, a voice call, in uncompressed format, needs 64 kbps and consists of one 8-bit sample every 125 a sec. However, traffic in data networks is bursty. It typically arrives at non-uniform rates as the traffic rate varies. For instance, video conferencing with compression, users interact with applications, for instance, browsing a new web page, and computers switch between tasks. Bursts of traffic are more difficult to handle than constant rate traffic because they can fill buffers and cause packets to be lost. Traffic shaping is a technique for regulating the average rate and burstiness of a flow of data that enters the network. The goal is to allow applications to transmit a wide variety of traffic that suits their needs, including some bursts, yet have a simple and useful way to describe the possible traffic patterns to the network. When a flow is set up, the user and the network, that is, the customer and the provider, agree on a certain traffic pattern, that is, shape, for that flow. In effect, the customer says to the provider, my transmission pattern will look like this, can you handle it? Sometimes this agreement is called an SLA, service level agreement, especially when it is made over aggregate flows and long periods of time, such as all of the traffic for a given customer. As long as the customer fulfills her part of the bargain and only sends packets according to the agreed on contract, the provider promises to deliver them all in a timely fashion. Traffic shaping reduces congestion and thus helps the network live up to its promise. However, to make it work, there is also the issue of how the provider can tell if the customer is following the agreement and what to do if the customer is not. Packets in excess of the agreed pattern might be dropped by the network, or they might be marked as having lower priority. Monitoring a traffic flow is called traffic policing. Shaping and policing are not so important for peer-to-peer and other transfers that will consume any and all available bandwidth, but they are of great importance for real-time data, such as audio and video connections, which have stringent quality of service requirements. Leaky in token buckets. We have already seen one way to limit the amount of data an application sends, the sliding window, which uses one parameter to limit how much data is in transit at any given time, which indirectly limits the rate. Now we will look at a more general way to characterize traffic with the leaky bucket and token bucket algorithms. The formulations are slightly different, but give an equivalent result. Try to imagine a bucket with a small hole in the bottom, as illustrated in figure 5-28b. No matter the rate at which water enters the bucket, the outflow is at a constant rate, r, when there is any water in the bucket, and 0, when the bucket is empty. Also, once the bucket is full to capacity b, any additional water entering it spills over the sides and is lost. Check bucket here. Host packets rate RBB rate R take out water / tokens put in water network. B. C. Figure 5-28. Shaping packets. B. A leaky bucket. C. A token bucket. This bucket can be used to shape or police packets entering the network, as shown in figure 5-28. Conceptually, each host is connected to the network by an interface containing a leaky bucket. To send a packet into the network, it must be possible to put more water into the bucket. If the packet arrives when the bucket is full, the packet must either be queued until enough water leaks out to hold it or be discarded. The former might happen at a host shaping its traffic for the network as part of the operating system. The latter might happen in hardware at a provider network interface that is policing traffic entering the network. This technique was proposed by Turner, 1986, and is called the leaky bucket algorithm. A different but equivalent formulation is to imagine the network interface as a bucket that is being filled, as shown in figure 5-28c. The tap is running at rate R and the bucket has a capacity of B, as before. Now, to send a packet we must be able to take water, or tokens, as the contents are commonly called, out of the bucket, rather than putting water into the bucket. No more than a fixed number of tokens, B, can accumulate in the bucket, and if the bucket is empty, we must wait until more tokens arrive before we can send another packet. This algorithm is called the token bucket algorithm. Leaky and token buckets limit the long-term rate of a flow, but allow short-term bursts up to a maximum regulated length to pass through unaltered and without suffering any artificial delays. Large bursts will be smoothed by a leaky bucket traffic shaper to reduce congestion in the network. As an example, imagine that a computer can produce data at up to 1000 megabits per second, 125 million bytes / secretary, and that the first link of the network also runs at this speed. The pattern of traffic the host generates is shown in figure 5-29. This pattern is bursty. The average rate over 1 second is 200 megabits per second, even though the host sends a burst of 16,000 kb at the top speed of 1000 megabits per second, for 1/8 of the second, 25 MB/s for 250 msec 125 MB/s for 125 msec time, msec, 16,000, 1000 rate, Mbps, D, B, E, C, F. 1000. Bucket, KB, with R equals 25 MB/s, B equals 0 with R equals 25 MB/s, B equals 9600 KB. Bucket always empty. Bucket empties. Traffic delayed time, msec, 1000, 9600, 0 figure 5-29. Traffic from a host. Output shaped by a token bucket of rate 200 megabits per second and capacity, B, 9600 KB, and C, 0 KB. Token bucket level for shaping with rate 200 megabits per second and capacity, D, 16000 KB, E, 9600 KB, and F, 0 KB. Now suppose that the routers can accept data at the top speed only for short intervals, until their buffers fill up. The buffer size is 9600 KB, smaller than the traffic burst. For long intervals, the routers work best at rates not exceeding 200 megabits per second, say, because this is all the bandwidth given to the customer. The implication is that, if traffic is sent in this pattern, some of it will be dropped in the network, because it does not fit into the buffers at routers. To avoid this packet loss, we can shape the traffic at the host with a token bucket. If we use a rate R of 200 megabits per second and a capacity B of 9600 KB, the traffic will fall within what the network can handle. The output of this token bucket is shown in figure 5-29b. The host can send full throttle at 1000 megabits per second for a short while until it has drained the bucket. Then it has to cut back to 200 megabits per second until the burst has been sent. The effect is to spread out the burst over time because it was too large to handle all at once. The level of the token bucket is shown in figure 5-29e. It starts off full and is depleted by the initial burst. When it reaches zero, new packets can be sent only at the rate at which the buffer is filling. There can be no more bursts until the bucket has recovered. The bucket fills when no traffic is being sent and stays flat when traffic is being sent at the fill rate. We can also shape the traffic to be less bursty. Figure 5-29c shows the output of a token bucket with R equals 200 megabits per second and a capacity of 0. This is the extreme case in which the traffic has been completely smoothed. No bursts are allowed, and the traffic enters the network at a steady rate. The corresponding bucket level, shown in figure 5-29f, is always empty. Traffic is being queued on the host for release into the network and there is always a packet waiting to be sent when it is allowed. Finally, figure 5-29d shows the bucket level for a token bucket with R equals 200 megabits per second and a capacity of B equals 16,000 KB. This is the smallest token bucket through which the traffic passes unaltered. It might be used at a router in the network to police the traffic that the host sends. If the host is sending traffic that conforms to the token bucket on which it has agreed with the network, the traffic will fit through that same token bucket run at the router at the edge of the network. If the host sends at a faster or burstier rate, the token bucket will run out of water. If this happens, a traffic policer will know that the traffic is not as described. It will then either drop the excess packets or lower their priority, depending on the design of the network. In our example, the bucket empties only momentarily at the end of the initial burst, then recovers enough for the next burst. Leaky and token buckets are easy to implement. We will now describe the operation of a token bucket. Even though we have described water flowing continuously into and out of the bucket, real implementations must work with discrete quantities. A token bucket is implemented with a counter for the level of the bucket. The counter is advanced by R/units at every clock tick of seconds. This would be 200 bit every 1 second. Our example above. Every time a unit of traffic is sent into the network, the counter is decremented, and traffic may be sent until the counter reaches 0. When the packets are all the same size, the bucket level can just be counted in packets. For instance, 200 bit is 20 packets of 1250 bytes. However, often variable-sized packets are being used. In this case, the bucket level is counted in bytes. If the residual byte count is too low to send a large packet, the packet must wait until the next tick, or even longer, if the fill rate is small. Calculating the length of the maximum burst until the bucket empties is slightly tricky. It is longer than just 9600 KB divided by 125 MB/secretary, because while the burst is being output, more tokens arrive. If we call the burst length s seconds, the maximum output rate m bytes/secretary, the token bucket capacity b bytes, and the token arrival rate r bytes/secretary, we can see that an output burst contains a maximum of b plus rs bytes. We also know that the number of bytes in a maximum speed burst of length s seconds is manuscript, hence, we have b plus rs equals manuscript. We can solve this equation to get s equals b/m r. For our parameters of b equals 9600 KB, m equals 125 MB/secretary, and r equals 25 MB/secretary, we get a burst time of about 94 ms. A potential problem with the token bucket algorithm is that it reduces large bursts down to the long-term rate r. It is frequently desirable to reduce the peak rate but without going down to the long-term rate, and also without raising the long-term rate to allow more traffic into the network. One way to get smoother traffic is to insert a second token bucket after the first one. The rate of the second bucket should be much higher than the first one. Basically, the first bucket characterizes the traffic, fixing its average rate, but allowing some bursts. The second bucket reduces the peak rate at which the bursts are sent into the network. For example, if the rate of the second token bucket is set to be 500 megabits per second and the capacity is set to 0, the initial burst will enter the network at a peak rate of 500 megabits per second, which is lower than the 1000 megabits per second rate we had previously. Using all of these buckets can be a bit tricky. When token buckets are used for traffic shaping at hosts, packets are queued and delayed until the buckets permit them to be sent. When token buckets are used for traffic policing at routers in the network, the algorithm is simulated to make sure that no more packets are sent than permitted. Nevertheless, these tools provide ways to shape the network traffic into more manageable forms to assist in meeting quality of service requirements 5.4.3 packet scheduling. Being able to regulate the shape of the offered traffic is a good start. However, to provide a performance guarantee, we must reserve sufficient resources along the route that the packets take through the network. To do this, we are assuming that the packets of a flow follow the same route. Spraying them over routers at random makes it hard to guarantee anything. As a consequence, something similar to a virtual circuit has to be set up from the source to the destination, and all the packets that belong to the flow must follow this route. Algorithms that allocate router resources among the packets of a flow and between competing flows are called packet scheduling algorithms. 3 different kinds of resources can potentially be reserved for different flows. 1. Bandwidth. 2. Buffer space. 3. CPU cycles. The first one, bandwidth, is the most obvious. If a flow requires 1 megabits per second and the outgoing line has a capacity of 2 megabits per second, trying to direct 3 flows through that line is not going to work. Thus, reserving bandwidth means not oversubscribing any output line. A second resource that is often in short supply is buffer space. When a packet arrives, it is buffered inside the router until it can be transmitted on the chosen outgoing line. The purpose of the buffer is to absorb small bursts of traffic as the flows contend with each other. If no buffer is available, the packet has to be discarded, since there is no place to put it. For good quality of service, some buffers might be reserved for a specific flow, so that flow does not have to compete for buffers with other flows. Up to some maximum value, there will always be a buffer available when the flow needs one. Finally, CPU cycles may also be a scarce resource. It takes router CPU time to process a packet, so a router can process only a certain number of packets per second. While modern routers are able to process most packets quickly, some kinds of packets require greater CPU processing, such as the ICMP packets we will describe in Secretary 5.6. Making sure that the CPU is not overloaded is needed to ensure timely processing of these packets. Packet scheduling algorithms allocate bandwidth and other router resources by determining which of the buffered packets to send on the output line next. We already described the most straightforward scheduler when explaining how routers work. Each router buffers packets in a queue for each output line until they can be sent, and they are sent in the same order that they arrived. This algorithm is known as FIFO, first in first out, or equivalently FCFS, first come first serve. FIFO routers usually drop newly arriving packets when the queue is full. Since the newly arrived packet would have been placed at the end of the queue, this behavior is called tail drop. It is intuitive, and you may be wondering what alternatives exist. In fact, the red algorithm we described in Secretary 5.3.5 chose a newly arriving packet to drop at random when the average queue length grew large. The other scheduling algorithms that we will describe also create other opportunities for deciding which packet to drop when the buffers are full. FIFO scheduling is simple to implement, but it is not suited to providing good quality of service, because when there are multiple flows, one flow can easily affect the performance of the other flows. If the first flow is aggressive and sends large bursts of packets, they will lodge in the queue. Processing packets in the order of their arrival means that the aggressive sender can hog most of the capacity of the route as its packets traverse, starving the other flows and reducing their quality of service. To add insult to injury, the packets of the other flows that do get through are likely to be delayed because they had to sit in the queue behind many packets from the aggressive sender. Many packet scheduling algorithms have been devised that provide stronger isolation between flows and thwart attempts at interference. Batty and Crowcroft, 2000. One of the first ones was the fair queuing algorithm devised by Nagel, 1987. The essence of this algorithm is that routers have separate queues, one for each flow for a given output line. When the line becomes idle, the router scans the queues round robin, as shown in figure 5230. It then takes the first packet on the next queue. In this way, with n hosts competing for the output line, each host gets to send one out of every n packets. It is fair in the sense that all flows get to send packets at the same rate. Sending more packets will not improve this rate. Although a start, the algorithm has a flaw. It gives more bandwidth to hosts that use large packets than to hosts that use small packets. Demers and others, 1990, suggested an improvement in which the round robin is done in such a way as to simulate a byte by byte round robin, instead of a packet by packet round robin. The trick is to compute a virtual time, that is the number of the round at which each packet would finish being sent. Each round drains a byte from all of the queues that have data to send. The packets are then sorted in order of their finishing times and sent in that order. Figure 5230. Round robin fair queuing. This algorithm and an example of finish times for packets arriving in 3 flows are illustrated in figure 5231. If a packet has length L, the round at which it will finish is simply L rounds after the start time. The start time is either the finish time of the previous packet or the arrival time of the packet if the queue is empty when it arrives. Figure 5231. Weighted fair queuing. B. Finishing times for the packets. From the table in figure 5232, B, and looking only at the first 2 packets in the top 2 queues, packets arrive in the order A, B, D, and F. Packet A arrives at round 0 and is 8 bytes long, so its finish time is round 8. Similarly, the finish time for packet B is 11. Packet D arrives while B is being sent. Its finish time is 9 byte rounds after it starts when B finishes, or 20. Similarly, the finish time for F is 16. In the absence of new arrivals, the relative sending order is A, B, F, D. Even though F arrived after D, it is possible that another small packet will arrive on the top flow and obtain a finish time before D. It will only jump ahead of D if the transmission of that packet has not started. Fair queuing does not preempt packets that are currently being transmitted. Because packets are sent in their entirety, fair queuing is only an approximation of the ideal byte by byte scheme. But it is a very good approximation, staying within one packet transmission of the ideal scheme at all times. One shortcoming of this algorithm in practice is that it gives all hosts the same priority. In many situations, it is desirable to give, for example, video servers more bandwidth than, say, file servers. This is easily possible by giving the video server 2 or more bytes per round. This modified algorithm is called WFQ, weighted fair queuing. Letting the number of bytes per round be the weight of a flow, W, we can now give the formula for computing the finish time. Phi equals maximum AI phi 1 plus Li/W, where AI is the arrival time, phi is the finish time, and Li is the length of packet I. The bottom queue of figure 5231 has a weight of 2. So its packets are sent more quickly, as you can see in the finish times given in figure 5231 B. Another practical consideration is implementation complexity. WFQ requires that packets be inserted by their finish time into a sorted queue. With n flows, this is at best an O log n operation per packet, which is difficult to achieve for many flows in high-speed routers. Schroeder and Varghese, 1995, describe an approximation called deficit round robin that can be implemented very efficiently with only O1 operations per packet. WFQ is widely used given this approximation. Other kinds of scheduling algorithms exist too. A simple example is priority scheduling, in which each packet is marked with a priority. High priority packets are always sent before any low priority packets that are buffered. Within a priority, packets are sent in FIFO order. However, priority scheduling has the disadvantage that a burst of high priority packets can starve low priority packets, which may have to wait indefinitely. WFQ often provides a better alternative. By giving the high priority queue a large weight, say 3, high priority packets will often go through a short line, as relatively few packets should be high priority, yet some fraction of low priority packets will continue to be sent even when there is high priority traffic. A high and low priority system is essentially a TQWFQ system in which the high priority has infinite weight. As a final example of a scheduler, packets might carry timestamps and be sent in timestamp order. Clark and others, 1992, describe a design in which the timestamp records how far the packet is behind or ahead of schedule as it is sent through a sequence of routers on the path. Packets that have been queued behind other packets at a router will tend to be behind schedule, and the packets that have been serviced first will tend to be ahead of schedule. Sending packets in order of their timestamps has the beneficial effect of speeding up slow packets, while at the same time slowing down fast packets. The result is that all packets are delivered by the network with a more consistent delay. 5.4. For admission control, we have now seen all the necessary element for CoS, and it is time to put them together to actually provide it. CoS guarantees are established through the process of admission control. We first saw admission control used to control congestion, which is a performance guarantee, albeit a weak one. The guarantees we are considering now are stronger, but the model is the same. The user offers a flow with an accompanying CoS requirement to the network. The network then decides whether to accept or reject the flow, based on its capacity and the commitments it has made to other flows. If it accepts, the network reserves capacity in advance at routers to guarantee CoS when traffic is sent on the new flow. The reservations must be made at all of the routers along the route that the packets take through the network. Any routers on the path without reservations might become congested, and a single congested router can break the CoS guarantee. Many routing algorithms find the single best path between each source and each destination and send all traffic over the best path. This may cause some flows to be rejected if there is not enough spare capacity along the best path. CoS guarantees for new flows may still be accommodated by choosing a different route for the flow that has excess capacity. This is called CoS routing. Chen and Nastat, 1998, give an overview of these techniques. It is also possible to split the traffic for each destination over multiple paths to more easily find excess capacity. A simple method is for routers to choose equal cost paths and to divide the traffic equally or in proportion to the capacity of the outgoing links. However, more sophisticated algorithms are also available. Nalakudati and Zhang, 2002. Given a path, the decision to accept or reject a flow is not a simple matter of comparing the resources, bandwidth, buffers, cycles, requested by the flow with the router's excess capacity in those three dimensions. It is a little more complicated than that. To start with, although some applications may know about their bandwidth requirements, few know about buffers or CPU cycles, so at the minimum, a different way is needed to describe flows and translate this description to router resources. We will get to this shortly. Next, some applications are far more tolerant of an occasional missed deadline than others. The applications must choose from the type of guarantees that the network can make, whether hard guarantees or behavior that will hold most of the time. All else being equal, everyone would like hard guarantees, but the difficulty is that they are expensive because they constrain worst case behavior. Guarantees for most of the packets are often sufficient for applications, and more flows with this guarantee can be supported for a fixed capacity. Finally, some applications may be willing to haggle about the flow parameters and others may not. For example, a movie viewer that normally runs at 30 frames/secretary may be willing to drop back to 25 frames/secretary if there is not enough free bandwidth to support 30 frames/secretary. Similarly, the number of pixels per frame, audio bandwidth, and other properties may be adjustable. Because many parties may be involved in the flow negotiation, the sender, the receiver, and all the routers along the path between them, flows must be described accurately in terms of specific parameters that can be negotiated. A set of such parameters is called a flow specification. Typically, the sender, for instance, the video server, produces a flow specification proposing the parameters it would like to use. As the specification propagates along the route, each router examines it and modifies the parameters as need be. The modifications can only reduce the flow, not increase it, for instance, a lower data rate, not a higher one. When it gets to the other end, the parameters can be established. As an example of what can be in a flow specification, consider the example of figure 5.2.32. This is based on RFCs 20-10 and 20-11 for integrated services, a CoS design we will cover in the next section. It has 5 parameters. The first 2 parameters, the token bucket rate and token bucket size, use a token bucket to give the maximum sustained rate the sender may transmit, averaged over a long time interval, and the largest burst it can send over a short time interval. Parameter unit token bucket rate bytes/secretary token bucket size bytes peak data rate bytes/secretary minimum packet size bytes maximum packet size bytes figure 5.2.32. An example flow specification. The third parameter, the peak data rate, is the maximum transmission rate tolerated, even for brief time intervals. The sender must never exceed this rate even for short bursts. The last 2 parameters specify the minimum and maximum packet sizes, including the transport and network layer headers, for instance, TCP and IP. The minimum size is useful because processing each packet takes some fixed time, no matter how short. A router may be prepared to handle 10,000 packets/secretary of 1 KB each, but not be prepared to handle 100,000 packets/secretary of 50 bytes each, even though this represents a lower data rate. The maximum packet size is important due to internal network limitations that may not be exceeded. For example, if part of the path goes over an Ethernet, the maximum packet size will be restricted to no more than 1500 bytes, no matter what the rest of the network can handle. An interesting question is how a router turns a flow specification into a set of specific resource reservations. At first glance, it might appear that, if a router has a link that runs at, say, 1 Gbps and the average packet is 1000 bits, it can process 1 million packets/secretary. This observation is not the case, though, because there will always be idle periods on the link due to statistical fluctuations in the load. If the link needs every bit of capacity to get its work done, idling for even a few bits creates a backlog it can never get rid of. Even with the load slightly below the theoretical capacity, queues can build up, and delays can occur. Consider a situation in which packets arrive at random with a mean arrival rate of packets/secretary. The packets have random lengths, and can be sent on the link with a mean service rate of packets/secretary. Under the assumption that both the arrival and service distributions are Poisson distributions, what is called an M/M/1 queuing system, where M stands for Markov, that is, Poisson, it can be proven using queuing theory that the mean delay experienced by a packet, T, is T equals 1x1/1 equals 1x1, n1 where n equals/ is the CPU utilization. The first factor, 1/ is what the service time would be in the absence of competition. The second factor is the slowdown due to competition with other flows. For example, if equals 950,000 packets/secretary and equals 1 million packets/secretary, then n equals 0.95 and the mean delay experienced by each packet will be 20 ASIC instead of 1 ASIC. This time accounts for both the queuing time and the service time, as can be seen when the load is very low, /0. If there are, say, 30 routers along the flow's route, queuing delay alone will account for 600 ASIC of delay. One method of relating flow specifications to router resources that correspond to bandwidth and delay performance guarantees is given by Perec and Gallagher, 1993, 1994. It is based on traffic sources shaped by R, B, token buckets and WFQ at routers. Each flow is given a WFQ weight W large enough to drain its token bucket rate R as shown in figure 5.233. For example, if the flow has a rate of 1 megabits per second and the router and output link have a capacity of 1 Gbps, the weight for the flow must be greater than 1/1000th of the total of the weights for all of the flows at that router for the output link. This guarantees the flow a minimum bandwidth. If it cannot be given a large enough rate, the flow cannot be admitted. Figure 5.233. Bandwidth and delay guarantees with token buckets and WFQ. The largest queuing delay the flow will see is a function of the burst size of the token bucket. Consider the two extreme cases. If the traffic is smooth, without any bursts, packets will be drained from the router just as quickly as they arrive. There will be no queuing delay, ignoring packetization effects. On the other hand, if the traffic is saved up in bursts, then a maximum size burst, B, may arrive at the router all at once. In this case the maximum queuing delay, D, will be the time taken to drain this burst at the guaranteed bandwidth, or B/R, again, ignoring packetization effects. If this delay is too large, the flow must request more bandwidth from the network. These guarantees are hard. The token buckets bound the burstiness of the source, and fair queuing isolates the bandwidth given to different flows. This means that the flow will meet its bandwidth and delay guarantees regardless of how the other competing flows behave at the router. Those other flows cannot break the guarantee even by saving up traffic and all sending at once. Moreover, the result holds for a path through multiple routers in any network topology. Each flow gets a minimum bandwidth because that bandwidth is guaranteed at each router. The reason each flow gets a maximum delay is more subtle. In the worst case, that a burst of traffic hits the first router and competes with the traffic of other flows, it will be delayed up to the maximum delay at E. However, this delay will also smooth the burst. In turn, this means that the burst will incur no further queuing delays at later routers. The overall queuing delay will be at most D5.4.5 integrated services between 1995 and 1997. IETF put a lot of effort into devising an architecture for streaming multimedia. This work resulted in over 24 RFCs, starting with RFCs 20-05 to 20-12. The generic name for this work is Integrated Services. It was aimed at both unicast and multicast applications. An example of the former is a single user streaming a video clip from a news site. An example of the latter is a collection of digital television stations broadcasting their programs as streams of IP packets to many receivers at various locations. Below we will concentrate on multicast, since unicast is a special case of multicast. In many multicast applications, groups can change membership dynamically, for example, as people enter a video conference and then get bored and switch to a soap opera or the croquet channel. Under these conditions, the approach of having the senders reserve bandwidth in advance does not work well, since it would require each sender to track all entries and exits of its audience. For a system designed to transmit television with millions of subscribers, it would not work at all. RSVP, the Resource Reservation Protocol, the main part of the integrated services architecture that is visible to the users of the network is RSVP. It is described in RFCs 20-05 to 20-10. This protocol is used for making the reservations. Other protocols are used for sending the data. RSVP allows multiple senders to transmit to multiple groups of receivers. permits individual receivers to switch channels freely and optimizes bandwidth use, while at the same time eliminating congestion. In its simplest form, the protocol uses multicast routing using spanning trees, as discussed earlier. Each group is assigned a group address. To send to a group, a sender puts the group's address in its packets. The standard multicast routing algorithm then builds a spanning tree covering all group members. The routing algorithm is not part of RSVP. The only difference from normal multicasting is a little extra information that is multicast to the group periodically to tell the routers along the tree to maintain certain data structures in their memories. As an example, consider the network of figure 5 to 34. Hosts 1 and 2 are multicast senders, and hosts 3, 4, and 5 are multicast receivers. In this example, the senders and receivers are disjoint, but in general, the two sets may overlap. The multicast trees for hosts 1 and 2 are shown in figure 5 to 34b and figure 5 to 34c, respectively. Figure 5 to 34, a network, B, the multicast spanning tree for host 1, C, the multicast spanning tree for host 2. To get better reception and eliminate congestion, any of the receivers in a group can send a reservation message up the tree to the sender. The message is propagated using the reverse path forwarding algorithm discussed earlier. At each hop, the router notes the reservation and reserves the necessary bandwidth. We saw in the previous section how a weighted fair queuing scheduler can be used to make this reservation. If insufficient bandwidth is available, it reports back failure. By the time the message gets back to the source, bandwidth has been reserved all the way from the sender to the receiver, making the reservation request along the spanning tree. An example of such a reservation is shown in figure 5 to 35. Here host 3 has requested a channel to host 1. Once it has been established, packets can flow from 1 to 3 without congestion. Now consider what happens if host 3 next reserves a channel to the other sender, host 2, so the user can watch 2 television programs at once. A second path is reserved, as illustrated in figure 5 to 35b. Note that 2 separate channels are needed from host 3 to router E, because 2 independent streams are being transmitted. Figure 5 to 35. Host 3 requests a channel to host 1, B. Host 3 then requests a second channel to host 2, C. Host 5 requests a channel to host 1. Finally, in figure 5 to 35, C. Host 5 decides to watch the program being transmitted by host 1 and also makes the reservation. First, dedicated bandwidth is reserved as far as router H. However, this router sees that it already has a feed from host 1, so if the necessary bandwidth has already been reserved, it does not have to reserve any more. Note that hosts 3 and 5 might have asked for different amounts of bandwidth. For instance, if host 3 is playing on a small screen and only wants the low resolution information, so the capacity reserved must be large enough to satisfy the greediest receiver. When making a reservation, a receiver can, optionally, specify one or more sources that it wants to receive from. It can also specify whether these choices are fixed for the duration of the reservation, or whether the receiver wants to keep open the option of changing sources later. The routers use this information to optimize bandwidth planning. In particular, 2 receivers are only set up to share a path if they both agree not to change sources later on. The reason for this strategy in the fully dynamic case is that reserved bandwidth is decoupled from the choice of source. Once a receiver has reserved bandwidth, it can switch to another source and keep that portion of the existing path that is valid for the new source. If host 2 is transmitting several video streams in real time, for example a TV broadcaster with multiple channels, host 3 may switch between them at will without changing its reservation. The routers do not care what program the receiver is watching. 5.4.6 Differentiated services. Flow-based algorithms have the potential to offer good quality of service to one or more flows because they reserve whatever resources are needed along the route. However, they also have a downside. They require an advanced setup to establish each flow, something that does not scale well when there are thousands or millions of flows. Also, they maintain internal perflow state in the routers, making them vulnerable to router crashes. Finally, the changes required to the router code are substantial and involve complex router-to-router exchanges for setting up the flows. As a consequence, while work continues to advance integrated services, few deployments of it or anything like it exist yet. For these reasons, IETF has also devised a simpler approach to quality of service, one that can be largely implemented locally in each router without advanced setup and without having the whole path involved. This approach is known as class-based, as opposed to flow-based, quality of service. IETF has standardized an architecture for it, called differentiated services, which is described in RFCs 2474, 2475, and numerous others. We will now describe it. Differentiated services can be offered by a set of routers forming an administrative domain, for instance, an ISP or a telco. The administration defines a set of service classes with corresponding forwarding rules. If a customer subscribes to differentiated services, customer packets entering the domain are marked with a class to which they belong. This information is carried in the differentiated services field of IPv4 and IPv6 packets, described in Secretary 5.6. The classes are defined as per hop behaviors because they correspond to the treatment the packet will receive at each router, not a guarantee across the network. Better service is provided to packets with some per hop behaviors, for instance, premium service, than to others, for instance, regular service. Traffic within a class may be required to conform to some specific shape, such as a leaky bucket with some specified drain rate. An operator with a nose for business might charge extra for each premium packet transported, or might allow up to N premium packets per month for a fixed additional monthly fee. Note that this scheme requires no advanced setup, no resource reservation, and no time-consuming end-to-end negotiation for each flow, as with integrated services. This makes differentiated services relatively easy to implement. Class-based service also occurs in other industries. For example, package delivery companies often offer overnight, 2-day, and 3-day service. Airlines offer first class, business class, and cattle class service. Long-distance trains often have multiple service classes. Even the Paris subway has 2 different service classes. For packets, the classes may differ in terms of delay, jitter, and probability of being discarded in the event of congestion, among other possibilities, but probably not roomy or Ethernet frames. To make the difference between flow-based quality of service and class-based quality of service clearer, consider an example: internet telephony. With a flow-based scheme, each telephone call gets its own resources and guarantees. With a class-based scheme, all the telephone calls together get the resources reserved for the class telephony. These resources cannot be taken away by packets from the web browsing class or other classes, but no telephone call gets any private resources reserved for it alone. Expedited forwarding: the choice of service classes is up to each operator, but since packets are often forwarded between networks run by different operators, IETF has defined some network-independent service classes. The simplest class is expedited forwarding, so let us start with that one. It is described in RFC 3246. The idea behind expedited forwarding is very simple. 2 classes of service are available: regular and expedited. The vast majority of the traffic is expected to be regular, but a limited fraction of the packets are expedited. The expedited packets should be able to transit the network as though no other packets were present. In this way they will get low loss, low delay and low jitter service, just what is needed for VoIP. A symbolic representation of this 2-tube system is given in figure 5.236. Note that there is still just one physical line. The 2 logical pipes shown in the figure represent a way to reserve bandwidth for different classes of service, not a second physical line. One way to implement this strategy is as follows. Packets are classified as expedited or regular and marked accordingly. This step might be done on the sending host or in the ingress first router. The advantage of doing classification on the sending host is that more information is available about which packets belong to which flows. This task may be performed by networking software or even the operating system to avoid having to change existing applications. For example, it is becoming common for VoIP packets to be marked for expedited service by hosts. If the packets pass through a corporate network or ISP that supports expedited service, they will receive preferential treatment. If the network does not support expedited service, no harm is done. Regular packets, expedited packets, figure 5.236. Expedited packets experience a traffic-free network. Of course, if the marking is done by the host, the ingress router is likely to police the traffic to make sure that customers are not sending more expedited traffic than they have paid for. Within the network, the routers may have two output queues for each outgoing line, one for expedited packets and one for regular packets. When a packet arrives, it is queued accordingly. The expedited queue is given priority over the regular one, for example, by using a priority scheduler. In this way, expedited packets see an unloaded network, even when there is, in fact, a heavy load of regular traffic. A short forwarding, a somewhat more elaborate scheme for managing the service classes, is called a short forwarding. It is described in RFC 2597. A short forwarding specifies that there shall be 4 priority classes, each class having its own resources. The top 3 classes might be called gold, silver, and bronze. In addition, it defines 3 discard classes for packets that are experiencing congestion, low, medium, and high. Taken together, these 2 factors define 12 service classes. Figure 5.237 shows one-way packets might be processed under a short forwarding. The first step is to classify the packets into one of the 4 priority classes. As before, this step might be done on the sending host, as shown in the figure, or in the ingress router, and the rate of higher priority packets may be limited by the operator as part of the service offering. The next step is to determine the discard class for each packet. This is done by passing the packets of each priority class through a traffic policer, such as a token bucket. The policer lets all of the traffic through, but it identifies packets that fit within small bursts as low discard, packets that exceed small bursts as medium discard, and packets that exceed large bursts as high discard. The combination of priority and discard classes then encoded in each packet. Finally, the packets are processed by routers in the network with a packet scheduler that distinguishes the different classes. A common choice is to use weighted fair queues. Router silver, gold, bronze packet source 4 priority classes, classifier policer 12 priority/drop classes, packets with diff serve mark figure 5.237. A possible implementation of a short forwarding weighted fair queuing for the 4 priority classes, with higher classes given higher weights. In this way, the higher classes will get most of the bandwidth, but the lower classes will not be starved of bandwidth entirely. For example, if the weights double from one class to the next higher class, the higher class will get twice the bandwidth. Within a priority class, packets with the higher discard class can be preferentially dropped by running an algorithm such as RED, random early detection, which we saw in Secretary 5.3.5. RED will start to drop packets as congestion builds, but before the router has run out of buffer space. At this stage, there is still buffer space with which to accept low discard packets while dropping high discard packets. 5.5 Internetworking. Until now, we have implicitly assumed that there is a single homogeneous network, with each machine using the same protocol in each layer. Unfortunately, this assumption is wildly optimistic. Many different networks exist, including PANs, LANs, MANs, and WANs. We have described Ethernet, Internet over Cable, the fixed and mobile telephone networks, 802.11, 802.16, and more. Numerous protocols are in widespread use across these networks in every layer. In the following sections, we will take a careful look at the issues that arise when 2 or more networks are connected to form an internetwork, or more simply an internet. It would be much simpler to join networks together if everyone used a single networking technology, and it is often the case that there is a dominant kind of network, such as Ethernet. Some pundits speculate that the multiplicity of technologies will go away as soon as everyone realizes how wonderful fill in your favorite network is. Do not count on it. History shows this to be wishful thinking. Different kinds of networks grapple with different problems. So, for example, Ethernet and satellite networks are always likely to differ. Reusing existing systems, such as running data networks on top of cable, the telephone network, and power lines, adds constraints that cause the features of the networks to diverge. Heterogeneity is here to stay. If there will always be different networks, it would be simpler if we did not need to interconnect them. This also is unlikely. Bob Metcalfe postulated that the value of a network with n nodes is the number of connections that may be made between the nodes, or N2. Gilder, 1993. This means that large networks are much more valuable than small networks because they allow many more connections, so there always will be an incentive to combine smaller networks. The internet is the prime example of this interconnection. We will write internet with a capital I to distinguish it from other internets or connected networks. The purpose of joining all these networks is to allow users on any of them to communicate with users on all the other ones. When you pay an ISP for internet service, you may be charged depending on the bandwidth of your line, but what you are really paying for is the ability to exchange packets with any other host that is also connected to the internet. After all, the internet would not be very popular if you could only send packets to other hosts in the same city. Since networks often differ in important ways, getting packets from one network to another is not always so easy. We must address problems of heterogeneity and also problems of scale as the resulting internet grows very large. We will begin by looking at how networks can differ to see what we are up against. Then we shall see the approach used so successfully by IP, Internet Protocol, the network layer protocol of the internet, including techniques for tunneling through networks, routing in Internetworks, and packet fragmentation 5.5.1. How networks differ. Networks can differ in many ways. Some of the differences, such as different modulation techniques or frame formats, are internal to the physical and data link layers. These differences will not concern us here. Instead, in Figure 5.2.38 we list some of the differences that can be exposed to the network layer. It is papering over these differences that makes internetworking more difficult than operating within a single network. When packets sent by a source on one network must transit one or more foreign networks before reaching the destination network, many problems can occur at the interfaces between networks. To start with, the source needs to be able to address the destination. What do we do if the source is on an Ethernet network and the destination is on a WE maximum network? Assuming we can even specify a WE maximum destination from an Ethernet network, packets would cross from a connectionless network to a connection-oriented one. This may require that a new connection be set up on short notice, which injects a delay and much overhead if the connection is not used for many more packets. Many specific differences may have to be accommodated as well. How do we multicast a packet to a group with some members on a network that does not? Item some possibilities. Service offered connectionless versus connection oriented, addressing different sizes, flat or hierarchical, broadcasting present or absent. Also multicast. Packet size. Every network has its own maximum ordering, ordered and unordered delivery, quality of service present or absent, many different kinds, reliability different, levels of loss, security, privacy rules, encryption, etc. Parameters, different timeouts, flow specifications, etc. Accounting by connect time, packet, byte, or not at all. Figure 5.2.38. Some of the many ways networks can differ. Support multicast. The differing maximum packet sizes used by different networks can be a major nuisance too. How do you pass an 8000 byte packet through a network whose maximum size is 1500 bytes? If packets on a connection-oriented network transit a connectionless network, they may arrive in a different order than they were sent. That is something the sender likely did not expect, and it might come as an unpleasant surprise to the receiver as well. These kinds of differences can be papered over with some effort. For example, a gateway joining two networks might generate separate packets for each destination in lieu of better network support for multicasting. A large packet might be broken up, sent in pieces, and then joined back together. Receivers might buffer packets and deliver them in order. Networks also can differ in large respects that are more difficult to reconcile. The clearest example is quality of service. If one network has strong QoS and the other offers best effort service, it will be impossible to make bandwidth and delay guarantees for real-time traffic end to end. In fact, they can likely only be made while the best effort network is operated at a low utilization or hardly used, which is unlikely to be the goal of most ISPs. Security mechanisms are problematic, but at least encryption for confidentiality and data integrity can be layered on top of networks that do not already include it. Finally, differences in accounting can lead to unwelcome bills when normal usage suddenly becomes expensive, as roaming mobile phone users with data plans have discovered 5.5.2 how networks can be connected. There are two basic choices for connecting different networks. We can build devices that translate or convert packets from each kind of network into packets for each other network. Or, like good computer scientists, we can try to solve the problem by adding a layer of indirection and building a common layer on top of the different networks. In either case, the devices are placed at the boundaries between networks. Early on, Cerf and Can, 1974, argued for a common layer to hide the differences of existing networks. This approach has been tremendously successful, and the layer they proposed was eventually separated into the TCP and IP protocols. Almost 4 decades later, IP is the foundation of the modern internet. For this accomplishment, Cerf and Can were awarded the 2004 Turing Award, informally known as the Nobel Prize of Computer Science. IP provides a universal packet format that all routers recognize and that can be passed through almost every network. IP has extended its reach from computer networks to take over the telephone network. It also runs on sensor networks and other tiny devices that were once presumed too resource constrained to support it. We have discussed several different devices that connect networks, including repeaters, hubs, switches, bridges, routers, and gateways. Repeaters and hubs just move bits from one wire to another. They are mostly analog devices and do not understand anything about higher layer protocols. Bridges and switches operate at the link layer. They can be used to build networks, but only with minor protocol translation in the process. For example, between 10, 100 and 1000 megabits per second Ethernet switches. Our focus in this section is interconnection devices that operate at the network layer, namely the routers. We will leave gateways, which are here layer interconnection devices, until later. Let us first explore at a high level how interconnection with a common network layer can be used to interconnect to similar networks. An internet comprised of 802.11 MPLS and Ethernet networks is shown in figure 5.239. Suppose that the source machine on the 802.11 network wants to send a packet to the destination machine on the Ethernet network. Since these technologies are different, and they are further separated by another kind of network, MPLS, some added processing is needed at the boundaries between the networks. Because different networks may, in general, have different forms of addressing, the packet carries a network layer address that can identify any host across the 3 networks. The first boundary the packet reaches is when it transitions from an 802.11 network to an MPLS network. 802.11 provides a connectionless service, but MPLS provides a connection-oriented service. This means that a virtual circuit must be set up to cross that network. Once the packet has traveled along the virtual circuit, it will reach the Ethernet network. At this boundary, the packet may be too large to be carried, since 802.11 can work with larger frames than Ethernet. To handle this problem, the packet is divided into fragments, and each fragment is sent separately. When the fragments reach the destination, they are reassembled. Then the packet has completed its journey. The protocol processing for this journey is shown in figure 5.239. B. The source accepts data from the transport layer and generates a packet with the common network layer header, which is IP in this example. The network header contains the 802.11 MPLS Ethernet source destination packet virtual circuit 802.11 IP router 802.11 IP MPLS IPF IP MPLS IP physical. B. Data from transport layer figure 5239. A packet crossing different networks. B. Network and link layer protocol processing ultimate destination address, which is used to determine that the packet should be sent via the first router. So the packet is encapsulated in an 802.11 frame whose destination is the first router and transmitted. At the router, the packet is removed from the frame's data field and the 802.11 frame header is discarded. The router now examines the IP address in the packet and looks up this address in its routing table. Based on this address, it decides to send the packet to the second router next. For this part of the path, an MPLS virtual circuit must be established to the second router and the packet must be encapsulated with MPLS headers that travel this circuit. At the far end, the MPLS header is discarded and the network address is again consulted to find the next network layer hop. It is the destination itself. Since the packet is too long to be sent over Ethernet, it is split into two portions. Each of these portions is put into the data field of an Ethernet frame and sent to the Ethernet address of the destination. At the destination, the Ethernet header is stripped from each of the frames and the contents are reassembled. The packet has finally reached its destination. Observe that there is an essential difference between the routed case and the switched or bridged case. With a router, the packet is extracted from the frame and the network address in the packet is used for deciding where to send it. With a switch or bridge, the entire frame is transported on the basis of its MAC address. Switches do not have to understand the network layer protocol being used to switch packets. Routers do. Unfortunately, internetworking is not as easy as we have made it sound. In fact, when bridges were introduced, it was intended that they would join different types of networks, or at least different types of LANs. They were to do this by translating frames from one LAN into frames from another LAN. However, this did not work well for the same reason that internetworking is difficult. The differences in the features of LANs, such as different maximum packet sizes and LANs with and without priority classes, are hard to mask. Today, bridges are predominantly used to connect the same kind of network at the link layer, and routers connect different networks at the network layer. Internetworking has been very successful at building large networks, but it only works when there is a common network layer. There have, in fact, been many network protocols over time. Getting everybody to agree on a single format is difficult when companies perceive it to their commercial advantage to have a proprietary format that they control. Examples besides IP, which is now the near universal network protocol, were IPX, Snap, and Apple Talk. None of these protocols are still in widespread use, but there will always be other protocols. The most relevant example now is probably IPv4 and IPv6. While these are both versions of IP, they are not compatible, or it would not have been necessary to create IPv6. A router that can handle multiple network protocols is called a multiprotocol router. It must either translate the protocols or leave connection for a higher protocol layer. Neither approach is entirely satisfactory. Connection at a higher layer, say, by using TCP, requires that all the networks implement TCP, which may not be the case. Then, it limits usage across the networks to applications that use TCP, which does not include many real-time applications. The alternative is to translate packets between the networks. However, unless the packet formats are close relatives with the same information fields, such conversions will always be incomplete and often doomed to failure. For example, IPv6 addresses are 128 bits long. They will not fit in a 32-bit IPv4 address field, no matter how hard the router tries. Getting IPv4 and IPv6 to run in the same network has proven to be a major obstacle to the deployment of IPv6. To be fair, so has getting customers to understand why they should want IPv6 in the first place. Greater problems can be expected when translating between fundamentally different protocols, such as connectionless and connection-oriented network protocols. Given these difficulties, conversion is only rarely attempted. Arguably, even IP has only worked so well by serving as a kind of lowest common denominator. It requires little of the networks on which it runs, but offers only best effort service as a result. 5.5.3 Tunneling. Handling the general case of making two different networks interwork is exceedingly difficult. However, there is a common special case that is manageable even for different network protocols. This case is where the source and destination hosts are on the same type of network, but there is a different network in between. As an example, think of an international bank with an IPv6 network in Paris, an IPv6 network in London, and connectivity between the offices via the IPv4 internet. This situation is shown in figure 5-40. IPv6 IPv4 IPv6 Paris London tunnel router IPv6 packet IPv4 IPv6 packet IPv6 packet. Figure 5-40. Tunneling a packet from Paris to London. The solution to this problem is a technique called tunneling. To send an IP packet to a host in the London office, a host in the Paris office constructs the packet containing an IPv6 address in London and sends it to the multi-protocol router that connects the Paris IPv6 network to the IPv4 internet. When this router gets the IPv6 packet, it encapsulates the packet with an IPv4 header addressed to the IPv4 side of the multi-protocol router that connects to the London IPv6 network. That is, the router puts a IPv6 packet inside a IPv4 packet. When this wrapped packet arrives, the London router removes the original IPv6 packet and sends it onward to the destination host. The path through the IPv4 internet can be seen as a big tunnel extending from one multi-protocol router to the other. The IPv6 packet just travels from one end of the tunnel to the other, snug in its nice box. It does not have to worry about dealing with IPv4 at all. Neither do the hosts in Paris or London. Only the multi-protocol routers have to understand both IPv4 and IPv6 packets. In effect, the entire trip from one multi-protocol router to the other is like a hop over a single link. An analogy may make tunneling clearer. Consider a person driving her car from Paris to London. Within France, the car moves under its own power, but when it hits the English Channel, it is loaded onto a high-speed train and transported to England through the Channel. Cars are not permitted to drive through the Channel. Effectively, the car is being carried as freight, as depicted in figure 5-41. At the far end, the car is let loose on the English roads and once again continues to move under its own power. Tunneling of packets through a foreign network works the same way. Tunneling is widely used to connect isolated hosts and networks using other networks. The network that results is called an overlay, since it has effectively been overlaid on the base network. Deployment of a network protocol with a new feature is a common reason, as our IPv6 over IPv4 example shows. The disadvantage of tunneling is that none of the hosts on the network that is tunneled over can be reached because the packets cannot escape in the middle of the tunnel. Car English Channel Paris London Railroad track railroad carriage figure 5-41. Tunneling a car from France to England. However, this limitation of tunnels is turned into an advantage with VPNs, virtual private networks. A VPN is simply an overlay that is used to provide a measure of security. We will explore VPNs when we get to chapter 8.5.5.4 Internetwork routing. Routing through an internet poses the same basic problem as routing within a single network, but with some added complications. To start, the networks may internally use different routing algorithms. For example, one network may use link state routing and another distance vector routing. Since link state algorithms need to know the topology, but distance vector algorithms do not, this difference alone would make it unclear how to find the shortest paths across the internet. Networks run by different operators lead to bigger problems. First, the operators may have different ideas about what is a good path through the network. One operator may want the route with the least delay, while another may want the most inexpensive route. This will lead the operators to use different quantities to set the shortest path costs, for instance, milliseconds of delay versus monetary cost. The weights will not be comparable across networks, so shortest paths on the internet will not be well defined. Worse yet, one operator may not want another operator to even know the details of the paths in its network, perhaps because the weights and paths may reflect sensitive information, such as the monetary cost, that represents a competitive business advantage. Finally, the internet may be much larger than any of the networks that comprise it. It may therefore require routing algorithms that scale well by using a hierarchy, even if none of the individual networks need to use a hierarchy. All of these considerations lead to a two-level routing algorithm. Within each network, an intradomain or interior gateway protocol is used for routing. Gateway is an older term for outer. It might be a link state protocol of the kind we have already described. Across the networks that make up the internet, an interdomain or exterior gateway protocol is used. The networks may all use different intradomain protocols, but they must use the same interdomain protocol. In the internet, the interdomain routing protocol is called BGP, Border Gateway Protocol. We will describe it in the next section. There is one more important term to introduce. Since each network is operated independently of all the others, it is often referred to as an autonomous system. A good mental model for an is an ISP network. In fact, an ISP network may be comprised of more than one if it is managed, or has been acquired, as multiple networks. But the difference is usually not significant. The two levels are usually not strictly hierarchical, as highly suboptimal paths might result if a large international network and a small regional network were both abstracted to be a single network. However, relatively little information about routes within the networks is exposed to find routes across the internetwork. This helps to address all of the complications. It improves scaling and lets operators freely select routes within their own networks using a protocol of their choosing. It also does not require weights to be compared across networks or expose sensitive information outside of networks. However, we have said little so far about how the routes across the networks of the internet are determined. In the internet, a large determining factor is the business arrangement between ISPs. Each ISP may charge or receive money from the other ISPs for carrying traffic. Another factor is that if internetwork routing requires crossing international boundaries, various laws may suddenly come into play, such as Sweden's strict privacy laws about exporting personal data about Swedish citizens from Sweden. All of these non-technical factors are wrapped up in the concept of a routing policy that governs the way autonomous networks select the routes that they use. We will return to routing policies when we describe BGP 5.5.5 packet fragmentation. Each network or link imposes some maximum size on its packets. These limits have various causes, among them 1. Hardware, for instance, the size of an Ethernet frame. 2. Operating system, for instance, all buffers are 512 bytes. 3. Protocols, for instance, the number of bits in the packet length field. 4. Compliance with some international standard. 5. Desire to reduce error-induced retransmissions to some level. 6. Desire to prevent one packet from occupying the channel too long. The result of all these factors is that the network designers are not free to choose any old maximum packet size they wish. Maximum payloads for some common technologies are 1500 bytes for Ethernet and 2272 bytes for 802.11. IP is more generous, allows for packets as big as 65,515 bytes. Hosts usually prefer to transmit large packets because this reduces packet overhead such as bandwidth wasted on header bytes. An obvious internetworking problem appears when a large packet wants to travel through a network whose maximum packet size is too small. This nuisance has been a persistent issue, and solutions to it have evolved along with much experience gained on the internet. One solution is to make sure the problem does not occur in the first place. However, this is easier said than done. A source does not usually know the path a packet will take through the network to a destination, so it certainly does not know how small packets must be to get there. This packet size is called the path MTU, path maximum transmission unit. Even if the source did know the path MTU, packets are routed independently in a connectionless network such as the internet. This routing means that paths may suddenly change, which can unexpectedly change the path MTU. The alternative solution to the problem is to allow routers to break up packets into fragments, sending each fragment as a separate network layer packet. However, as every parent of a small child knows, converting a large object into small fragments is considerably easier than the reverse process. Physicists have even given this effect a name, the second law of thermodynamics. Packet switching networks too have trouble putting the fragments back together again. Two opposing strategies exist for combining the fragments back into the original packet. The first strategy is to make fragmentation caused by a small packet network transparent to any subsequent networks through which the packet must pass on its way to the ultimate destination. This option is shown in figure 5.42. In this approach, when an oversized packet arrives at G1, the router breaks it up into fragments. Each fragment is addressed to the same exit router, G2, where the pieces are combined. In this way, passage through the small packet network is made transparent. Subsequent networks are not even aware that fragmentation has occurred. Transparent fragmentation is straightforward, but has some problems. For one thing, the exit router must know when it has received all the pieces, so either a count field or an end of packet bit must be provided. Also, because all packets must exit via the same router so that they can be reassembled, the routes are constrained. By not allowing some fragments to follow one route to the ultimate destination and other fragments a disjoint route, some performance may be lost. More significant is the amount of work that the router may have to do. It may need to buffer the fragments as they arrive and decide when to throw them away if not all of the fragments arrive. Some of this work may be wasteful too, as the packet may pass through a series of small packet networks and need to be repeatedly fragmented and reassembled. The other fragmentation strategy is to refrain from recombining fragments at any intermediate routers. Once a packet has been fragmented, each fragment is treated as though it were an original packet. The routers pass the fragments, as shown in figure 5.42b, and reassembly is performed only at the destination host. Packet network 1 G1 fragments a large packet G2 reassembles the fragments G3 fragments again G4 reassembles again network 2. Packet G1 fragments a large packet the fragments are not reassembled until the final destination, a host, is reached. B. Figure 5.42. Transparent fragmentation. B. Non-transparent fragmentation. The main advantage of non-transparent fragmentation is that it requires routers to do less work. It works this way. A complete design requires that the fragments be numbered in such a way that the original data stream can be reconstructed. The design used by IP is to give every fragment a packet number, carried on all packets, an absolute byte offset within the packet, and a flag indicating whether it is the end of the packet. An example is shown in figure 5.43. While simple, this design has some attractive properties. Fragments can be placed in a buffer at the destination in the right place for reassembly, even if they arrive out of order. Fragments can also be fragmented if they pass over a network with a yet smaller MTU. This is shown in figure 5.43c. Retransmissions of the packet, if all fragments were not received, can be fragmented into different pieces. Finally, fragments can be of arbitrary size, down to a single byte plus the packet header. In all cases, the destination simply uses the packet number and fragment offset to place the data in the right position, and the end of packet flag to determine when it has the complete packet. Unfortunately, this design still has problems. The overhead can be higher than with transparent fragmentation, because fragment headers are now carried over some links where they may not be needed. But the real problem is the existence of fragments in the first place. Kent and Mogul, 1987, argue that fragmentation is detrimental to performance because, as well as the header overheads, a whole packet is lost if any of its fragments are lost, and because fragmentation is more of a burden for hosts than was originally realized. Number of the first elementary fragment in this packet number end of packet bit 27 0 1 a b c d e f g h I j 27 0 0 a b c d e f g h 27 8 1 I j 27 0 0 a b c d e 27 5 0 f g h 27 8 1 IJ header 1 byte header B C figure 5 to 43. Fragmentation when the elementary data size is 1 byte. Original packet containing 10 data bytes. B. Fragments after passing through a network with maximum packet size of 8 payload bytes plus header. C. Fragments after passing through a size 5 gateway. This leads us back to the original solution of getting rid of fragmentation in the network, the strategy used in the modern internet. The process is called Path MTU Discovery, Mogul and Deering, 1990. It works as follows. Each IP packet is sent with its header bits set to indicate that no fragmentation is allowed to be performed. If a router receives a packet that is too large, it generates an error packet, returns it to the source, and drops the packet. This is shown in figure 5 to 44. When the source receives the error packet, it uses the information inside to refragment the packet into pieces that are small enough for the router to handle. If a router further down the path has an even smaller MTU, the process is repeated. Source destination packet with length. Try 1200, try 900, 1400, 1200, 900 figure 5 to 44. Path MTU discovery. The advantage of Path MTU discovery is that the source now knows what length packet to send. If the routes and Path MTU change, new error packets will be triggered, and the source will adapt to the new path. However, fragmentation is still needed between the source and the destination, unless the higher layers learn the Path MTU and pass the right amount of data to IP. TCP and IP are typically implemented together as TCP/IP to be able to pass this sort of information. Even if this is not done for other protocols, fragmentation has still been moved out of the network and into the hosts. The disadvantage of Path MTU discovery is that there may be added startup delays simply to send a packet. More than one round-trip delay may be needed to probe the path and find the MTU before any data is delivered to the destination. This begs the question of whether there are better designs. The answer is probably yes. Consider the design in which each router simply truncates packets that exceed its MTU. This would ensure that the destination learns the MTU as rapidly as possible from the amount of data that was delivered and receives some of the data. 5.6 The network layer in the internet. It is now time to discuss the network layer of the internet in detail. But before getting into specifics, it is worth taking a look at the principles that drove its design in the past and made it the success that it is today. All too often, nowadays, people seem to have forgotten them. These principles are enumerated and discussed in RFC 1958, which is well worth reading and should be mandatory for all protocol designers with a final exam at the end. This RFC draws heavily on ideas put forth by Clark, 1988, and Saltzer and others, 1984. We will now summarize what we consider to be the top 10 principles, from most important to least important. 1. Make sure it works. Do not finalize the design or standard until multiple prototypes have successfully communicated with each other. All too often, designers first write a 1,000-page standard, get it approved, then discover it is deeply flawed and does not work. Then they write version 1.1 of the standard. This is not the way to go to. Keep it simple. When in doubt, use the simplest solution. William of Ockham stated this principle, Ockham's razor, in the 14th century. Put in modern terms, fight features. If a feature is not absolutely essential, leave it out, especially if the same effect can be achieved by combining other features. 3. Make clear choices. If there are several ways of doing the same thing, choose one. Having two or more ways to do the same thing is looking for trouble. Standards often have multiple options or modes or parameters because several powerful parties insist that their way is best. Designers should strongly resist this tendency. Just say number 4. Exploit modularity. This principle leads directly to the idea of having protocol stacks, each of whose layers is independent of all the other ones. In this way, if circumstances require one module or layer to be changed, the other ones will not be affected. 5. Expect heterogeneity. Different types of hardware, transmission facilities, and applications will occur on any large network. To handle them, the network design must be simple, general, and flexible. 6. Avoid static options and parameters. If parameters are unavoidable, for instance, maximum packet size, it is best to have the sender and receiver negotiate a value, rather than defining fixed choices. 7. Look for a good design. It need not be perfect. Often, the designers have a good design, but it cannot handle some weird special case. Rather than messing up the design, the designer should go with a good design and put the burden of working around it on the people with the strange requirements. 8. Be strict when sending and tolerant when receiving. In other words, send only packets that rigorously comply with the standards, but expect incoming packets that may not be fully conformant and try to deal with them. 9. Think about scalability. If the system is to handle millions of hosts and billions of users effectively, no centralized databases of any kind are tolerable and load must be spread as evenly as possible over the available resources. 10. Consider performance and cost. If a network has poor performance or outrageous costs, nobody will use it. Let us now leave the general principles and start looking at the details of the internet's network layer. In the network layer, the internet can be viewed as a collection of networks or ASes, autonomous systems, that are interconnected. There is no real structure, but several major backbones exist. These are constructed from high bandwidth lines and fast routers. The biggest of these backbones, to which everyone else connects to reach the rest of the internet, are called Tier 1 networks. Attached to the backbones are ISPs, internet service providers, that provide internet access to homes and businesses, data centers and co-location facilities full of server machines, and regional, mid-level, networks. The data centers serve much of the content that is sent over the internet. Attached to the regional networks are more ISPs, LANs at many universities and companies, and other edge networks. A sketch of this quasi-hierarchical organization is given in Figure 5-45. Leased lines to Asia: a US backbone, leased transatlantic lines, a European backbone, national network, company network, Ethernet IP router, mobile network, Wi maximum cable, home network, regional network. Figure 5-45. The internet is an interconnected collection of many networks. The glue that holds the whole internet together is the network layer protocol, IP, Internet Protocol. Unlike most older network layer protocols, IP was designed from the beginning with Internetworking in mind. A good way to think of the network layer is this: its job is to provide a best effort, that is, not guaranteed, way to transport packets from source to destination, without regard to whether these machines are on the same network, or whether there are other networks in between them. Communication in the internet works as follows. The transport layer takes data streams and breaks them up, so that they may be sent as IP packets. In theory, packets can be up to 64 KB each, but in practice they are usually not more than 1500 bytes, so they fit in one Ethernet frame. IP routers forward each packet through the internet, along a path from one router to the next, until the destination is reached. At the destination, the network layer hands the data to the transport layer, which gives it to the receiving process. When all the pieces finally get to the destination machine, they are reassembled by the network layer into the original datagram. This datagram is then handed to the transport layer. In the example of Figure 5-45, a packet originating at a host on the home network has to traverse 4 networks and a large number of IP routers before even getting to the company network on which the destination host is located. This is not unusual in practice, and there are many longer paths. There is also much redundant connectivity in the internet, with backbones and ISPs connecting to each other in multiple locations. This means that there are many possible paths between two hosts. It is the job of the IP routing protocols to decide which paths to use. 5.6.1 The IP version 4 protocol. An appropriate place to start our study of the network layer in the internet is with the format of the IP datagrams themselves. An IPv4 datagram consists of a header part and a body or payload part. The header has a 20 byte fixed part and a variable length optional part. The header format is shown in figure 5 to 46. The bits are transmitted from left to right and top to bottom, with the high order bit of the version field going first. This is a big endian network byte order. On little endian machines, such as Intel x86 computers, a software conversion is required on both transmission and reception. In retrospect, little endian would have been a better choice, but at the time IP was designed, no one knew it would come to dominate computing. Version IHL total length time to live protocol differentiated services identification header checksum fragment offset source address destination address options 0 or more words DFMF 32 bits figure 5 to 46. The IPv4 Internet Protocol header. The version field keeps track of which version of the protocol the datagram belongs to. Version 4 dominates the internet today, and that is where we have started our discussion. By including the version at the start of each datagram, it becomes possible to have a transition between versions over a long period of time. In fact, IPv6, the next version of IP, was defined more than a decade ago, yet is only just beginning to be deployed. We will describe it later in this section. Its use will eventually be forced when each of China's almost 231 people has a desktop PC, a laptop, and an IP phone. As an aside on numbering, IPv5 was an experimental real-time stream protocol that was never widely used. Since the header length is not constant, a field in the header, IHL, is provided to tell how long the header is, in 32-bit words. The minimum value is 5, which applies when no options are present. The maximum value of this 4-bit field is 15, which limits the header to 60 bytes, and thus the options field to 40 bytes. For some options, such as one that records the route a packet has taken, 40 bytes is far too small, making those options useless. The differentiated services field is one of the few fields that has changed its meaning slightly over the years. Originally, it was called the type of service field. It was and still is intended to distinguish between different classes of service. Various combinations of reliability and speed are possible. For digitized voice, fast delivery beats accurate delivery. For file transfer, error-free transmission is more important than fast transmission. The type of service field provided 3 bits to signal priority and 3 bits to signal whether a host cared more about delay, throughput, or reliability. However, no one really knew what to do with these bits at routers, so they were left unused for many years. When differentiated services were designed, IETF threw in the towel and reused this field. Now, the top 6 bits are used to mark the packet with its service class. We described the expedited and assured services earlier in this chapter. The bottom 2 bits are used to carry explicit congestion notification information, such as whether the packet has experienced congestion. We described explicit congestion notification as part of congestion control earlier in this chapter. The total length includes everything in the datagram, both header and data. The maximum length is 65,535 bytes. At present, this upper limit is tolerable, but with future networks, larger datagrams may be needed. The identification field is needed to allow the destination host to determine which packet a newly arrived fragment belongs to. All the fragments of a packet contain the same identification value. Next comes an unused bit, which is surprising, as available real estate in the IP header is extremely scarce. As an April Fool's joke, Belavin, 2003, proposed using this bit to detect malicious traffic. This would greatly simplify security, as packets with the evil bit set would be known to have been sent by attackers and could just be discarded. Unfortunately, network security is not this simple. Then come 2 1-bit fields related to fragmentation. DF stands for don't fragment. It is an order to the routers not to fragment the packet. Originally, it was intended to support hosts incapable of putting the pieces back together again. Now it is used as part of the process to discover the path MTU, which is the largest packet that can travel along a path without being fragmented. By marking the datagram with the DF bit, the sender knows it will either arrive in one piece or an error message will be returned to the sender. MF stands for more fragments. All fragments except the last one have this bit set. It is needed to know when all fragments of a datagram have arrived. The fragment offset tells where in the current packet this fragment belongs. All fragments except the last one in a datagram must be a multiple of 8 bytes, the elementary fragment unit. Since 13 bits are provided, there is a maximum of 8192 fragments per datagram, supporting a maximum packet length up to the limit of the total length field. Working together, the identification, IMF, and fragment offset fields are used to implement fragmentation as described in Secretary 5.5.5. The TTL, time to live, field is a counter used to limit packet lifetimes. It was originally supposed to count time in seconds, allowing a maximum lifetime of 255 seconds. It must be decremented on each hop, and is supposed to be decremented multiple times when a packet is queued for a long time on a router. In practice, it just counts hops. When it hits 0, the packet is discarded and a warning packet is sent back to the source host. This feature prevents packets from wandering around forever, something that otherwise might happen if the routing tables ever become corrupted. When the network layer has assembled a complete packet, it needs to know what to do with it. The protocol field tells it which transport process to give the packet to. TCP is one possibility, but so are UDP and some others. The numbering of protocols is global across the entire internet. Protocols and other assigned numbers were formerly listed in RFC 1700, but nowadays they are contained in an online database located at www.ina.org. Since the header carries vital information such as addresses, it rates its own checksum for protection, the header checksum. The algorithm is to add up all the 16-bit halfwords of the header as they arrive, using ones complement arithmetic, and then take the ones complement of the result. For purposes of this algorithm, the header checksum is assumed to be 0 upon arrival. Such a checksum is useful for detecting errors while the packet travels through the network. Note that it must be recomputed at each hop, because at least one field always changes, the time to live field, but tricks can be used to speed up the computation. The source address and destination address indicate the IP address of the source and destination network interfaces. We will discuss internet addresses in the next section. The options field was designed to provide an escape, to allow subsequent versions of the protocol to include information not present in the original design, to permit experimenters to try out new ideas, and to avoid allocating header bits to information that is rarely needed. The options are of variable length. Each begins with a 1-byte code identifying the option. Some options are followed by a 1-byte option length field, and then 1 or more data bytes. The options field is padded out to a multiple of 4 bytes. Originally, the 5 options listed in figure 5 to 47 were defined. The security option tells how secret the information is. In theory, a military router might use this field to specify not to route packets through certain countries the military considers to be bad guys. In practice, all routers ignore it, so its only practical function is to help spies find the good stuff more easily. The strict source routing option gives a complete path from source to destination as a sequence of IP addresses. The datagram is required to follow that option. Description security specifies how secret the datagram is. Strict source routing gives the complete path to be followed. Loose source routing gives a list of routers not to be missed. Record route makes each router append its IP address. Timestamp makes each router append its address and timestamp. Figure 5 to 47. Some of the IP options: exact route, It is most useful for system managers who need to send emergency packets when the routing tables have been corrupted, or for making timing measurements. The loose source routing option requires the packet to traverse the list of routers specified, in the order specified, but it is allowed to pass through other routers on the way. Normally, this option will provide only a few routers to force a particular path. For example, to force a packet from London to Sydney, to go west instead of east, this option might specify routers in New York, Los Angeles, and Honolulu. This option is most useful when political or economic considerations dictate passing through or avoiding certain countries. The record route option tells each router along the path to append its IP address to the options field. This allows system managers to track down bugs in the routing algorithms. Why are packets from Houston to Dallas visiting Tokyo first? When the ARPANET was first set up, no packet ever passed through more than 9 routers, so 40 bytes of options was plenty. As mentioned above, now it is too small. Finally, the timestamp option is like the record route option, except that in addition to recording its 32-bit IP address, each router also records a 32-bit timestamp. This option too is mostly useful for network measurement. Today, IP options have fallen out of favor. Many routers ignore them or do not process them efficiently, shunting them to the side is an uncommon case. That is, they are only partly supported, and they are rarely used. 5.6.2 IP addresses. A defining feature of IPv4 is its 32-bit addresses. Every host and router on the internet has an IP address that can be used in the source address and destination address fields of IP packets. It is important to note that an IP address does not actually refer to a host. It really refers to a network interface, so if a host is on 2 networks, it must have 2 IP addresses. However, in practice, most hosts are on 1 network, and thus have 1 IP address. In contrast, routers have multiple interfaces, and thus multiple IP addresses. Prefixes IP addresses are hierarchical, unlike Ethernet addresses. Each 32-bit address is comprised of a variable length network portion in the top bits and a host portion in the bottom bits. The network portion has the same value for all hosts on a single network, such as an Ethernet LAN. This means that a network corresponds to a contiguous block of IP address space. This block is called a prefix. IP addresses are written in dotted decimal notation. In this format, each of the 4 bytes is written in decimal, from 0 to 255. For example, the 32-bit hexadecimal address ATD00297 is written as 128.208.2.151. Prefixes are written by giving the lowest IP address in the block and the size of the block. The size is determined by the number of bits in the network portion. The remaining bits in the host portion can vary. This means that the size must be a power of 2. By convention, it is written after the prefix IP address as a slash followed by the length in bits of the network portion. In our example, if the prefix contains 28 addresses, and so leaves 24 bits for the network portion, it is written as 128.208.0.0 over 24. Since the prefix length cannot be inferred from the IP address alone, routing protocols must carry the prefixes to routers. Sometimes prefixes are simply described by their length, as in a /16 which is pronounced /16. The length of the prefix corresponds to a binary mask of ones in the network portion. When written out this way, it is called a subnet mask. It can be ANDed with the IP address to extract only the network portion. For our example, the subnet mask is 255.255.255.0. Figure 5 to 48 shows a prefix and a subnet mask. 32 bits network prefix length equals L bits host subnet mask 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 0 0 0 0 0 0 0 0 32 L bits. Figure 5 to 48. an IP prefix and a subnet mask. Hierarchical addresses have significant advantages and disadvantages. The key advantage of prefixes is that routers can forward packets based on only the network portion of the address, as long as each of the networks has a unique address block. The host portion does not matter to the routers because all hosts on the same network will be sent in the same direction. It is only when the packets reach the network for which they are destined that they are forwarded to the correct host. This makes the routing tables much smaller than they would otherwise be. Consider that the number of hosts on the internet is approaching 1 billion. That would be a very large table for every router to keep. However, by using a hierarchy, routers need to keep routes for only around 300,000 prefixes. While using a hierarchy lets internet routing scale, it has two disadvantages. First, the IP address of a host depends on where it is located in the network. An Ethernet address can be used anywhere in the world, but every IP address belongs to a specific network, and routers will only be able to deliver packets destined to that address to the network. Designs such as mobile IP are needed to support hosts that move between networks, but want to keep the same IP addresses. The second disadvantage is that the hierarchy is wasteful of addresses unless it is carefully managed. If addresses are assigned to networks in 2 large blocks, there will be many addresses that are allocated, but not in use. This allocation would not matter much if there were plenty of addresses to go around. However, it was realized more than 2 decades ago that the tremendous growth of the internet was rapidly depleting the free address space. IPv6 is a solution to this shortage, but until it is widely deployed there will be great pressure to allocate IP addresses so that they are used very efficiently. Subnet's network numbers are managed by a non-profit corporation called ICANN, Internet Corporation for Assigned Names and Numbers, to avoid conflicts. In turn, ICANN has delegated parts of the address space to various regional authorities, which dole out IP addresses to ISPs and other companies. This is the process by which a company is allocated a block of IP addresses. However, this process is only the start of the story, as IP address assignment is ongoing as companies grow. We have said that routing by prefix requires all the hosts in a network to have the same network number. This property can cause problems as networks grow. For example, consider a university that started out with our example /16 prefix for use by the computer science department for the computers on its Ethernet. A year later, the electrical engineering department wants to get on the internet. The art department soon follows suit. What IP addresses should these departments use? Getting further blocks requires going outside the university and may be expensive or inconvenient. Moreover, the /16 already allocated has enough addresses for over 60,000 hosts. It might be intended to allow for significant growth, but until that happens, it is wasteful to allocate further blocks of IP addresses to the same university. A different organization is required. The solution is to allow the block of addresses to be split into several parts for internal use as multiple networks, while still acting like a single network to the outside world. This is called subnetting, and the networks, such as Ethernet LANs, that result from dividing up a larger network are called subnets. As we mentioned in chapter 1, you should be aware that this new usage of the term conflicts with older usage of subnet to mean the set of all routers and communication lines in a network. Figure 5-49 shows how subnets can help with our example. The single /16 has been split into pieces. This split does not need to be even, but each piece must be aligned so that any bits can be used in the lower host portion. In this case, half of the block, a /17, is allocated to the computer science dept, a quarter is allocated to the electrical engineering department, a /18, and 1/8, a /19, to the art department. The remaining eighth is unallocated. A different way to see how the block was divided is to look at the resulting prefixes when written in binary notation. Computer science 10 million, 11 million and 10,001 vertical bracket XXXXXXXXXXXXXXXXXXXX electrical England. 10 million, 11 million and 10,000 00 vertical bracket xxxxxxxxxxxxxxxxxx art. 10 million, 11 million and 10,000 011 vertical bracket xxxxxxxxxxxxxxxxxx here. The vertical bar shows the boundary between the subnet number and the host portion. Art 128.208.0.0/16 to internet 128.208.96.0/19 EECS 128.208.128.0/17 128.208.0.0/18 figure 5 to 49. Splitting an IP prefix into separate networks with subnetting. When a packet comes into the main router, how does the router know which subnet to give it to? This is where the details of our prefixes come in. One way would be for each router to have a table with 65,536 entries telling it which outgoing line to use for each host on campus. But this would undermine the main scaling benefit we get from using a hierarchy. Instead, the routers simply need to know the subnet masks for the networks on campus. When a packet arrives, the router looks at the destination address of the packet and checks which subnet it belongs to. The router can do this by ANDing the destination address with the mask for each subnet and checking to see if the result is the corresponding prefix. For example, consider a packet destined for IP address 128.208.2.151. To see if it is for the computer science department, we end with 255.255.128.0 to take the first 17 bits, which is 128.208.0.0, and see if they match the prefix address, which is 128.208.128.0. They do not match. Checking the first 18 bits for the electrical engineering department, we get 128.208.0.0 when ANDing with the subnet mask. This does match the prefix address, so the packet is forwarded onto the interface which leads to the electrical engineering network. The subnet divisions can be changed later if necessary by updating all subnet masks at routers inside the university. Outside the network, the subnetting is not visible, so allocating a new subnet does not require contacting ICANN or changing any external databases. CIDR classless interdomain routing, even if blocks of IP addresses are allocated so that the addresses are used efficiently, there is still a problem that remains: routing table explosion. Routers in organizations at the edge of a network, such as a university, need to have an entry for each of their subnets, telling the router which line to use to get to that network. For routes to destinations outside of the organization, they can use the simple default rule of sending the packets on the line toward the ISP that connects the organization to the rest of the internet. The other destination addresses must all be out there somewhere. Routers and ISPs and backbones in the middle of the internet have no such luxury. They must know which way to go to get to every network, and no simple default will work. These core routers are said to be in the default free zone of the internet. No one really knows how many networks are connected to the internet anymore, but it is a large number, probably at least a million. This can make for a very large table. It may not sound large by computer standards, but realize that routers must perform a lookup in this table to forward every packet, and routers at large ISPs may forward up to millions of packets per second. Specialized hardware and fast memory are needed to process packets at these rates, not a general purpose computer. In addition, routing algorithms require each router to exchange information about the addresses it can reach with other routers. The larger the tables, the more information needs to be communicated and processed. The processing grows at least linearly with the table size. Greater communication increases the likelihood that some parts will get lost, at least temporarily, possibly leading to routing instabilities. The routing table problem could have been solved by going to a deeper hierarchy, like the telephone network. For example, having each IP address contain a country, state/province, city, network, and host field might work. Then, each router would only need to know how to get to each country, the states or provinces in its own country, the cities in its state or province, and the networks in its city. Unfortunately, this solution would require considerably more than 32 bits for IP addresses, and would use addresses inefficiently, and Liechtenstein would have as many bits in its addresses as the United States. Fortunately, there is something we can do to reduce routing table sizes. We can apply the same insight as subnetting. Routers at different locations can know about a given IP address as belonging to prefixes of different sizes. However, instead of splitting an address block into subnets, here we combine multiple small prefixes into a single larger prefix. This process is called route aggregation. The resulting larger prefix is sometimes called a supernet, to contrast with subnets as the division of blocks of addresses. With aggregation, IP addresses are contained in prefixes of varying sizes. The same IP address that one router treats as part of a /22, a block containing 210 addresses, may be treated by another router as part of a larger /20, which contains 212 addresses. It is up to each router to have the corresponding prefix information. This design works with subnetting and is called CIDR, classless interdomain routing, which is pronounced CIDR, as in the drink. The most recent version of it is specified in RFC 4632, Fuller and Lee, 2006. The name highlights the contrast with addresses that encode hierarchy with classes, which we will describe shortly. To make CIDR easier to understand, let us consider an example in which a block of 8192 IP addresses is available starting at 194.24.0.0. Suppose that Cambridge University needs 2048 addresses and is assigned the addresses 194.24.0.0 through 194. July 255, along with mask 255.255.248.0. This is a /21 prefix. Next, Oxford University asks for 4096 addresses. Since a block of 4096 addresses must lie on a 4096 byte boundary, Oxford cannot be given addresses starting at 194.24.8.0. Instead, it gets 194.24.16.0 through 194.24.31.255, along with subnet mask 255.255.240.0. Finally, the University of Edinburgh asks for 1024 addresses and is assigned addresses 194.24.8.0 through 194.24.11.255 and mask 255.255.252.0. These assignments are summarized in Figure 5250. University first address last address how many prefix Cambridge 194.24.0.0 194. The 24th of July 255 2048 194.24.0.0/21 Edinburgh 194.24.8.0 194.24.11.255 1024 194.24.8.0/22 available 194.24.12.0 194.24.15.255 1024 194.24.12.0/22 Oxford 194.24.16.0, 194.24.31.255, 4096, 194.24.16.0 over 20 figure. 5 to 50. A set of IP address assignments. All of the routers in the default free zone are now told about the IP addresses in the 3 networks. Routers close to the universities may need to send on a different outgoing line for each of the prefixes, so they need an entry for each of the prefixes in their routing tables. An example is a router in London in figure 5-51. Now let us look at these 3 universities from the point of view of a distant router in New York. All of the IP addresses in the 3 prefixes should be sent from New York, or the US in general, to London. The routing process in London notices this and combines the 3 prefixes into a single aggregate entry for the prefix 194.24.0.0 over 19 that it passes to the New York router. This prefix contains 8K addresses and covers the 3 universities and the otherwise unallocated 1024 addresses. By using aggregation, 3 prefixes have been reduced to 1, reducing the prefixes that the New York router must be told about and the routing table entries in the New York router. Edinburgh 192.24.0.0 over 19, 1 aggregate prefix, 192.24.8.0 over 20 to Cambridge Oxford. 192.24.16.0 over 20, 192.24.0.0 over 21 New York London. 3 prefixes, figure 5 to 51. Aggregation of IP prefixes. When aggregation is turned on, it is an automatic process. It depends on which prefixes are located where in the internet, not on the actions of an administrator assigning addresses to networks. Aggregation is heavily used throughout the internet and can reduce the size of router tables to around 200,000 prefixes. As a further twist, prefixes are allowed to overlap. The rule is that packets are sent in the direction of the most specific route, or the longest matching prefix that has the fewest IP addresses. Longest matching prefix routing provides a useful degree of flexibility, as seen in the behavior of the router at New York in figure 5-52. This router still uses a single aggregate prefix to send traffic for the 3 universities to London. However, the previously available block of addresses within this prefix has now been allocated to a network in San Francisco. One possibility is for the New York router to keep 4 prefixes, sending packets for 3 of them to London and packets for the 4th to San Francisco. Instead, longest matching prefix routing can handle this forwarding with the 2 prefixes that are shown. One overall prefix is used to direct traffic for the entire block to London. One more specific prefix is also used to direct a portion of the larger prefix to San Francisco. With the longest matching prefix rule, IP addresses within the San Francisco network will be sent on the outgoing line to San Francisco, and all other IP addresses in the larger prefix will be sent to London. Conceptually, CIDR works as follows. When a packet comes in, the routing table is scanned to determine if the destination lies within the prefix. It is possible that multiple entries with different prefix lengths will match, in which case the entry with the longest prefix is used. Thus, if there is a match for a /20 mask and a /24 mask, the /24 entry is used to look up the outgoing line for the packet. However, this process would be tedious if the table were really scanned entry by entry 192.24.0.0 over 19 192.24.8.0 over 22. 192.24.16.0 over 20 192.24.0.0 over 21 New York London 192.24.12.0 over 20 to San Francisco 192.24.12.0 over 22 figure 5 to 52. Longest matching prefix routing at the New York router. Instead, complex algorithms have been devised to speed up the address matching process. Ruz Sanchez and others, 2001. Commercial routers use custom VLSI chips with these algorithms embedded in hardware. Classful and special addressing to help you better appreciate why CIDR is so useful. We will briefly relate the design that predated it. Before 1993, IP addresses were divided into the 5 categories listed in figure 5 to 53. This allocation has come to be called classful addressing. 32 bits range of host addresses 1.0.0.0 to 127.255.255.255 128.0.0.0 to 191.255.255.255 192.0.0.0 to 223.255.255.255 224.0.0.0 to 239.255.255.255 240.0.0.0 to 255.255.255 Class 0 Network Host 10. Network host 110, network host 1110, multicast address 1111 reserved for future use. ABCDE figure 5 to 53. IP address formats. The Class A, B, and C formats allow for up to 128 networks with 16 million hosts each, 16,384 networks with up to 65,536 hosts each, and 2 million networks, for instance, LANs, with up to 256 hosts each, although a few of these are special. Also supported is multicast, the Class D format, in which a datagram is directed to multiple hosts. Addresses beginning with 1111 are reserved for use in the future. They would be valuable to use now given the depletion of the IPv4 address space. Unfortunately, many hosts will not accept these addresses as valid because they have been off limits for so long, and it is hard to teach old hosts new tricks. This is a hierarchical design, but unlike CIDR, the sizes of the address blocks are fixed. Over 2 billion addresses exist, but organizing the address space by classes wastes millions of them. In particular, the real villain is the Class B network. For most organizations, a Class A network with 16 million addresses is too big, and a Class C network with 256 addresses is too small. A Class B network with 65,536 is just right. In internet folklore, this situation is known as the Three Bears problem, as in Goldilocks and the Three Bears, Southey, 1848. In reality, though, a Class B address is far too large for most organizations. Studies have shown that more than half of all Class B networks have fewer than 50 hosts. A Class C network would have done the job, but no doubt every organization that asked for a Class B address thought that one day it would outgrow the 8-bit host field. In retrospect, it might have been better to have had Class C networks use 10 bits instead of 8 for the host number, allowing 1022 hosts per network. Had this been the case, most organizations would probably have settled for a Class C network, and there would have been 500,000 of them, versus only 16,384 Class B networks. It is hard to fault the internet's designers for not having provided more, and smaller, Class B addresses. At the time the decision was made to create the 3 classes, the internet was a research network connecting the major research universities in the US, plus a very small number of companies and military sites doing networking research. No one then perceived the internet becoming a mass market communication system rivaling the telephone network. At the time, someone no doubt said, the US has about 2,000 colleges and universities. Even if all of them connect to the internet and many universities in other countries join too, we are never going to hit 16,000, since there are not that many universities in the whole world. Furthermore, having the host number be an integral number of bytes speeds up packet processing, which was then done entirely in software. Perhaps someday people will look back and fault the folks who designed the telephone number scheme and say, what idiots. Why didn't they include the planet number in the phone number? But at the time, it did not seem necessary. To handle these problems, subnets were introduced to flexibly assign blocks of addresses within an organization. Later, CIDR was added to reduce the size of the global routing table. Today, the bits that indicate whether an IP address belongs to Class A, B, or C network are no longer used, though references to these classes in the literature are still common. To see how dropping the classes made forwarding more complicated, consider how simple it was in the old classful system. When a packet arrived at a router, a copy of the IP address was shifted right 28 bits to yield a 4-bit class number. A 16-way branch then sorted packets into A, B, C, and D classes, with 8 of the cases for Class A, 4 of the cases for Class B, and 2 of the cases for Class C. The code for each class then masked off the 8, 16, or 24-bit network number and right-aligned it in a 32-bit word. The network number was then looked up in the A, B, or C table, usually by indexing for A and B networks, and hashing for C networks. Once the entry was found, the outgoing line could be looked up, and the packet forwarded. This is much simpler than the longest matching prefix operation, which can no longer use a simple table lookup, because an IP address may have any length prefix. Class D addresses continue to be used in the internet for multicast. Actually, it might be more accurate to say that they are starting to be used for multicast, since internet multicast has not been widely deployed in the past. There are also several other addresses that have special meanings, as shown in figure 5-54. The IP address 0.0.0.0, the lowest address, is used by hosts when they are being booted. It means this network or this host. IP addresses with 0 as the network number refer to the current network. These addresses allow machines to refer to their own network without knowing its number, but they have to know the network mask to know how many zeros to include. The address consisting of a 1s, or 255.255.255.255, the highest address is used to mean all hosts on the indicated network. It allows broadcasting on the local network, typically a LAN. The addresses with a proper network number and all ones in the host field allow machines to send broadcast packets to distant LANs anywhere in the internet. However, many network administrators disable this feature as it is mostly a security hazard. Finally, all addresses of the form 127.xx.y.zz are reserved for loopback testing. Packets sent to that address are not put out onto the wire, they are processed locally and treated as incoming packets. This allows packets to be sent to the host without the sender knowing its number, which is useful for testing. This host A host on this network broadcast on the local network 0 host network 127, anything, broadcast on a distant network loopback 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. 1 1 1 1 1 1 1 1 1 1 0 0 0 0 1 1 1 1 1 1 1 1 figure 5-54. Special IP addresses. NAT network address translation IP addresses are scarce. an ISP might have a /16 address, giving it 65,534 usable host numbers. If it has more customers than that, it has a problem. This scarcity has led to techniques to use IP addresses sparingly. One approach is to dynamically assign an IP address to a computer when it is on and using the network, and to take the IP address back when the host becomes inactive. The IP address can then be assigned to another computer that becomes active. In this way, a single /16 address can handle up to 65,534 active users. This strategy works well in some cases, for example, for dial-up networking and mobile and other computers that may be temporarily absent or powered off. However, it does not work very well for business customers. Many PCs in businesses are expected to be on continuously. Some are employee machines, backed up at night, and some are servers that may have to serve a remote request at a moment's notice. These businesses have an access line that always provides connectivity to the rest of the internet. Increasingly, this situation also applies to home users subscribing to ADSL or internet over cable, since there is no connection charge, just a monthly flat rate charge. Many of these users have 2 or more computers at home, often one for each family member, and they all want to be online all the time. The solution is to connect all the computers into a home network via LAN and put a wireless router on it. The router then connects to the ISP. From the ISP's point of view, the family is now the same as a small business with a handful of computers. Welcome to Jones Incorporated. With the techniques we have seen so far, each computer must have its own IP address all day long. For an ISP with many thousands of customers, particularly business customers and families that are just like small businesses, the demand for IP addresses can quickly exceed the block that is available. The problem of running out of IP addresses is not a theoretical one that might occur at some point in the distant future. It is happening right here and right now. The long-term solution is for the whole internet to migrate to IPv6, which has 128-bit addresses. This transition is slowly occurring, but it will be years before the process is complete. To get by in the meantime, a quick fix was needed. The quick fix that is widely used today came in the form of NAT, Network Address Translation, which is described in our FC 3022, and which we will summarize below. For additional information, see Dutcher, 2001. The basic idea behind NAT is for the ISP to assign each home or business a single IP address, or at most, a small number of them, for internet traffic. Within the customer network, every computer gets a unique IP address, which is used for routing intramural traffic. However, just before a packet exits the customer network and goes to the ISP, an address translation from the unique internal IP address to the shared public IP address takes place. This translation makes use of 3 ranges of IP addresses that have been declared as private. Networks may use them internally as they wish. The only rule is that no packets containing these addresses may appear on the internet itself. The 3 reserved ranges are 10.0.0.0, 10.255.255.255 over 8, 16,777,216 hosts, 172.16.0.0, 172.31.255.255 over 12, 1,048,576 hosts, 192.168.0.0, 192.168.255.255 over 16, 65,536 hosts. The first range provides for 16,777,216 addresses, except for all zeros and all ones, as usual, and is the usual choice, even if the network is not large. The operation of NAT is shown in figure 5-55. Within the customer premises, every machine has a unique address of the form 10.xyz. However, before a packet leaves the customer premises, it passes through an NAT box that converts the internal IP source address 10.0.0.1 in the figure to the customer's true IP address 198.60.42.12 in this example. The NAT box is often combined in a single device with a firewall, which provides security by carefully controlling what goes into the customer network and what comes out of it. We will study firewalls in Chapter 8. It is also possible to integrate the NAT box into a router or ADSL modem. Packet after translation boundary of customer premises NAT box / firewall ISP router IP equals 198.60.42.12 port equals 3344 IP equals 10.0.0.1 port equals 5544 to internet packet before translation customer router and LAN figure 5 to 55. Placement and operation of a NAT box. So far, we have glossed over one tiny but crucial detail. When the reply comes back, for instance, from a web server, it is naturally addressed to 198.60.42.12. So how does the NAT box know which internal address to replace it with? Herein lies the problem with NAT. If there were a spare field in the IP header, that field could be used to keep track of who the real sender was, but only one bit is still unused. In principle, a new option could be created to hold the true source address, but doing so would require changing the IP code on all the machines on the entire internet to handle the new option. This is not a promising alternative for a quick fix. What actually happens is as follows. The NAT designers observed that most IP packets carry either TCP or UDP payloads. When we study TCP and UDP in Chapter 6, we will see that both of these have headers containing a source port and a destination port. Below we will just discuss TCP ports, but exactly the same story holds for UDP ports. The ports are 16-bit integers that indicate where the TCP connection begins and ends. These ports provide the field needed to make NAT work. When a process wants to establish a TCP connection with a remote process, it attaches itself to an unused TCP port on its own machine. This is called the source port and tells the TCP code where to send incoming packets belonging to this connection. The process also supplies a destination port to tell who to give the packets to on the remote side. Ports 0 to 1023 are reserved for well-known services. For example, port 80 is the port used by web servers, so remote clients can locate them. Each outgoing TCP message contains both a source port and a destination port. Together, these ports serve to identify the processes using the connection on both ends. An analogy may make the use of ports clearer. Imagine a company with a single main telephone number. When people call the main number, they reach an operator who asks which extension they want, and then puts them through to that extension. The main number is analogous to the customer's IP address and the extensions on both ends are analogous to the ports. Ports are effectively an extra 16 bits of addressing that identify which process gets which incoming packet. Using the source port field, we can solve our mapping problem. Whenever an outgoing packet enters the NAT box, the 10.xyz source address is replaced by the customer's true IP address. In addition, the TCP source port field is replaced by an index into the NAT box's 65,536 entry translation table. This table entry contains the original IP address and the original source port. Finally, both the IP and TCP header checksums are recomputed and inserted into the packet. It is necessary to replace the source port because connections from machines 10.0.0.1 and 10.0.0.2 of may both happen to use port 5000, for example, so the source port alone is not enough to identify the sending process. When a packet arrives at the NAT box from the ISP, the source port in the TCP header is extracted and used as an index into the NAT box's mapping table. From the entry located, the internal IP address and original TCP source port are extracted and inserted into the packet. Then, both the IP and TCP checksums are recomputed and inserted into the packet. The packet is then passed to the customer router for normal delivery using the 10.xyz address. Although this scheme sort of solves the problem, networking purists in the IP community have a tendency to regard it as an abomination on the face of the earth. Briefly summarized, here are some of the objections. First, NAT violates the architectural model of IP, which states that every IP address uniquely identifies a single machine worldwide. The whole software structure of the internet is built on this fact. With NAT, thousands of machines may, and do, use address 10.0.0.1. Second, NAT breaks the end-to-end connectivity model of the internet, which says that any host can send a packet to any other host at any time. Since the mapping in the NAT box is set up by outgoing packets, incoming packets cannot be accepted until after outgoing ones. In practice, this means that a home user with NAT can make TCP/IP connections to a remote web server, but a remote user cannot make connections to a game server on the home network. Special configuration or NAT traversal techniques are needed to support this kind of situation. Third, NAT changes the internet from a connectionless network to a peculiar kind of connection-oriented network. The problem is that the NAT box must maintain information, that is, the mapping, for each connection passing through it. Having the network maintain connection state is a property of connection-oriented networks, not connectionless ones. If the NAT box crashes and its mapping table is lost, all its TCP connections are destroyed. In the absence of NAT, a router can crash and restart with no long-term effect on TCP connections. The sending process just times out within a few seconds and retransmits all unacknowledged packets. With NAT, the internet becomes as vulnerable as a circuit-switched network. Fourth, NAT violates the most fundamental rule of protocol layering. Layer K may not make any assumptions about what layer K+1 has put into the payload field. This basic principle is there to keep the layers independent. If TCP is later upgraded to TCP2 with a different header layout, for instance, 32-bit ports, NAT will fail. The whole idea of layered protocols is to ensure that changes in one layer do not require changes in other layers. NAT destroys this independence. Fifth, processes on the internet are not required to use TCP or UDP. If a user on machine A decides to use some new transport protocol to talk to a user on machine B, for example, for a multimedia application, introduction of a NAT box will cause the application to fail because the NAT box will not be able to locate the TCP source port correctly. A sixth and related problem is that some applications use multiple TCP/IP connections or UDP ports in prescribed ways. For example, FTP, the standard file transfer protocol, inserts IP addresses in the body of packet for the receiver to extract and use. Since NAT knows nothing about these arrangements, it cannot rewrite the IP addresses or otherwise account for them. This lack of understanding means that FTP and other applications such as the H323 Internet Telephony Protocol, which we will study in Chapter 7, will fail in the presence of NAT unless special precautions are taken. It is often possible to patch NAT for these cases, but having to patch the code in the NAT box every time a new application comes along is not a good idea. Finally, since the TCP source port field is 16 bits, at most 65,536 machines can be mapped onto an IP address. Actually, the number is slightly less, because the first 4096 ports are reserved for special users. However, if multiple IP addresses are available, each one can handle up to 61,440 machines. A view of these and other problems with NAT is given in our FC 2993. Despite the issues, NAT is widely used in practice, especially for home and small business networks, as the only expedient technique to deal with the IP address shortage. It has become wrapped up with firewalls and privacy because it blocks unsolicited incoming packets by default. For this reason, it is unlikely to go away even when IPv6 is widely deployed. 5.6.3 IP version 6 IP has been in heavy use for decades. It has worked extremely well, as demonstrated by the exponential growth of the internet. Unfortunately, IP has become a victim of its own popularity. It is close to running out of addresses. Even with CIDR and NAT using addresses more sparingly, the last IPv4 addresses are expected to be assigned by ICANN before the end of 2012. This looming disaster was recognized almost 2 decades ago, and it sparked a great deal of discussion and controversy within the internet community about what to do about it. In this section, we will describe both the problem and several proposed solutions. The only long-term solution is to move to larger addresses. IPv6, IP version 6, is a replacement design that does just that. It uses 128-bit addresses. A shortage of these addresses is not likely anytime in the foreseeable future. However, IPv6 has proved very difficult to deploy. It is a different network layer protocol that does not really interwork with IPv4, despite many similarities. Also, companies and users are not really sure why they should want IPv6 in any case. The result is that IPv6 is deployed and used on only a tiny fraction of the internet. Estimates are 1%, despite having been an internet standard since 1998. The next several years will be an interesting time, as the few remaining IPv4 addresses are allocated. Will people start to auction off their IPv4 addresses on eBay? Will a black market in them spring up? Who knows? In addition to the address problems, other issues loom in the background. In its early years, the internet was largely used by universities, high-tech industries, and the US government, especially the Department of Defense. With the explosion of interest in the internet starting in the mid-1990s, it began to be used by a different group of people, often with different requirements. For one thing, numerous people with smartphones use it to keep in contact with their home bases. For another, with the impending convergence of the computer, communication, and entertainment industries, it may not be that long before every telephone and television set in the world is an internet node, resulting in a billion machines being used for audio and video on demand. Under these circumstances, it became apparent that IP had to evolve and become more flexible. Seeing these problems on the horizon, in 1990 IETF started work on a new version of IP, one that would never run out of addresses, would solve a variety of other problems, and be more flexible and efficient as well. Its major goals were: 1. Support billions of hosts, even with inefficient address allocation. 2. Reduce the size of the routing tables. 3. Simplify the protocol to allow routers to process packets faster. 4. Provide better security, authentication, and privacy. 5. Pay more attention to the type of service, particularly for real-time data. 6. Aid multicasting by allowing scopes to be specified. 7. Make it possible for a host to roam without changing its address. 8. Allow the protocol to evolve in the future. 9. Permit the old and new protocols to coexist for years. The design of IPv6 presented a major opportunity to improve all of the features in IPv4 that fall short of what is now wanted. To develop a protocol that met all these requirements, IETF issued a call for proposals and discussion in RFC 1550. 21 responses were initially received. By December 1992, 7 serious proposals were on the table. They ranged from making minor patches to IP, to throwing it out altogether and replacing it with a completely different protocol. One proposal was to run TCP over CLNP, the network layer protocol designed for OC. With its 160-bit addresses, CLNP would have provided enough address space forever, as it could give every molecule of water in the oceans enough addresses, roughly 25, to set up a small network. This choice would also have unified 2 major network layer protocols. However, many people felt that this would have been an admission that something in the OC world was actually done right, a statement considered politically incorrect in internet circles. CLNP was patterned closely on IP, so the two are not really that different. In fact, the protocol ultimately chosen differs from IP far more than CLNP does. Another strike against CLNP was its poor support for service types, something required to transmit multimedia efficiently. Three of the better proposals were published in IEEE Network: Deering, 1993, Francis, 1993, and Katz and Ford, 1993. After much discussion, revision, and jockeying for position, a modified combined version of the Deering and Francis proposals, by now called SIP, Simple Internet Protocol Plus, was selected and given the designation IPv6. IPv6 meets IETF's goals fairly well. It maintains the good features of IP, discards or de-emphasizes the bad ones, and adds new ones where needed. In general, IPv6 is not compatible with IPv4, but it is compatible with the other auxiliary internet protocols, including TCP, UDP, ICMP, IGMP, OSPF, BGP, and DNS, with small modifications being required to deal with longer addresses. The main features of IPv6 are discussed below. More information about it can be found in RFCs 2460 through 2466. First and foremost, IPv6 has longer addresses than IPv4. They are 128 bits long, which solves a problem that IPv6 set out to solve, providing an effectively unlimited supply of internet addresses. We will have more to say about addresses shortly. The second major improvement of IPv6 is the simplification of the header. It contains only 7 fields versus 13 in IPv4. This change allows routers to process packets faster and thus improves throughput and delay. We will discuss the header shortly too. The third major improvement is better support for options. This change was essential with the new header, because fields that previously were required are now optional, because they are not used so often. In addition, the way options are represented is different, making it simple for routers to skip over options not intended for them. This feature speeds up packet processing time. A fourth area in which IPv6 represents a big advances in security. IETF had its fill of newspaper stories about precocious 12-year-olds using their personal computers to break into banks and military bases all over the internet. There was a strong feeling that something had to be done to improve security. Authentication and privacy are key features of the new IP. These were later retrofitted to IPv4, however, so in the area of security the differences are not so great anymore. Finally, more attention has been paid to quality of service. Various half-hearted efforts to improve QoS have been made in the past, but now, with the growth of multimedia on the internet, the sense of urgency is greater. The main IPv6 header. The IPv6 header is shown in figure 5-56. The version field is always 6 for IPv6 and 4 for IPv4. During the transition period from IPv4, which has already taken more than a decade, routers will be able to examine this field to tell what kind of packet they have. As an aside, making this test wastes a few instructions in the critical path, given that the data link header usually indicates the network protocol for demultiplexing, so some routers may skip the check. For example, the Ethernet type field has different values to indicate an IPv4 or an IPv6 payload. The discussions between the do it right and make it fast camps will no doubt be lengthy and vigorous. 32 bits version diff services flow label payload length next header hop limit source address 16 bytes destination address 16 bytes figure 5-56. The IPv6 fixed header required. The differentiated services field, originally called traffic class, is used to distinguish the class of service for packets with different real-time delivery requirements. It is used with the differentiated service architecture for quality of service in the same manner as the field of the same name in the IPv4 packet. Also, the low order 2 bits are used to signal explicit congestion indications, again in the same way as with IPv4. The flow label field provides a way for a source and destination to mark groups of packets that have the same requirements and should be treated in the same way by the network, forming a pseudo connection. For example, a stream of packets from one process on a certain source host to a process on a specific destination host might have stringent delay requirements and thus need reserved bandwidth. The flow can be set up in advance and given an identifier. When a packet with a non-zero flow label shows up, All the routers can look it up in internal tables to see what kind of special treatment it requires. In effect, flows are an attempt to have it both ways, the flexibility of a datagram network and the guarantees of a virtual circuit network. Each flow for quality of service purposes is designated by the source address, destination address, and flow number. This design means that up to 220 flows may be active at the same time between a given pair of IP addresses. It also means that, even if two flows coming from different hosts, but with the same flow label pass through the same router, the router will be able to tell them apart using the source and destination addresses. It is expected that flow labels will be chosen randomly, rather than assigned sequentially starting at 1, so routers are expected to hash them. The payload length field tells how many bytes follow the 40-byte header of figure 5 to 56. The name was changed from the IPv4 total length field because the meaning was changed slightly. The 40 header bytes are no longer counted as part of the length, as they used to be. This change means the payload can now be 65,535 bytes instead of a mere 65,515 bytes. The next header field lets the cat out of the bag. The reason the header could be simplified is that there can be additional, optional, extension headers. This field tells which of the, currently, 6 extension headers, if any, follow this one. If this header is the last IP header, the next header field tells which transport protocol handler, for instance, TCP, UDP, to pass the packet to. The hop limit field is used to keep packets from living forever. It is, in practice, the same as the time to live field in IPv4, namely, a field that is decremented on each hop. In theory, in IPv4 it was a time in seconds, but no router used it that way, so the name was changed to reflect the way it is actually used. Next come the source address and destination address fields. Deering's original proposal, SIP, used 8-byte addresses, but during the review process many people felt that with 8-byte addresses IPv6 would run out of addresses within a few decades, whereas with 16-byte addresses it would never run out. Other people argued that 16 bytes was overkill, whereas still others favored using 20-byte addresses to be compatible with the OC datagram protocol. Still another faction wanted variable-sized addresses. After much debate and more than a few words unprintable in an academic textbook, it was decided that fixed-length 16-byte addresses were the best compromise. A new notation has been devised for writing 16-byte addresses. They are written as 8 groups of 4 hexadecimal digits with colons between the groups, like this. 8000 colon 0000 colon 0000 colon 0000 colon 0123 colon 4567 colon 89 AB CDF. Since many addresses will have many zeros inside them, 3 optimizations have been authorized. First, leading zeros within a group can be omitted, so 0123 can be written as 123. Second, one or more groups of 16 0 bits can be replaced by a pair of colons. Thus, the above address now becomes 8000 colon 123 colon 4567 colon 89 AB CDF. Finally, IPv4 addresses can be written as a pair of colons and an old dotted decimal number, for example, colon 192.31.20.46 perhaps. It is unnecessary to be so explicit about it, but there are a lot of 16-byte addresses. Specifically, there are 2128 of them, which is approximately 3x 1038. If the entire Earth, land, and water were covered with computers, IPv6 would allow 7x 1023 IP addresses per square meter. Students of chemistry will notice that this number is larger than Avogadro's number. While it was not the intention to give every molecule on the surface of the Earth its own IP address, we are not that far off. In practice, the address space will not be used efficiently, just as the telephone number address space is not. The area code for Manhattan, 212, is nearly full, but that for Wyoming, 307, is nearly empty. In RFC 3194, Durand and Hutima calculated that, using the allocation of telephone numbers as a guide, even in the most pessimistic scenario there will still be well over 1000 IP addresses per square meter of the entire Earth's surface, land, and water. In any likely scenario, there will be trillions of them per square meter. In short, it seems unlikely that we will run out in the foreseeable future. It is instructive to compare the IPv4 header, figure 5 to 46, with the IPv6 header, figure 5 to 56, to see what has been left out in IPv6. The IHL field is gone, because the IPv6 header has a fixed length. The protocol field was taken out, because the next header field tells what follows the last IP header, for instance, a UDP or TCP segment. All the fields relating to fragmentation were removed, because IPv6 takes a different approach to fragmentation. To start with, all IPv6 conformant hosts are expected to dynamically determine the packet size to use. They do this using the path MTU discovery procedure we described in Secretary 5.5.5. In brief, when a host sends an IPv6 packet that is too large, instead of fragmenting it, the router that is unable to forward it drops the packet and sends an error message back to the sending host. This message tells the host to break up all future packets to that destination. Having the host send packets that are the right size in the first place is ultimately much more efficient than having the routers fragment them on the fly. Also, the minimum size packet that routers must be able to forward has been raised from 576 to 1280 bytes to allow 1024 bytes of data and many headers. Finally, the checksum field is gone, because calculating it greatly reduces performance. With the reliable networks now used, combined with the fact that the data link layer and transport layers normally have their own checksums, the value of yet another checksum was deemed not worth the performance price it extracted. Removing all these features has resulted in a lean and mean network layer protocol. Thus, the goal of IPv6, a fast, yet flexible, protocol with plenty of address space, is met by this design. Extension headers. Some of the missing IPv4 fields are occasionally still needed, so IPv6 introduces the concept of optional extension headers. These headers can be supplied to provide extra information, but encoded in an efficient way. 6 kinds of extension headers are defined at present, as listed in figure 5 to 57. Each one is optional, but if more than one is present they must appear directly after the fixed header, and preferably in the order listed. Extension header description: hop by hop options, miscellaneous information for routers, destination options, additional information for the destination routing, loose list of routers to visit, fragmentation management of datagram fragments, authentication verification of the sender's identity, encrypted security, payload information about the encrypted contents, figure 5 to 57. IPv6 extension headers. Some of the headers have a fixed format, others contain a variable number of variable length options. For these, each item is encoded as a type, length, value, tuple. The type is a 1 byte field telling which option this is. The type values have been chosen so that the first 2 bits tell routers that do not know how to process the option what to do. The choices are: skip the option, discard the packet, and send back an ICMP packet, and discard the packet, but do not send ICMP packets for multicast addresses, to prevent one bad multicast packet from generating millions of ICMP reports. The length is also a 1 byte field. It tells how long the value is, 0 to 255 bytes. The value is any information required, up to 255 bytes. The hop by hop header is used for information that all routers along the path must examine. So far, one option has been defined: support of datagrams exceeding 64 KB. The format of this header is shown in figure 5 to 58. When it is used, the payload length field in the fixed header is set to 0. Next header: jumbo payload length 0, 194, for figure 5 to 58. The hop by hop extension header for large datagrams, jumbograms. As with all extension headers, this one starts with a byte telling what kind of header comes next. This byte is followed by one telling how long the hop by hop header is in bytes, excluding the first 8 bytes, which are mandatory. All extensions begin this way. The next 2 bytes indicate that this option defines the datagram size, code 194, and that the size is a 4-byte number. The last 4 bytes give the size of the datagram. Sizes less than 65,536 bytes are not permitted and will result in the first router discarding the packet and sending back an ICMP error message. Datagrams using this header extension are called jumbograms. The use of jumbograms is important for supercomputer applications that must transfer gigabytes of data efficiently across the internet. The destination options header is intended for fields that need only be interpreted at the destination host. In the initial version of IPv6, the only options defined are null options for padding this header out to a multiple of 8 bytes, so initially it will not be used. It was included to make sure that new routing and host software can handle it in case someone thinks of a destination option someday. The routing header lists one or more routers that must be visited on the way to the destination. It is very similar to the IPv4 loose source routing in that all addresses listed must be visited in order, but other routers not listed may be visited in between. The format of the routing header is shown in figure 5-59. Next, header extension length routing type segments left type specific data figure 5-59. The extension header for routing. The first 4 bytes of the routing extension header contain 4 1-byte integers. The next header and header extension length fields were described above. The routing type field gives the format of the rest of the header. Type 0 says that a reserved 32-bit word follows the first word, followed by some number of IPv6 addresses. Other types may be invented in the future, as needed. Finally, the segments left field keeps track of how many of the addresses in the list have not yet been visited. It is decremented every time one is visited. When it hits 0, the packet is on its own with no more guidance about what route to follow. Usually, at this point it is so close to the destination that the best route is obvious. The fragment header deals with fragmentation similarly to the way IPv4 does. The header holds the datagram identifier, fragment number, and a bit telling whether more fragments will follow. In IPv6, unlike in IPv4, only the source host can fragment a packet. Routers along the way may not do this. This change is a major philosophical break with the original IP, but in keeping with current practice for IPv4. Plus, it simplifies the router's work and makes routing go faster. As mentioned above, if a router is confronted with a packet that is too big, it discards the packet and sends an ICMP error packet back to the source. This information allows the source host to fragment the packet into smaller pieces using this header and try again. The authentication header provides a mechanism by which the receiver of a packet can be sure of who sent it. The encrypted security payload makes it possible to encrypt the contents of a packet so that only the intended recipient can read it. These headers use the cryptographic techniques that we will describe in chapter 8 to accomplish their missions. Controversies given the open design process and the strongly held opinions of many of the people involved, it should come as no surprise that many choices made for IPv6 were highly controversial, to say the least. We will summarize a few of these briefly below. For all the gory details, see the RFCs. We have already mentioned the argument about the address length. The result was a compromise. 16-byte fixed length addresses. Another fight developed over the length of the hop limit field. One camp felt strongly that limiting the maximum number of hops to 255, implicit in using an 8-bit field, was a gross mistake. After all, paths of 32 hops are common now, and 10 years from now much longer paths may be common. These people argued that using a huge address size was far-sighted, but using a tiny hop count was short-sighted. In their view, the greatest sin a computer scientist can commit is to provide too few bits somewhere. The response was that arguments could be made to increase every field, leading to a bloated header. Also, the function of the hop limit field is to keep packets from wandering around for too long a time, and 65,535 hops is far too long. Finally, as the internet grows, more and more long distance links will be built, making it possible to get from any country to any other country in half a dozen hops at most. If it takes more than 125 hops to get from the source and the destination to their respective international gateways, something is wrong with the national backbones. The 8-bitters won this one. Another hot potato was the maximum packet size. The supercomputer community wanted packets in excess of 64 KB. When a supercomputer gets started transferring, it really means business and does not want to be interrupted every 64 KB. The argument against large packets is that if a 1 megabyte packet hits a 1.5 Mbps/1 line, that packet will tie the line up for over 5 seconds, producing a very noticeable delay for interactive users sharing the line. A compromise was reached here. Normal packets are limited to 64 KB, but the hop-by-hop extension header can be used to permit jumbograms. A third hot topic was removing the IPv4 checksum. Some people likened this move to removing the brakes from a car. Doing so makes the car lighter, so it can go faster, but if an unexpected event happens, you have a problem. The argument against checksums was that any application that really cares about data integrity has to have a transport layer checksum anyway, so having another one in IP, in addition to the data link layer checksum, is overkill. Furthermore, experience showed that computing the IP checksum was a major expense in IPv4. The anti-checksum camp won this one, and IPv6 does not have a checksum. Mobile hosts were also a point of contention. If a portable computer flies halfway around the world, can it continue operating there with the same IPv6 address, or does it have to use a scheme with home agents? Some people wanted to build explicit support for mobile hosts into IPv6. That effort failed when no consensus could be found for any specific proposal. Probably the biggest battle was about security. Everyone agreed it was essential. The war was about where to put it and how. First, where. The argument for putting it in the network layer is that it then becomes a standard service that all applications can use without any advanced planning. The argument against it is that really secure applications generally want nothing less than end-to-end encryption, where the source application does the encryption and the destination application undoes it. With anything less, the user is at the mercy of potentially buggy network layer implementations over which he has no control. The response to this argument is that these applications can just refrain from using the IP security features and do the job themselves. The rejoinder to that is that the people who do not trust the network to do it right do not want to pay the price of slow bulky IP implementations that have this capability, even if it is disabled. Another aspect of where to put security relates to the fact that many, but not all, countries have very stringent export laws concerning cryptography. Some, notably France and Iraq, also restrict its use domestically so that people cannot have secrets from the government. As a result, any IP implementation that used a cryptographic system strong enough to be of much value could not be exported from the United States and many other countries to customers worldwide. Having to maintain two sets of software, one for domestic use and one for export, is something most computer vendors vigorously oppose. One point on which there was no controversy is that no one expects the IPv4 internet to be turned off on a Sunday evening and come back up as an IPv6 internet Monday morning. Instead, isolated islands of IPv6 will be converted, initially communicating via tunnels, as we showed in Secretary 5.5.3. As the IPv6 islands grow, they will merge into bigger islands. Eventually, all the islands will merge, and the internet will be fully converted. At least, that was the plan. Deployment has proved the Achilles heel of IPv6. It remains little used, even though all major operating systems fully support it. Most deployments are new situations in which a network operator, for example, a mobile phone operator, needs a large number of IP addresses. Many strategies have been defined to help ease the transition. Among them are ways to automatically configure the tunnels that carry IPv6 over the IPv4 internet, and ways for hosts to automatically find the tunnel endpoints. Dual stack hosts have an IPv4 and an IPv6 implementation so that they can select which protocol to use depending on the destination of the packet. These strategies will streamline the substantial deployment that seems inevitable when IPv4 addresses are exhausted. For more information about IPv6, see Davis, 2008, 5.6.4 Internet Control Protocols. In addition to IP, which is used for data transfer, the internet has several companion control protocols that are used in the network layer. They include ICMP, ARP, and DHCP. In this section, we will look at each of these in turn, describing the versions that correspond to IPv4 because they are the protocols that are in common use. ICMP and DHCP have similar versions for IPv6. The equivalent of ARP is called NDP, Neighbor Discovery Protocol, for IPv6. IMCP, the Internet Control Message Protocol. The operation of the internet is monitored closely by the routers. When something unexpected occurs during packet processing at a router, the event is reported to the sender by the ICMP, Internet Control Message Protocol. ICMP is also used to test the internet. About a dozen types of ICMP messages are defined. Each ICMP message type is carried encapsulated in an IP packet. The most important ones are listed in Figure 5 to 60. The destination unreachable message is used when the router cannot locate the destination, or when a packet with the DF bit cannot be delivered because a small pocket network stands in the way. Message type description: destination unreachable packet could not be delivered. Time exceeded. Time till if field hit 0. Parameter problem: invalid header field. Source quench choke packet redirect. Teacher router about geography. Echo and echo reply check if a machine is alive. Timestamp request / reply same as echo but with timestamp. Router advertisement / solicitation. Find a nearby router. Figure 5 to 60. The principal ICMP message types. The time exceeded message is sent when a packet is dropped because its TTL, time to live, counter has reached 0. This event is a symptom that packets are looping or that the counter values are being set too low. One clever use of this error message is a traceroute utility that was developed by Van Jacobson in 1987. Traceroute finds the routers along the path from the host to a destination IP address. It finds this information without any kind of privileged network support. The method is simply to send a sequence of packets to the destination, first with a TTL of 1, then a TTL of 2, 3, and so on. The counters on these packets will reach 0 at successive routers along the path. These routers will each obediently send a time exceeded message back to the host. From those messages, the host can determine the IP addresses of the routers along the path, as well as keep statistics and timings on parts of the path. It is not what the time exceeded message was intended for, but it is perhaps the most useful network debugging tool of all time. The parameter problem message indicates that an illegal value has been detected in a header field. This problem indicates a bug in the sending host's IP software, or possibly in the software of a router transited. The source quench message was long ago used to throttle hosts that were sending too many packets. When a host received this message, it was expected to slow down. It is rarely used anymore, because when congestion occurs, these packets tend to add more fuel to the fire, and it is unclear how to respond to them. Congestion control in the internet is now done, largely by taking action in the transport layer, using packet losses as a congestion signal. We will study it in detail in chapter 6. The redirect message is used when a router notices that a packet seems to be routed incorrectly. It is used by the router to tell the sending host to update to a better route. The echo and echo reply messages are sent by hosts to see if a given destination is reachable and currently alive. Upon receiving the echo message, the destination is expected to send back an echo reply message. These messages are used in the ping utility that checks if a host is up and on the internet. The timestamp request and timestamp reply messages are similar, except that the arrival time of the message and the departure time of the reply are recorded in the reply. This facility can be used to measure network performance. The router advertisement and router solicitation messages are used to let hosts find nearby routers. A host needs to learn the IP address of at least one router to be able to send packets off the local network. In addition to these messages, others have been defined. The online list is now kept at www.ina.org/assignments/icomp parameters. The address resolution protocol, although every machine on the internet has one or more IP addresses, these addresses are not sufficient for sending packets. Data link layer NICs, network interface cards, such as Ethernet cards, do not understand internet addresses. In the case of Ethernet, every NIC ever manufactured comes equipped with a unique 48-bit Ethernet address. Manufacturers of Ethernet NICs request a block of Ethernet addresses from IEEE to ensure that no two NICs have the same address, to avoid conflicts should the two NICs ever appear on the same LAN. The NICs send and receive frames based on 48-bit Ethernet addresses. They know nothing at all about 32-bit IP addresses. The question now arises, how do IP addresses get mapped onto data link layer addresses, such as Ethernet? To explain how this works, let us use the example of figure 5-61, in which a small university with 2/24 networks is illustrated. One network, CS, is a switched Ethernet in the computer science department. It has the prefix 192.32.65.0/24. The other LAN, EE, also switched Ethernet, is in electrical engineering and has the prefix 192.32.63.0/24. The two LANs are connected by an IP router. Each machine on an Ethernet and each interface on the router has a unique Ethernet address, labeled E1 through E6, and a unique IP address on the CS or EE network. Let us start out by seeing how a user on host 1 sends a packet to a user on host 2 on the CS network. Let us assume the sender knows the name of the intended receiver, possibly something like eagle.cs.uni.edu. The first step is to find the IP address for host 2. This lookup is performed by DNS, which we will study in chapter 7. For the moment, we will just assume that DNS returns the IP address for host 2, 192.32.65.5. The upper layer software on host 1 now builds a packet with 192.32.65.5 in the destination address field and gives it to the IP software to transmit. The IP software can look at the address and see that the destination is on the CS network, that is, its own network. However, it still needs some way to find the destination's Ethernet address to send the frame. One solution is to have a configuration file somewhere in the system that maps IP addresses onto Ethernet addresses. While IP1 equals 192.32.65.72 E1 E5 E4 E6 192.32.65.1 IP2 equals 192.32.65.5. 192.32.63.1 IP4 equals 192.32.63.8 IP3 equals 192.32.63.3 EE network. 192.32.63.0/24 outer host 1 host 2 host 3 host 4 frame source IP source Eth. Destination IP destination Eth. Host 1 to 2 on CSNet IP1 E1 IP2 E2 host 1 to 4 on CSNet IP1 E1 IP4 E3 host 1 to 4 on EENet IP1 E4 IP4 E6 figure 5-61. Two switched Ethernet LANs joined by a router. This solution is certainly possible for organizations with thousands of machines. Keeping all these files up to date is an error-prone, time-consuming job. A better solution is for host 1 to output a broadcast packet onto the Ethernet asking who owns IP address 192.32.65.5. The broadcast will arrive at every machine on the CS Ethernet, and each one will check its IP address. Host 2 alone will respond with its Ethernet address, E2. In this way host 1 learns that IP address 192.32.65.5 is on the host with Ethernet address E2. The protocol used for asking this question and getting the reply is called ARP, Address Resolution Protocol. Almost every machine on the internet runs it. ARP is defined in RFC 826. The advantage of using ARP over configuration files is the simplicity. The system manager does not have to do much except assign each machine an IP address and decide about subnet masks. ARP does the rest. At this point, the IP software on host 1 builds an Ethernet frame addressed to E2, puts the IP packet addressed to 192.32.65.5 in the payload field and dumps it onto the Ethernet. The IP and Ethernet addresses of this packet are given in figure 5 to 61. The Ethernet NIC of host 2 detects this frame, recognizes it as a frame for itself, scoops it up, and causes an interrupt. The Ethernet driver extracts the IP packet from the payload and passes it to the IP software, which sees that it is correctly addressed and processes it. Various optimizations are possible to make ARP work more efficiently. To start with, once a machine has run ARP, it caches the result in case it needs to contact the same machine shortly. Next time it will find the mapping in its own cache, thus eliminating the need for a second broadcast. In many cases, host 2 will need to send back a reply, forcing it to run ARP to determine the sender's Ethernet address. This ARP broadcast can be avoided by having host 1 include its IP to Ethernet mapping in the ARP packet. When the ARP broadcast arrives at host 2, the pair 192.32.65.7 E1 is entered into host 2's ARP cache. In fact, all machines on the Ethernet can enter this mapping into their ARP caches. To allow mappings to change, for example, when a host is configured to use a new IP address but keeps its old Ethernet address, entries in the ARP cache should time out after a few minutes. A clever way to help keep the cached information current and to optimize performance is to have every machine broadcast its mapping when it is configured. This broadcast is generally done in the form of an ARP looking for its own IP address. There should not be a response, but a side effect of the broadcast is to make or update an entry in everyone's ARP cache. This is known as a gratuitous ARP. If a response does unexpectedly arrive, two machines have been assigned the same IP address. The error must be resolved by the network manager before both machines can use the network. Now let us look at figure 5 to 61 again, only this time assume that host 1 wants to send a packet to host 4, 192.32.63.8 on the EE network. Host 1 will see that the destination IP address is not on the CS network. It knows to send all such off-network traffic to the router, which is also known as the default gateway. By convention, the default gateway is the lowest address on the network, 198.31.65.1. To send a frame to the router, host 1 must still know the Ethernet address of the router interface on the CS network. It discovers this by sending an ARP broadcast for 198.31.65.1, from which it learns E3. It then sends the frame. The same lookup mechanisms are used to send a packet from one router to the next over a sequence of routers in an internet path. When the Ethernet NIC of the router gets this frame, it gives the packet to the IP software. It knows from the network masks that the packet should be sent onto the EE network, where it will reach host 4. If the router does not know the Ethernet address for host 4, then it will use ARP again. The table in figure 5 to 61 lists the source and destination Ethernet and IP addresses that are present in the frames as observed on the CS and EE networks. Observe that the Ethernet addresses change with the frame on each network, while the IP addresses remain constant, because they indicate the endpoints across all of the interconnected networks. It is also possible to send a packet from host 1 to host 4 without host 1 knowing that host 4 is on a different network. The solution is to have the router answer ARPs on the CS network for host 4 and give its Ethernet address, E3, as the response. It is not possible to have host 4 apply directly because it will not see the ARP request, as routers do not forward Ethernet level broadcasts. The router will then receive frames sent to 192.32.63.8 and forward them onto the EE network. This solution is called proxy ARP. It is used in special cases in which a host wants to appear on a network, even though it actually resides on another network. A common situation, for example, is a mobile computer that wants some other node to pick up packets for it when it is not on its home network. DHCP, the Dynamic Host Configuration Protocol ARP, as well as other internet protocols, makes the assumption that hosts are configured with some basic information, such as their own IP addresses. How do hosts get this information? It is possible to manually configure each computer, but that is tedious and error-prone. There is a better way, and it is called DHCP, Dynamic Host Configuration Protocol. With DHCP, every network must have a DHCP server that is responsible for configuration. When a computer is started, it has a built-in Ethernet or other link layer address embedded in the NIC, but no IP address. Much like ARP, the computer broadcasts a request for an IP address on its network. It does this by using a DHCP discover packet. This packet must reach the DHCP server. If that server is not directly attached to the network, the router will be configured to receive DHCP broadcasts and relay them to the DHCP server, wherever it is located. When the server receives the request, it allocates a free IP address and sends it to the host in a DHCP offer packet, which again may be relayed via the router. To be able to do this work even when hosts do not have IP addresses, the server identifies a host using its Ethernet address, which is carried in the DHCP discover packet. An issue that arises with automatic assignment of IP addresses from a pool is for how long an IP address should be allocated. If a host leaves the network and does not return its IP address to the DHCP server, that address will be permanently lost. After a period of time, many addresses may be lost. To prevent that from happening, IP address assignment may be for a fixed period of time, a technique called leasing. Just before the lease expires, the host must ask for a DHCP renewal. If it fails to make a request or the request is denied, the host may no longer use the IP address it was given earlier. DHCP is described in RFCs 2131 and 2132. It is widely used in the internet to configure all sorts of parameters in addition to providing hosts with IP addresses. As well as in business and home networks, DHCP is used by ISPs to set the parameters of devices over the internet access link, so that customers do not need to phone their ISPs to get this information. Common examples of the information that is configured include the network mask, the IP address of the default gateway, and the IP addresses of DNS and time servers. DHCP has largely replaced earlier protocols called DRAP and BOOTP with more limited functionality 5.6.5 label switching and MPLS so far. On our tour of the network layer of the internet, we have focused exclusively on packets as datagrams that are forwarded by IP routers. There is also another kind of technology that is starting to be widely used, especially by ISPs, in order to move internet traffic across their networks. This technology is called MPLS, multi-protocol label switching, and it is perilously close to circuit switching. Despite the fact that many people in the internet community have an intense dislike for connection-oriented networking, the idea seems to keep coming back. As Yogi Berra once put it is like déjà vu all over again. However, there are essential differences between the way the internet handles route construction and the way connection-oriented networks do it, so the technique is certainly not traditional circuit switching. MPLS adds a label in front of each packet, and forwarding is based on the label rather than on the destination address. Making the label an index into an internal table makes finding the correct output line just a matter of table lookup. Using this technique, forwarding can be done very quickly. This advantage was the original motivation behind MPLS, which began as proprietary technology known by various names including tag switching. Eventually, IETF began to standardize the idea. It is described in RFC 3031 and many other RFCs. The main benefits over time have come to be routing that is flexible and forwarding that is suited to quality of service as well as fast. The first question to ask is, where does the label go? Since IP packets were not designed for virtual circuits, there is no field available for virtual circuit numbers within the IP header. For this reason, a new MPLS header had to be added in front of the IP header. On a router to router line using PPP as the framing protocol, the frame format, including the PPP, MPLS, IP, and TCP headers, is as shown in figure 5-62. PPP MPLS IP label co-SSTTL bits 20 headers 3, 1, 8 TCP user data CRC figure 5-62. Transmitting a TCP segment using IP, MPLS, and PPP. The generic MPLS header is 4 bytes long and has 4 fields. Most important is the label field, which holds the index. The co-S field indicates the class of service. The S field relates to stacking multiple labels, which is discussed below. The TTL field indicates how many more times the packet may be forwarded. It is decremented at each router, and if it hits 0, the packet is discarded. This feature prevents infinite looping in the case of routing instability. MPLS falls between the IP network layer protocol and the PPP link layer protocol. It is not really a layer 3 protocol because it depends on IP or other network layer addresses to set up label paths. It is not really a layer 2 protocol either because it forwards packets across multiple hops, not a single link. For this reason, MPLS is sometimes described as a layer 2.5 protocol. It is an illustration that real protocols do not always fit neatly into our ideal layered protocol model. On the brighter side, because the MPLS headers are not part of the network layer packet or the data link layer frame, MPLS is to a large extent independent of both layers. Among other things, this property means it is possible to build MPLS switches that can forward both IP packets and non-IP packets, depending on what shows up. This feature is where the multiprotocol in the name MPLS came from. MPLS can also carry IP packets over non-IP networks. When an MPLS enhanced packet arrives at a LSR label switched router, the label is used as an index into a table to determine the outgoing line to use and also the new label to use. This label swapping is used in all virtual circuit networks. Labels have only local significance and 2 different routers can feed unrelated packets with the same label into another router for transmission on the same outgoing line. To be distinguishable at the other end, labels have to be remapped at every hop. We saw this mechanism in action in figure 523. MPLS uses the same technique. As an aside, some people distinguish between forwarding and switching. Forwarding is the process of finding the best match for a destination address in a table to decide where to send packets. An example is the longest matching prefix algorithm used for IP forwarding. In contrast, switching uses a label taken from the packet as an index into a forwarding table. It is simpler and faster. These definitions are far from universal, however. Since most hosts and routers do not understand MPLS, we should also ask when and how the labels are attached to packets. This happens when an IP packet reaches the edge of an MPLS network. The layer label edge router inspects the destination IP address and other fields to see which MPLS path the packet should follow and puts the right label on the front of the packet. Within the MPLS network, this label is used to forward the packet. At the other edge of the MPLS network, the label has served its purpose and is removed, revealing the IP packet again for the next network. This process is shown in figure 5-63. One difference from traditional virtual circuits is a level of aggregation. It is certainly possible for each flow to have its own set of labels through the MPLS network. However, it is more common for routers to group multiple flows that end at a particular router or LAN and use a single label for them. The flows that are grouped together under a single label are said to belong to the same FEC, forwarding equivalence class. This class covers not only where the packets are going, but also their service class, in the differentiated services sense, because all the packets are treated the same way for forwarding purposes. With traditional virtual circuit routing, it is not possible to group several distinct paths with different endpoints onto the same virtual circuit identifier, because there would be no way to distinguish them at the final destination. With MPLS, switching on label only label switch router IP label edge router add label remove label to next network label figure 5 to 63. Forwarding an IP packet through an MPLS network, the packets still contain their final destination address in addition to the label. At the end of the labeled route, the label header can be removed and forwarding can continue the usual way using the network layer destination address. Actually, MPLS goes even further. It can operate at multiple levels at once by adding more than one label to the front of a packet. For example, suppose that there are many packets that already have different labels. Because we want to treat the packets differently somewhere in the network that should follow a common path to some destination. Instead of setting up many label switching paths, one for each of the different labels, we can set up a single path. When the already labeled packets reach the start of this path, another label is added to the front. This is called a stack of labels. The outermost label guides the packets along the path. It is removed at the end of the path, and the labels revealed, if any, are used to forward the packet further. The S bit in figure 5 to 62 allows a router removing a label to know if there are any additional labels left. It is set to 1 for the bottom label and 0 for all the other labels. The final question we will ask is how the label forwarding tables are set up so that packets follow them. This is one area of major difference between MPLS and conventional virtual circuit designs. In traditional virtual circuit networks, when a user wants to establish a connection, a setup packet is launched into the network to create the path and make the forwarding table entries. MPLS does not involve users in the setup phase. Requiring users to do anything other than send a datagram would break too much existing internet software. Instead, the forwarding information is set up by protocols that are a combination of routing protocols and connection setup protocols. These control protocols are cleanly separated from label forwarding, which allows multiple, different control protocols to be used. One of the variants works like this. When a router is booted, it checks to see which routes it is the final destination for instance, which prefixes belong to its interfaces. It then creates one or more FECs for them, allocates a label for each one, and passes the labels to its neighbors. They, in turn, enter the labels in their forwarding tables and send new labels to their neighbors until all the routers have acquired the path. Resources can also be reserved as the path is constructed to guarantee an appropriate quality of service. Other variants can set up different paths, such as traffic engineering paths that take unused capacity into account and create paths on demand to support service offerings such as quality of service. Although the basic ideas behind MPLS are straightforward, the details are complicated, with many variations and use cases that are being actively developed. For more information, see Davian Farrell, 2008, and Davian Rector, 2000. 5.6.60 SPF an interior gateway routing protocol. We have now finished our study of how packets are forwarded in the internet. It is time to move on to the next topic, routing in the internet. As we mentioned earlier, the internet is made up of a large number of independent networks or ASs, autonomous systems, that are operated by different organizations, usually a company, university, or ISP. Inside of its own network, an organization can use its own algorithm for internal routing, or intradomain routing, as it is more commonly known. Nevertheless, there are only a handful of standard protocols that are popular. In this section, we will study the problem of intradomain routing and look at the OSPF protocol that is widely used in practice. An intradomain routing protocol is also called an interior gateway protocol. In the next section, we will study the problem of routing between independently operated networks, or interdomain routing. For that case, all networks must use the same interdomain routing protocol or exterior gateway protocol. The protocol that is used in the internet is BGP, Border Gateway Protocol. Early intradomain routing protocols used a distance vector design based on the distributed Bellman-Ford algorithm inherited from the ARPANET. RIP, Routing Information Protocol, is the main example that is used to this day. It works well in small systems, but less well as networks get larger. It also suffers from the count to infinity problem and generally slow convergence. The ARPANET switched over to a link state protocol in May 1979 because of these problems, and in 1988 IETF began work on a link state protocol for intradomain routing. That protocol, called OSPF, Open Shortest Path First, became a standard in 1990. It drew on a protocol called ISIS, Intermediate System to Intermediate System, which became an ISO standard. Because of their shared heritage, the two protocols are much more alike than different. For the complete story, see RFC 2328. They are the dominant intradomain routing protocols, and most router vendors now support both of them. OSPF is more widely used in company networks, and ISIS is more widely used in ISP networks. Of the two, we will give a sketch of how OSPF works. Given the long experience with other routing protocols, the group designing OSPF had a long list of requirements that had to be met. First, the algorithm had to be published in the open literature, hence the O in OSPF. A proprietary solution owned by one company would not do. Second, the new protocol had to support a variety of distance metrics, including physical distance, delay, and so on. Third, it had to be a dynamic algorithm, one that adapted to changes in the topology automatically and quickly. Fourth, and new for OSPF, it had to support routing based on type of service. The new protocol had to be able to route real-time traffic one way and other traffic a different way. At the time, IP had a type of service field, but no existing routing protocol used it. This field was included in OSPF, but still nobody used it, and it was eventually removed. Perhaps this requirement was ahead of its time, as it preceded IETF's work on differentiated services, which has rejuvenated classes of service. Fifth, and related to the above, OSPF had to do load balancing, splitting the load over multiple lines. Most previous protocols sent all packets over a single best route, even if there were two routes that were equally good. The other route was not used at all. In many cases, splitting the load over multiple routes gives better performance. Sixth, support for hierarchical systems was needed. By 1988, some networks had grown so large that no router could be expected to know the entire topology. OSPF had to be designed so that no router would have to. Seventh, some modicum of security was required to prevent fun-loving students from spoofing routers by sending them false routing information. Finally, provision was needed for dealing with routers that were connected to the internet via a tunnel. Previous protocols did not handle this well. OSPF supports both point-to-point links, for instance, SONET, and broadcast networks, for instance, most LANs. Actually, it is able to support networks with multiple routers, each of which can communicate directly with the others, called multi-access networks, even if they do not have broadcast capability. Earlier protocols did not handle this case well. An example of an autonomous system network is given in Figure 5-64. Hosts are omitted because they do not generally play a role in OSPF, while routers and networks, which may contain hosts, do. Most of the routers in Figure 5-64 are connected to other routers by point-to-point links and to networks to reach the hosts on those networks. However, routers R3, R4, and R5 are connected by a broadcast LAN such as switched Ethernet. OSPF operates by abstracting the collection of actual networks, routers, and links into a directed graph in which each arc is assigned a weight, distance, delay, etc. A point-to-point connection between two routers is represented by a pair of arcs, one in each direction. Their weights may be different. A broadcast network is represented by a node for the network itself, plus a node for each router. The arcs from that network node to the routers have weight 0. They are important nonetheless, as without them there is no path through the network. Other networks, which have only hosts, have only an arc reaching them, and not one returning. This structure gives routes to hosts, but not through them. LAN 1 LAN 2 LAN 4 LAN 3 R2 R4 R1 R3 R5 R4 R2 R1 R3 R5 LAN 1 LAN 2 LAN 1 LAN 4 B 0 0 3 0 3 4 5 8 7 5 5 4 4 1 1 Figure 5 to 64. An autonomous system. B. A graph representation of Figure 5 to 64. B. Shows the graph representation of the network of Figure 5 to 64. What OSPF fundamentally does is represent the actual network as a graph like this, and then use the link state method to have every router compute the shortest path from itself to all other nodes. Multiple paths may be found that are equally short. In this case, OSPF remembers the set of shortest paths, and during packet forwarding, traffic is split across them. This helps to balance load. It is called DCMP, equal cost multipath. Many of the asses in the internet are themselves large and non-trivial to manage. To work at this scale, OSPF allows NAS to be divided into numbered areas, where an area is a network or a set of contiguous networks. Areas do not overlap, but need not be exhaustive. That is, some routers may belong to no area. Routers that lie wholly within an area are called internal routers. An area is a generalization of an individual network. Outside an area, its destinations are visible, but not its topology. This characteristic helps routing to scale. Every AS has a backbone area, called Area 0. The routers in this area are called backbone routers. All areas are connected to the backbone, possibly by tunnels, so it is possible to go from any area in the AS to any other area in the AS via the backbone. A tunnel is represented in the graph as just another arc with a cost. As with other areas, the topology of the backbone is not visible outside the backbone. Each router that is connected to two or more areas is called an area border router. It must also be part of the backbone. The job of an area border router is to summarize the destinations in one area and to inject this summary into the other areas to which it is connected. This summary includes cost information, but not all the details of the topology within an area. Passing cost information allows hosts in other areas to find the best area border router to use to enter an area. Not passing topology information reduces traffic and simplifies the shortest path computations of routers in other areas. However, if there is only one border router out of an area, even the summary does not need to be passed. Routes to destinations out of the area always start with the instruction go to the border router. This kind of area is called a stub area. The last kind of router is the AS boundary router. It injects routes to external destinations on other ASes into the area. The external routes then appear as destinations that can be reached via the AS boundary router with some cost. An external route can be injected at one or more AS boundary routers. The relationship between ASes, areas, and the various kinds of routers is shown in Figure 5 to 65. One router may play multiple roles. For example, a border router is also a backbone router. Area 2, stub. Area 0, backbone. Area 1 backbone router as boundary router internal router area border router 1 autonomous system Figure 5 to 65. The relation between ASes, backbones, and areas in OSPF. During normal operation, each router within an area has the same link state database and runs the same shortest path algorithm. Its main job is to calculate the shortest path from itself to every other router and network in the entire AS. An area border router needs the databases for all the areas to which it is connected and must run the shortest path algorithm for each area separately. For a source and destination in the same area, the best intra-area route that lies wholly within the area is chosen. For a source and destination in different areas, the inter-area route must go from the source to the backbone, across the backbone to the destination area, and then to the destination. This algorithm forces a star configuration on OSPF, with the backbone being the hub and the other areas being spokes. Because the route with the lowest cost is chosen, routers in different parts of the network may use different area border routers to enter the backbone and destination area. Packets are routed from source to destination as is. They are not encapsulated or tunneled unless going to an area whose only connection to the backbone is a tunnel. Also, routes to external destinations may include the external cost from the IS boundary router over the external path, if desired, or just the cost internal to the IS. When a router boots, it sends hello messages on all of its point-to-point lines and multicasts them on LANs to the group consisting of all the other routers. From the responses, each router learns who its neighbors are. Routers on the same LAN are all neighbors. OSPF works by exchanging information between adjacent routers, which is not the same as between neighboring routers. In particular, it is inefficient to have every router on the LAN talk to every other router on the LAN. To avoid this situation, one router is elected as the designated router. It is said to be adjacent to all the other routers on its LAN and exchanges information with them. In effect, it is acting as a single node that represents the LAN. Neighboring routers that are not adjacent do not exchange information with each other. A backup designated router is always kept up to date to ease the transition should the primary designated router crash and need to be replaced immediately. During normal operation, each router periodically floods link state update messages to each of its adjacent routers. These messages gives its state and provide the costs used in the topological database. The flooding messages are acknowledged to make them reliable. Each message has a sequence number, so a router can see whether an incoming link state update is older or newer than what it currently has. Routers also send these messages when a link goes up or down, or its cost changes. Database description messages give the sequence numbers of all the link state entries currently held by the sender. By comparing its own values with those of the sender, the receiver can determine who has the most recent values. These messages are used when a link is brought up. Either partner can request link state information from the other one by using link state request messages. The result of this algorithm is that each pair of adjacent routers checks to see who has the most recent data, and new information is spread throughout the area this way. All these messages are sent directly in IP packets. The 5 kinds of messages are summarized in figure 5 to 66. Message type description hello used to discover who the neighbors are. Link state update provides the sender's costs to its neighbors. Link state ACK acknowledges link state update. Database description announces which updates the sender has. Link state request requests information from the partner. Figure 5 to 66. The 5 types of OSPF messages. Finally, we can put all the pieces together. Using flooding, each router informs all the other routers in its area of its links to other routers and networks and the cost of these links. This information allows each router to construct the graph for its area or areas and compute the shortest paths. The backbone area does this work too. In addition, the backbone routers accept information from the area border routers in order to compute the best route from each backbone router to every other router. This information is propagated back to the area border routers, which advertise it within their areas. Using this information, internal routers can select the best route to a destination outside their area, including the best exit router to the backbone 5.6.7 BGP, the exterior gateway routing protocol within a single AS, OSPF and IS other protocols that are commonly used. Between ASes, a different protocol, called BGP, Border Gateway Protocol, is used. A different protocol is needed because the goals of an intradomain protocol and an interdomain protocol are not the same. All an intra-domain protocol has to do is move packets as efficiently as possible from the source to the destination. It does not have to worry about politics. In contrast, inter-domain routing protocols have to worry about politics a great deal. Metz, 2001. For example, a corporators might want the ability to send packets to any internet site and receive packets from any internet site. However, it might be unwilling to carry transit packets originating in a foreign AS and ending in a different foreign AS, even if its owners is on the shortest path between the two foreign ASes. That's their problem, not ours. On the other hand, it might be willing to carry transit traffic for its neighbors, or even for specific other ASes that paid it for this service. Telephone companies, for example, might be happy to act as carriers for their customers, but not for others. Exterior gateway protocols in general, and BGP in particular, have been designed to allow many kinds of routing policies to be enforced in the inter-AS traffic. Typical policies involve political, security, or economic considerations. A few examples of possible routing constraints are: 1. Do not carry commercial traffic on the educational network. 2. Never send traffic from the Pentagon on a route through Iraq. 3. Use Telia Sonera instead of Verizon because it is cheaper. 4. Don't use AT&T in Australia because performance is poor. 5. Traffic starting or ending at Apple should not transit Google. As you might imagine from this list, routing policies can be highly individual. They are often proprietary because they contain sensitive business information. However, we can describe some patterns that capture the reasoning of the company above, and that are often used as a starting point. A routing policy is implemented by deciding what traffic can flow over which of the links between ASes. One common policy is that a customer ISP pays another provider ISP to deliver packets to any other destination on the internet and receive packets sent from any other destination. The customer ISP is said to buy transit service from the provider ISP. This is just like a customer at home buying internet access service from an ISP. To make it work, the provider should advertise routes to all destinations on the internet to the customer over the link that connects them. In this way, the customer will have a route to use to send packets anywhere. Conversely, the customer should advertise routes only to the destinations on its network to the provider. This will let the provider send traffic to the customer only for those addresses the customer does not want to handle traffic intended for other destinations. We can see an example of transit service in figure 5 to 67. There are 4 ASes that are connected. The connection is often made with a link at IXPs, Internet Exchange Points, facilities to which many ISPs have a link for the purpose of connecting with other ISPs. AS2, AS3, and AS4 are customers of AS1. They buy transit service from it. Thus, when source A sends to destination C, the packets travel from AS2 to AS1, and finally to AS4. The routing advertisements travel in the opposite direction to the packets. AS4 advertises C as a destination to its transit provider, AS1, to let sources reach C via AS1. Later, American Samoa 1 advertises a route to C to its other customers, including AS2, to let the customers know that they can send traffic to C via AS1. TR AS1 AS2 AS3 AS4 a Peku TR path of BGP routing advertisements, path of IP packets, solid, routing policy, TR equals transit Q equals customer pair equals peer BC figure 5 to 67. Routing policies between 4 autonomous systems. In figure 5 to 67, all of the other ASes buy transit service from AS1. This provides them with connectivity, so they can interact with any host on the internet. However, they have to pay for this privilege. Suppose that AS2 and AS3 exchange a lot of traffic. Given that their networks are connected already, if they want to, they can use a different policy. They can send traffic directly to each other for free. This will reduce the amount of traffic they must have AS1 deliver on their behalf, and hopefully it will reduce their bills. This policy is called peering. To implement peering, 2 ASes send routing advertisements to each other for the addresses that reside in their networks. Doing so makes it possible for AS2 to send AS3 packets from A, destined to B and vice versa. However, note that peering is not transitive. In figure 5 to 67, AS3 and AS4 also peer with each other. This peering allows traffic from C destined for B to be sent directly to AS4. What happens if C sends a packet to A? AS3 is only advertising a route to B to AS4. It is not advertising a route to A. The consequence is that traffic will not pass from AS4 to AS3 to AS2, even though a physical path exists. This restriction is exactly what AS3 wants. It peers with AS4 to exchange traffic, but does not want to carry traffic from AS4 to other parts of the internet, since it is not being paid to so do. Instead, American Samoa 4 gets transit service from AS1. Thus, it is AS1 who will carry the packet from C to A. Now that we know about transit and peering, we can also see that A, B, and C have transit arrangements. For example, A must buy internet access from AS2. A might be a single home computer or a company network with many LANs. However, it does not need to run BGP because it is a stub network that is connected to the rest of the internet by only one link. So the only place for it to send packets destined outside of the network is over the link to AS2. There is nowhere else to go. This path can be arranged simply by setting up a default route. For this reason, we have not shown A, B, and C as ASes that participate in interdomain routing. On the other hand, some company networks are connected to multiple ISPs. This technique is used to improve reliability, since if the path through one ISP fails, the company can use the path via the other ISP. This technique is called multi-homing. In this case, the company network is likely to run an interdomain routing protocol, for instance, BGP, to tell other ASes which addresses should be reached via which ISP links. Many variations on these transit and peering policies are possible, but they already illustrate how business relationships and control over where route advertisements go can implement different kinds of policies. Now we will consider in more detail how a routers running BGP advertise routes to each other and select paths over which to forward packets. BGP is a form of distance vector protocol, but it is quite unlike intradomain distance vector protocols such as RIP. We have already seen that policy, instead of minimum distance, is used to pick which routes to use. Another large difference is that instead of maintaining just the cost of the route to each destination, each BGP router keeps track of the path used. This approach is called a path vector protocol. The path consists of the next hop router, which may be on the other side of the ISP, not adjacent, and the sequence of ASes, or AS path, that the route has followed, given in reverse order. Finally, pairs of BGP routers communicate with each other by establishing TCP connections. Operating this way provides reliable communication and also hides all the details of the network being passed through. An example of how BGP routes are advertised is shown in figure 5 to 68. There are 3 ASes and the middle one is providing transit to the left and right ISPs. A route advertisement to prefix C starts in AS3. When it is propagated across the link to R to C at the top of the figure, it has the AS path of simply AS3 and the next hop router of R3A. At the bottom, it has the same AS path, but a different next hop, because it came across a different link. This advertisement continues to propagate and crosses the boundary into AS1. At router R1A, at the top of the figure, the AS path is AS2, AS3 and the next hop is R2A. R3A prefix ABC AS1 AS2 AS3 path of packets R3B R2C R2 R2A R2B R1A R1BC AS2, AS3, R2AC, AS3, R3AC, AS2, AS3, R2BC, AS2, AS3, R1AC, AS2, AS3. R1B as path next hop C, AS3, R3B figure 5 to 68. Propagation of BGP route advertisements. Carrying the complete path with the route makes it easy for the receiving router to detect and break routing loops. The rule is that each router that sends a route outside of the AS prepends its own AS number to the route. This is why the list is in reverse order. When a router receives a route, it checks to see if its own AS number is already in the AS path. If it is, a loop has been detected and the advertisement is discarded. However, and somewhat ironically, it was realized in the late 1990s that despite this precaution, BGP suffers from a version of the count to infinity problem, Labovitz and others, 2001. There are no long-lived loops, but routes can sometimes be slow to converge and have transient loops. Giving a list of ASes is a very coarse way to specify a path. An AS might be a small company or an international backbone network. There is no way of telling from the route. BGP does not even try, because different ASes may use different intradomain protocols whose costs cannot be compared. Even if they could be compared, an AS may not want to reveal its internal metrics. This is one of the ways that interdomain routing protocols differ from intradomain protocols. So far we have seen how a route advertisement is sent across the link between two ISPs. We still need some way to propagate BGP routes from one side of the ISP to the other so they can be sent on to the next ISP. This task could be handled by the intradomain protocol, but because BGP is very good at scaling to large networks, a variant of BGP is often used. It is called IBGP, internal BGP, to distinguish it from the regular use of BGP as eBGP, external BGP. The rule for propagating routes inside an ISP is that every router at the boundary of the ISP blends of all the routes seen by all the other boundary routers, for consistency. If one boundary router on the ISP blends of a prefix to IP 128.208.0.0/16, all the other routers will learn of this prefix. The prefix will then be reachable from all parts of the ISP, no matter how packets enter the ISP from other ASes. We have not shown this propagation in figure 5 to 68 to avoid clutter, but, for example, router R2B will know that it can reach C via either router R to C at top or router R2 at bottom. The next hop is updated as the route crosses within the ISP, so that routers on the far side of the ISP know which router to use to exit the ISP on the other side. This can be seen in the leftmost routes in which the next hop points to a router in the same ISP and not a router in the next ISP. We can now describe the key missing piece, which is how BGP routers choose which route to use for each destination. Each BGP router may learn a route for a given destination from the router it is connected to in the next ISP and from all of the other boundary routers, which have had different routes from the routers they are connected to in other ISPs. Each router must decide which route in this set of routes is the best one to use. Ultimately the answer is that it is up to the ISP to write some policy to pick the preferred route. However, this explanation is very general and not at all satisfying, so we can at least describe some common strategies. The first strategy is that routes via peered networks are chosen in preference to routes via transit providers. The former are free, the latter cost money. A similar strategy is that customer routes are given the highest preference. It is only good business to send traffic directly to the paying customers. A different kind of strategy is the default rule that shorter AS paths are better. This is debatable given that an AS could be a network of any size, so a path through 3 small ASes could actually be shorter than a path through one big AS. However, shorter tends to be better on average, and this rule is a common tiebreaker. The final strategy is to prefer the route that has the lowest cost within the ISP. This is the strategy implemented in figure 5 to 68. Packets sent from A to C exit as 1 at the top router, R1A. Packets sent from B exit via the bottom router, R1B. The reason is that both A and B are taking the lowest cost path or quickest route out of AS1. Because they are located in different parts of the ISP, the quickest exit for each one is different. The same thing happens as the packets pass through AS2. On the last leg, AS3 has to carry the packet from B through its own network. This strategy is known as early exit or hot potato routing. It has the curious side effect of tending to make routes asymmetric. For example, consider the path taken. When C sends a packet back to B, the packet will exit AS3 quickly at the top router to avoid wasting its resources. Similarly, it will stay at the top when AS2 passes it to AS1 as quickly as possible. Then the packet will have a longer journey in AS1. This is a mirror image of the path taken from B to C. The above discussion should make clear that each BGP router chooses its own best route from the known possibilities. It is not the case, as might naively be expected, that BGP chooses a path to follow at the AS level and OSPF chooses paths within each of the ASes. BGP and the interior gateway protocol are integrated much more deeply. This means that, for example, BGP can find the best exit point from one ISP to the next, and this point will vary across the ISP, as in the case of the hot potato policy. It also means that BGP routers in different parts of one AS may choose different AS paths to reach the same destination. Care must be exercised by the ISP to configure all of the BGP routers to make compatible choices given all of this freedom, but this can be done in practice. Amazingly, we have only scratched the surface of BGP. For more information, see the BGP version 4 specification in RFC 4271 and related RFCs. However, realize that much of its complexity lies with policies, which are not described in the specification of the BGP Protocol 5.6.8. Internet multicasting normal IP communication is between one sender and one receiver. However, for some applications, it is useful for a process to be able to send to a large number of receivers simultaneously. Examples are streaming a live sports event to many viewers, delivering program updates to a pool of replicated servers, and handling digital conference, that is, multiparty, telephone calls. IP supports one-to-many communication, or multicasting, using Class D IP addresses. Each Class D address identifies a group of hosts. 28 bits are available for identifying groups, so over 250 million groups can exist at the same time. When a process sends a packet to a Class D address, a best effort attempt is made to deliver it to all the members of the group addressed, but no guarantees are given. Some members may not get the packet. The range of IP address is 224.0.0.0 over 24 is reserved for multicast on the local network. In this case, no routing protocol is needed. The packets are multicast by simply broadcasting them on the LAN with a multicast address. All hosts on the LAN receive the broadcasts, and hosts that are members of the group process the packet. Routers do not forward the packet off the LAN. Some examples of local multicast addresses are 224.0.0.1 all systems on a LAN 224.0.0.2 all routers on a LAN 224.0.0.5 all OSPF routers on a LAN 224.0.0.251 all DNS servers on a LAN other multicast. Addresses may have members on different networks. In this case, a routing protocol is needed. But first the multicast routers need to know which hosts are members of a group. A process asks its host to join in a specific group. It can also ask its host to leave the group. Each host keeps track of which groups its processes currently belong to. When the last process on a host leaves a group, the host is no longer a member of that group. About once a minute, each multicast router sends a query packet to all the hosts on its LAN, using the local multicast address of 224.0.0.1, of course, asking them to report back on the groups to which they currently belong. The multicast routers may or may not be collocated with the standard routers. Each host sends back responses for all the Class D addresses it is interested in. These query and response packets use a protocol called IGMP, Internet Group Management Protocol. It is described in RFC 3376. Any of several multicast routing protocols may be used to build multicast spanning trees that give paths from senders to all of the members of the group. The algorithms that are used are the ones we described in Secretary 5.2.8. Within an AS, the main protocol used is PIM, Protocol Independent Multicast. PIM comes in several flavors. In dense mode PIM, a pruned reverse path forwarding tree is created. This is suited to situations in which members are everywhere in the network, such as distributing files to many servers within a data center network. In sparse mode PIM, spanning trees that are built are similar to core-based trees. This is suited to situations such as a content provider multicasting TV to subscribers on its IP network. A variant of this design, called Source-Specific Multicast PIM, is optimized for the case that there is only one sender to the group. Finally, multicast extensions to BGP or tunnels need to be used to create multicast routes when the group members are in more than one as 5.6.9 mobile IP. Many users of the internet have mobile computers and want to stay connected when they are away from home and even on the road in between. Unfortunately, the IP addressing system makes working far from home easier said than done, as we will describe shortly. When people began demanding the ability anyway, IETF set up a working group to find a solution. The working group quickly formulated a number of goals considered desirable in any solution. The major ones were: 1. Each mobile host must be able to use its home IP address anywhere. 2. Software changes to the fixed hosts were not permitted. 3. Changes to the router software and tables were not permitted. 4. Most packets for mobile hosts should not make detours on the way. 5. No overhead should be incurred when a mobile host is at home. The solution chosen was the one described in Secretary the 5th of February 10. In brief, every site that wants to allow its users to roam has to create a helper at the site called a home agent. When a mobile host shows up at a foreign site, it obtains a new IP address, called a care of address, at the foreign site. The mobile then tells the home agent where it is now by giving it the care of address. When a packet for the mobile arrives at the home site and the mobile is elsewhere, the home agent grabs the packet and tunnels it to the mobile at the current care of address. The mobile can send reply packets directly to whoever it is communicating with, but still using its home address as the source address. This solution meets all the requirements stated above, except that packets for mobile hosts do make detours. Now that we have covered the network layer of the internet, we can go into the solution in more detail. The need for mobility support in the first place comes from the IP addressing scheme itself. Every IP address contains a network number and a host number. For example, consider the machine with IP address 160.80.40.20/16. The 160.80 gives the network number, the 40.20 is the host number. Routers all over the world have routing tables telling which link to use to get to network 160.80. Whenever a packet comes in with a destination IP address of the form 160.80.xxx.gii, it goes out on that line. If all of a sudden, the machine with that address is carted off to some distant site, the packets for it will continue to be routed to its home LAN or router. At this stage, there are two options, both unattractive. The first is that we could create a route to a more specific prefix. That is, if the distant site advertises a route to 160.80.40.20/32, packets sent to the destination will start arriving in the right place again. This option depends on the longest matching prefix algorithm that is used at routers. However, we have added a route to an IP prefix with a single IP address in it. All ISPs in the world will learn about this prefix. If everyone changes global IP routes in this way, when they move their computer, each router would have millions of table entries at astronomical cost to the internet. This option is not workable. The second option is to change the IP address of the mobile. True, packets sent to the home IP address will no longer be delivered until all the relevant people, programs, and databases are informed of the change. But the mobile can still use the internet at the new location to browse the web and run other applications. This option handles mobility at a higher layer. It is what typically happens when a user takes a laptop to a coffee store and uses the internet via the local wireless network. The disadvantage is that it breaks some applications and it does not keep connectivity as the mobile moves around. As an aside, mobility can also be handled at a lower layer, the link layer. This is what happens when using a laptop on a single 802.11 wireless network. The IP address of the mobile does not change, and the network path remains the same. It is the wireless link that is providing mobility. However, the degree of mobility is limited. If the laptop moves too far, it will have to connect to the internet via another network with a different IP address. The mobile IP solution for IPv4 is given in RFC 3344. It works with the existing internet routing and allows hosts to stay connected with their own IP addresses as they move about. For it to work, the mobile must be able to discover when it has moved. This is accomplished with ICMP router advertisement and solicitation messages. Mobiles listen for periodic router advertisements or send a solicitation to discover the nearest router. If this router is not the usual address of the router when the mobile is at home, it must be on a foreign network. If this router has changed since last time, the mobile has moved to another foreign network. This same mechanism lets mobile hosts find their home agents. To get a care of IP address on the foreign network, a mobile can simply use DHCP. Alternatively, if IPv4 addresses are in short supply, the mobile can send and receive packets via a foreign agent that already has an IP address on the network. The mobile host finds a foreign agent using the same ICMP mechanism used to find the home agent. After the mobile obtains an IP address or finds a foreign agent, it is able to use the network to send a message to its home agent, informing the home agent of its current location. The home agent needs a way to intercept packets sent to the mobile only when the mobile is not at home. ARP provides a convenient mechanism. To send a packet over an Ethernet to an IP host, the router needs to know the Ethernet address of the host. The usual mechanism is for the router to send an ARP query to ask, for example, what is the Ethernet address of 160.80.40.20? When the mobile is at home, it answers ARP queries for its IP address with its own Ethernet address. When the mobile is away, the home agent responds to this query by giving its Ethernet address. The router then sends packets for 160.80.40.20 to the home agent. Recall that this is called a proxy ARP. To quickly update ARP mappings back and forth when the mobile leaves home or arrives back home, another ARP technique called a gratuitous ARP can be used. Basically, the mobile or home agent send themselves an ARP query for the mobile IP address that supplies the right answer so that the router notices and updates its mapping. Tunneling to send a packet between the home agent and the mobile host at the care of address is done by encapsulating the packet with another IP header destined for the care of address. When the encapsulated packet arrives at the care of address, the outer IP header is removed to reveal the packet. As with many internet protocols, the devil is in the details, and most often the details of compatibility with other protocols that are deployed. There are two complications. First, NAT boxes depend on peeking past the IP header to look at the TCP or UDP header. The original form of tunneling for mobile IP did not use these headers, so it did not work with NAT boxes. The solution was to change the encapsulation to include a UDP header. The second complication is that some ISPs check the source IP addresses of packets to see that they match where the routing protocol believes the source should be located. This technique is called ingress filtering, and it is a security measure intended to discard traffic with seemingly incorrect addresses that may be malicious. However, packets sent from the mobile to other internet hosts when it is on a foreign network will have a source IP address that is out of place, so they will be discarded. To get around this problem, the mobile can use the care of address as a source to tunnel the packets back to the home agent. From here, they are sent into the internet from what appears to be the right location. The cost is that the route is more roundabout. Another issue we have not discussed is security. When a home agent gets a message asking it to please forward all of Roberta's packets to some IP address, it had better not comply unless it is convinced that Roberta is the source of this request and not somebody trying to impersonate her. Cryptographic authentication protocols are used for this purpose. We will study such protocols in Chapter 8. Mobility protocols for IPv6 build on the IPv4 foundation. The scheme above suffers from the triangle routing problem in which packets sent to the mobile take a dogleg through a distant home agent. In IPv6, route optimization is used to follow a direct path between the mobile and other IP addresses after the initial packets have followed the long route. Mobile IPv6 is defined in RFC 3775. There is another kind of mobility that is also being defined for the internet. Some airplanes have built-in wireless networking that passengers can use to connect their laptops to the internet. The plane has a router that connects to the rest of the internet via a wireless link. Did you expect a wired link? So now we have a flying router, which means that the whole network is mobile. Network mobility designs support this situation without the laptops realizing that the plane is mobile. As far as they are concerned, it is just another network. Of course, some of the laptops may be using mobile IP to keep their home addresses while they are on the plane, so we have two levels of mobility. Network mobility is defined for IPv6 in RFC 3963. 5.7 Summary. The network layer provides services to the transport layer. It can be based on either datagrams or virtual circuits. In both cases, its main job is routing packets from the source to the destination. In datagram networks, a routing decision is made on every packet. In virtual circuit networks, it is made when the virtual circuit is set up. Many routing algorithms are used in computer networks. Flooding is a simple algorithm to send a packet along all paths. Most algorithms find the shortest path and adapt to changes in the network topology. The main algorithms are distance vector routing and link state routing. Most actual networks use one of these. Other important routing topics are the use of hierarchy in large networks, routing for mobile hosts, and broadcast, multicast, and enocast routing. Networks can easily become congested, leading to increased delay and lost packets. Network designers attempt to avoid congestion by designing the network to have enough capacity, choosing uncongested routes, refusing to accept more traffic, signaling sources to slow down, and shedding load. The next step beyond just dealing with congestion is to actually try to achieve a promised quality of service. Some applications care more about throughput, whereas others care more about delay and jitter. The methods that can be used to provide different qualities of service include a combination of traffic shaping, reserving resources at routers, and admission control. Approaches that have been designed for good quality of service include IETF integrated services, including RSVP, and differentiated services. Networks differ in various ways, so when multiple networks are interconnected, problems can occur. When different networks have different maximum packet sizes, fragmentation may be needed. Different networks may run different routing protocols internally, but need to run a common protocol externally. Sometimes the problems can be finished by tunneling a packet through a hostile network, but if the source and destination networks are different, this approach fails. The internet has a rich variety of protocols related to the network layer. These include the datagram protocol, IP, and associated control protocols such as ICMP, ARP, and DHCP. A connection-oriented protocol called MPLS carries IP packets across some networks. One of the main routing protocols used within networks is OSPF, and the routing protocol used across networks is BGP. The internet is rapidly running out of IP addresses, so a new version of IP, IPv6, has been developed and is ever so slowly being deployed. 5.7 Summary. The network layer provides services to the transport layer. It can be based on either datagrams or virtual circuits. In both cases, its main job is routing packets from the source to the destination. In datagram networks, a routing decision is made on every packet. In virtual circuit networks, it is made when the virtual circuit is set up. Many routing algorithms are used in computer networks. Flooding is a simple algorithm to send a packet along all paths. Most algorithms find the shortest path and adapt to changes in the network topology. The main algorithms are distance vector routing and link state routing. Most actual networks use one of these. Other important routing topics are the use of hierarchy in large networks, routing for mobile hosts, and broadcast, multicast, and enocast routing. Networks can easily become congested, leading to increased delay and lost packets. Network designers attempt to avoid congestion by designing the network to have enough capacity, choosing uncongested routes, refusing to accept more traffic, signaling sources to slow down, and shedding load. The next step beyond just dealing with congestion is to actually try to achieve a promised quality of service. Some applications care more about throughput, whereas others care more about delay and jitter. The methods that can be used to provide different qualities of service include a combination of traffic shaping, reserving resources at routers, and admission control. Approaches that have been designed for good quality of service include IETF integrated services, including RSVP, and differentiated services. Networks differ in various ways, so when multiple networks are interconnected, problems can occur. When different networks have different maximum packet sizes, fragmentation may be needed. Different networks may run different routing protocols internally, but need to run a common protocol externally. Sometimes the problems can be finished by tunneling a packet through a hostile network, but if the source and destination networks are different, this approach fails. The internet has a rich variety of protocols related to the network layer. These include the datagram protocol, IP, and associated control protocols such as ICMP, ARP, and DHCP. A connection-oriented protocol called MPLS carries IP packets across some networks. One of the main routing protocols used within networks is OSPF, and the routing protocol used across networks is BGP. The internet is rapidly running out of IP addresses, so a new version of IP, IPv6, has been developed and is ever so slowly being deployed. Problems 1. Give 2 example computer applications for which connection-oriented service is appropriate. Now give 2 examples for which connectionless service is best too. Datagram networks route each packet as a separate unit, independent of all others. Virtual circuit networks do not have to do this, since each data packet follows a predetermined route. Does this observation mean that virtual circuit networks do not need the capability to route isolated packets from an arbitrary source to an arbitrary destination? Explain your answer. 3. Give 3 examples of protocol parameters that might be negotiated when a connection is set up for. Assuming that all routers and hosts are working properly, and that all software in both is free of all errors, is there any chance, however small, that a packet will be delivered to the wrong destination? 5. Give a simple heuristic for finding 2 paths through a network from a given source to a given destination that can survive the loss of any communication line, assuming 2 such paths exist. The routers are considered reliable enough, so it is not necessary to worry about the possibility of router crashes. 6. Consider the network of figure 5 to 12. Distance vector routing is used, and the following vectors have just come into router C from B, 5, 0, 8, 12, 6, 2, from D, 16, 12, 6, 0, 9, 10, and from E, 7, 6, 3, 9, 0, 4. The cost of the links from C to B, D, and E are 6, 3, and 5, respectively. What is C's new routing table? Give both the outgoing line to use and the cost. 7. If costs are recorded as 8-bit numbers in a 50 router network and distance vectors are exchanged twice a second, how much bandwidth per full duplex line is chewed up by the distributed routing algorithm? Assume that each router has 3 lines to other routers 8. In figure 5 to 13 the boolean, or of the 2 sets of ACF bits are 111 in every row. Is this just an accident here, or does it hold for all networks under all circumstances? 9. For hierarchical routing with 4800 routers, what region and cluster sizes should be chosen to minimize the size of the routing table for a 3-layer hierarchy? A good starting place is a hypothesis that a solution with k clusters of k regions of k routers is close to optimal, which means that k is about the cube root of 4800, around 16. Use trial and error to check out combinations where all 3 parameters are in the general vicinity of 16, 10. In the text it was stated that when a mobile host is not at home, packets sent to its home LAN are intercepted by its home agent on that LAN. For an IP network on an 802.3 LAN, how does the home agent accomplish this interception? 11. Looking at the network of figure 5 to 6, how many packets are generated by a broadcast from B using a reverse path forwarding? B. The sync tree. 12. Consider the network of figure 5 to 15. Imagine that one new line is added between F and G, but the sync tree of figure 5 to 15, B, remains unchanged. What changes occur to figure 5 to 15, C, 13? Computer multicast spanning tree for router C in the following network for a group with members at routers A, B, C, D, E, F, I, and K14. Suppose that node B in figure 5 to 20 has just rebooted and has no routing information in its tables. It suddenly needs a route to H. It sends out broadcasts with TTL set to 1, 2, 3, and so on. How many rounds does it take to find a route? 15. As a possible congestion control mechanism in a network using virtual circuits internally, a router could refrain from acknowledging a received packet until 1. It knows its last transmission along the virtual circuit was received successfully, and 2. It has a free buffer. For simplicity, assume that the routers use a stop and wait protocol, and that each virtual circuit has one buffer dedicated to it for each direction of traffic. If it takes T-secretary to transmit a packet, data, or acknowledgement, and there are n routers on the path, what is the rate at which packets are delivered to the destination host? Assume that transmission errors are rare, and that the host router connection is infinitely fast. 16. A datagram network allows routers to drop packets whenever they need to. The probability of a router discarding a packet is P. Consider the case of a source host connected to the source router, which is connected to the destination router, and then to the destination host. If either of the routers discards a packet, the source host eventually times out and tries again. If both host router and router lines are counted as hops, what is the mean number of hops a packet makes per transmission? B. Transmissions a packet makes. C. Hops required per received packet. 17. Describe two major differences between the ECN method and the RED method of congestion avoidance. 18. A token bucket scheme is used for traffic shaping. A new token is put into the bucket every 5 sec. Each token is good for one short packet, which contains 48 bytes of data. What is the maximum sustainable data rate? 19. A computer on a 6 Mbps network is regulated by a token bucket. The token bucket is filled at a rate of 1 megabits per second. It is initially filled to capacity with 8 megabits. How long can the computer transmit at the full 6 megabits per second? 20. The network of figure 5 to 34 uses a SVP with multicast trees for hosts 1 and 2 as shown. Suppose that host 3 requests a channel of bandwidth 2 MB/secretary for a flow from host 1 and another channel of bandwidth 1 MB/secretary for a flow from host 2. At the same time, host 4 requests a channel of bandwidth 2 MB/secretary for a flow from host 1 and host 5 requests a channel of bandwidth 1 MB/secretary for a flow from host 2. How much total bandwidth will be reserved for these requests at routers A, B, C, E, H, J, K, and L? 21. A router can process 2 million packets/secretary. The load offered to it is 1.5 million packets/secretary on average. If a route from source to destination contains 10 routers, how much time is spent being queued and serviced by the router? 22. Consider the user of differentiated services with expedited forwarding. Is there a guarantee that expedited packets experience a shorter delay than regular packets? Why or why not? 23. Suppose that host A is connected to a router R1, R1 is connected to another router, R2, and R2 is connected to host B. Suppose that a TCP message that contains 900 bytes of data and 20 bytes of TCP header is passed to the IP code at host A for delivery to B. Show the total length, identification, DF, MF, and fragment offset fields of the IP header in each packet. transmitted over the 3 links. Assume that link AR1 can support a maximum frame size of 1024 bytes including a 14 byte frame header. Link R1-R2 can support a maximum frame size of 512 bytes, including an 8 byte frame header, and link R2B can support a maximum frame size of 512 bytes including a 12 byte frame header 24. A router is blasting out IP packets whose total length, data plus header, is 1024 bytes. Assuming that packets live for 10 seconds, what is the maximum line speed the router can operate at without danger of cycling through the IP datagram ID number space? 25. An IP datagram using the strict source routing option has to be fragmented. Do you think the option is copied into each fragment, or is it sufficient to just put it in the first fragment? Explain your answer. 26. Suppose that instead of using 16 bits for the network part of a Class B address originally, 20 bits had been used. How many Class B networks would there have been? 27. Convert the IP address whose hexadecimal representation is C22F1582 to dotted decimal notation 28. A network on the internet has a subnet mask of 255.255.240.0. What is the maximum number of hosts it can handle? 29. While IP addresses are tied to specific networks, Ethernet addresses are not. Can you think of a good reason why they are not? 30. A large number of consecutive IP addresses are available starting at 198.16.0.0. Suppose that 4 organizations, A, B, C, and D, request 4,000, 2,000, 4,000, and 8,000 addresses, respectively, and in that order. For each of these, give the first IP address assigned, the last IP address assigned, and the mask in the WXYZ/S notation 31. A router has just received the following new IP addresses: 57.6.96.0/21, 57.6.104.0/21, 57.6.112.0/21, and 57.6.120.0/21. If all of them use the same outgoing line, can they be aggregated? If so, to what? If not, why not? 32. The set of IP addresses from 29.18.0.0 to 19.18.128.255 has been aggregated to 29.18.0.0/17. However, there is a gap of 1024 unassigned addresses from 29.18.60.0 to 29.18.63.255 that are now suddenly assigned to a host using a different outgoing line. Is it now necessary to split up the aggregate address into its constituent blocks, add the new block to the table, and then see if any reaggregation is possible? If not, what can be done instead? 33. A router has the following CIDR entries in its routing table: address/mask next hop 135.46.56.0/22 interface 0135.46.60.0/22 interface 1. 192.53.40.0/23 router 1 default router 2 for each of the following IP addresses. What does the router do if a packet with that address arrives? 135.46.63.10 B. 135.46.57.14 C. 135.46.52.2 D. 192.53.40.7 E. 192.53.56.7 34. Many companies have a policy of having 2 or more routers connecting the company to the internet to provide some redundancy in case one of them goes down. Is this policy still possible with NAT? Explain your answer. 35. You have just explained the ARP protocol to a friend. When you are all done, he says, "I've got it." ARP provides a service to the network layer, so it is part of the data link layer. What do you say to him? 36. Describe a way to reassemble IP fragments at the destination. 37. Most IP datagram reassembly algorithms have a timer to avoid having a lost fragment tie up reassembly buffers forever. Suppose that a datagram is fragmented into 4 fragments. The first 3 fragments arrive, but the last one is delayed. Eventually, the timer goes off, and the 3 fragments in the receiver's memory are discarded. A little later, the last fragment stumbles in. What should be done with it? 38. In IP, the checksum covers only the header, and not the data. Why do you suppose this design was chosen? 39. A person who lives in Boston travels to Minneapolis, taking her portable computer with her. To her surprise, the LAN at her destination in Minneapolis is a wireless IP LAN, so she does not have to plug in. Is it still necessary to go through the entire business with home agents and foreign agents to make email and other traffic arrive correctly? 40. IPv6 uses 16-byte addresses. If a block of 1 million addresses is allocated every picosecond, how long will the addresses last? 41. The protocol field used in the IPv4 header is not present in the fixed IPv6 header. Why not? 42. When the IPv6 protocol is introduced, does the ARP protocol have to be changed? If so, are the changes conceptual or technical? 43. Write a program to simulate routing using flooding. Each packet should contain a counter that is decremented on each hop. When the counter gets to 0, the packet is discarded. Time is discrete, with each line handling 1 packet per time interval. Make 3 versions of the program. All lines are flooded, all lines except the input line are flooded, and only the statically chosen best K lines are flooded. Compare flooding with deterministic routing. K equals 1 in terms of both delay and the bandwidth used. 44. Write a program that simulates a computer network using discrete time. The first packet on each router queue makes 1 hop per time interval. Each router has only a finite number of buffers. If the packet arrives and there is no room for it, it is discarded and not retransmitted. Instead, there is an end-to-end protocol, complete with timeouts and acknowledgement packets, that eventually regenerates the packet from the source router. Plot the throughput of the network as a function of the end-to-end timeout interval, parameterized by error rate. 45. Write a function to do forwarding in an IP router. The procedure has 1 parameter, an IP address. It also has access to a global table consisting of an array of triples. Each triple contains 3 integers, an IP address, a subnet mask, and the outline line to use. The function looks up the IP address in the table using CIDR and returns the line to use as its value. 46. Use the traceroute, Unix, or Tracit, Windows, programs to trace the route from your computer to various universities on other continents. Make a list of transoceanic links you have discovered. Some sites to try are www.berkeley.edu, California, www.mid.edu, Massachusetts, www.vu.nl, Amsterdam, www.ucl.ac.uk, London, www.ucrd.au, Sydney, www.utokyo.ac.jp, Tokyo, www.uct.ac.zap, Cape Town,